Hi guys, my name is Karthik Arula and in this video we'll be solving the problem R, that is walk. So you can go through the problem once if you'd like and then we'll discuss it. Okay, we are given a directed graph G. It has n vertices and some edges, of course. Then what we are supposed to find out is we would like to find the count of the total number of paths that are of length exactly k. Okay, so number of paths that are of length exactly k, that is what we are supposed to find. So the question is very much straightforward. Let's look at a sample input and it will be more clear. Also the constraints here can be seen that n is up to 50 and k is up to 10 to the power 18. All right. So you can see the sample input 1, we have the following graph. You can see the diagram. Here we wanted to find out all the paths of length 2. So we have one path like this, maybe another like this, and starting from 2 we have this one path and also this one path. So there are overall of 6 paths and you can see which paths they are talking about. So one of the paths is 1, 2, then 3, then 1, 2, 4, 2, 3, 4. Alright, so it's very much clear. Let's just check the sample input 2 as well. Here we would like to find out all the paths of length exactly 3. Here we have 3 such paths. So one of them is 1, then 2, then back to 1 and then back to 2. This is one path. Another might be 1, 2, 3. That is not a okay. Sure, we can start from 2 as well. So 2, 1, 2 and then 3 and 2, 1, 2, 1. Okay, cool. You can see the sample input 3 as well if you'd like. We wanted to find out all the paths of length exactly 2 and there is only one such path, that is 4, then 5, then 6. Path length is 2 and there is no other path of length 2 exactly 2. Okay, alright. So I'll be describing 2 solutions in this video, and first of all we'll discuss a more intuitive solution which is n into k in complexity, and then we'll consider a more optimized solution for the problem. So now I'll be moving towards the solution. Alright guys, so we want to find the total number of paths of length exactly k in the given graph. Okay, now let's say to find the total number of paths of length exactly k, my path could begin at any vertex of the graph, right? So it could begin at any node u and it might end at any other node v, so that this length of this path is exactly k, right? I have to count all such paths. Now let's say instead I simplify the problem. I reduce this problem to the following. Okay, so let's say dp of u is the number of paths that start at node u and might end at any other node but are of length exactly k. Okay, so this is the total number of paths starting at node u and are of length exactly k. I'll just write this down. Number of paths that start at node u and are of length exactly k. Okay, so if I know dp of u for all the u, that is all u from 1 to n for every node, then my answer will simply be summation dpu where u goes from 1 to n, or summation dpi, and I could be any node from 1 to n, right? And this will be my answer. So I'll basically be counting all the possible, I'll be taking each and every node and seeing how the number of paths of length exactly k that start at the ith node, and then I'll sum them up and I can have my solution. Okay. Also, to find out dp of u, I'll have to think about the number of paths that start at some child node of u, right? So if this is node u and I wanted to find out all the k length paths starting at u, and there are some children of u, maybe c1, c2 up to ck, maybe not k, let's say cx maybe. All right, then what I would like to know is, if I knew the number of paths that are of length exactly k minus 1 starting at c1, starting at c2 and up to cx, then I could simply add those and I will get dp of u, right? So I'll introduce another variable in my dp. Now I'll be calling it dp of u comma k. Now dp of u comma k means the number of paths that are of length exactly k that and start at the node u. Better let's call it dp of uj. All right. Okay. Then as very much clear from this diagram, dp of uj can easily be written as dp of ci comma j minus 1, where ci is a child of u. C is a child of u, right? So by doing this, we'll be able to find out dp of uk for every node, right? And then we'll simply then our answer will simply become summation dpi comma k over all nodes 1 to n, right? Then this will be our final answer. So I hope this solution is clear to you, but the time complexity here will be big O of n into k, and as we saw that k is equals to 10 to the power 18, so this solution will definitely time out and we need to think of a better solution. Alright, so let's try to think of a better solution now. Okay, so first of all, I know one thing. If I knew basically the number of paths that start at some node x and end at some node y, which are of length exactly k, then I could definitely do one thing. I could take all the possible pairs and sum them up to get my answer. Okay, so what I am thinking of is the number of paths that start at some node u and end at some node v, such that this path length is exactly k. Alright, so for every pair, if I am able to find this thing out, the number of paths that start at some x and end at some other node y, so that the path length is exactly k, then if I'm able to find this thing out for each and every pair of nodes in the graph, then I know one thing, that my answer will simply be number of paths of length k, number of paths of length k that start at u and end at v for all valid pairs u comma v in the graph. For all valid pairs u comma v, right? So if the graph had 3 nodes, then I could find this thing. All the paths that start at node number 1 and end at node number 1, which have a path of exactly k. Also I could find out 1 comma 2, all paths starting at 1 ending at 2 and having a path length k. Same way 1 comma 3, then 2 comma 1, 2 comma 2, 2 comma 3, and similarly all the paths that start at node number 3 end at node number 2 and have a path length exactly k, then adding these guys up will give me my answer, right? Okay. So it might seem reasonable to represent these as a matrix. So here we have 1 comma 1, 1 comma 2 up to 1 comma n. So these are all the these entry basically represent the number of paths starting at node number 1 and ending at node number 2, 3 and up till n, and are of length exactly k. Alright, then again the second entry will look like something like this: 2 comma 1 meaning the number of paths starting from node number 2 ending at node number 1 and having a length exactly k. And similarly we can have this kind of matrix, right? Okay. And finally n comma n, number of paths that start at node number n, end at node number n, and have a path length of exactly k. If we were able to find out this matrix, our answer will simply be the sum of the entries of this matrix. Now let's think how we can find it. Okay, so what I am going to try is, I'm going to think of this. I'm going to assume that I have the matrix ak minus 1. Okay, let's define this as ak in the sense that the entries of this matrix sorry, yeah, ak in the sense that the entries of this matrix represents all the paths starting at some u ending at some node v and having length exactly k. So what I'm going to try is, I'm going to try to calculate ak using ak minus 1. Okay, so I'll assume that I know what ak minus 1 is, and I'm going to use ak minus 1 to find out ak. So here now let's assume I have ak minus 1 and try to calculate ak. Okay, so imagine that I'm trying to calculate ak and I'm calculating the first 1 comma 1 entry for this. So this means all the paths starting from node 1 ending at node 1 and having a length exactly k. Okay, now all the paths that start from node number 1, reach some node, some intermediate node, maybe just a second, reach some node, let's call this node maybe x, and then reach back to node number 1. Okay, and if this 1 to x path length is k minus 1 and then this path length is 1, then all these paths that go from node number 1 to some other node x using a path length of k minus 1 and then can go from x back to 1 must be counted in this entry, right? These are basically the paths that are going to make this entry, right? Okay, so we know 1 to x, basically let's choose all the possible intermediate nodes and go from node number 1 to 1. Okay, so go from 1 to 1 using a path length of k minus 1, and if then there is a loop on 1, basically an edge from 1 to 1, then I could go back to 1. Another way here would be, I start from node number 1, use a k minus 1 length path, reach node number 2, and if there exists an edge from 2 to 1, then I could use it, and all these paths of length k minus 1 from 1 to 2 must be added in the number of paths from 1 to 1 with length k, right? Okay, so hopefully this is making sense to you. I'll make it a little bit more clear now, a little more concrete. Alright, so as we saw, to calculate 1 comma 1, we're simply going to do this thing. Take any intermediate node x, see how many paths exist from 1 to x, and as many paths must be added to 1, and if there is an edge from x to 1, then simply add the number of paths from 1 to x, okay, to this entry. So this entry will simply become something like this: ak 1 comma 1 will become this thing, AK. Go from the first node to any other intermediate node X, and then there should also be some paths from X to 1, right? From X back to 1 also there must be a path. So we can know this by using the adjacency matrix ADJ, right? ADJ simply represents whether there is an edge from some particular node I to some particular node J. So ADJ at I comma J represents if there is an edge from I to J, then ADJ IJ will be 1 if there is an edge, otherwise it will be 0. So what I could do here is I could simply multiply this thing with ADJ adjacency matrix of X comma 1. So if there is an edge from node number X to node number 1, then I must be adding all these paths from 1 to X to AK 1 comma 1 entry, right? And over all X, all the possible intermediate nodes from 1 to N. So this thing must be clear to you. Just a little bit of correction, this has to be AK minus 1, right? Paths start from 1 and have a length exactly k minus 1 and reach X, okay? So this has to be A of k minus 1, okay? Okay. So if you pay a little bit more closer attention to this thing, what's basically happening is to calculate AK 1 comma 1, what we are doing is we are taking AK minus 1 and we are taking the matrix ADJ and we're simply choosing 1 comma some entry X from here and multiplying it with the X comma 1, right? So xth row here and the first column. What we're doing to calculate 1 comma 1 is we're taking 1 comma xth entry from AK minus 1 and the X comma 1th entry from ADJ and getting 1 comma 1. So let's try and write for AKIJ. Okay. So for AKIJ it will simply be number of nodes starting at node I ending at node J and of length exactly k. Choose a k minus 1 length path that starts at node I, ends at any intermediate node X, and then if there is an edge from node X back to node I, which is represented by ADJ X comma I, then add it to AKIJ. Overall possible intermediate nodes from 1 to N. So if you pay a little bit of attention to this thing, this is nothing but to calculate AK, you have to do a matrix multiplication of AK minus 1 and ADJ, right? So for calculating the I comma J entry, you will take the I comma xth element here and you will take the X comma ith element here and multiply this ith row of this matrix with the ith column of this matrix, right? So this is nothing but matrix multiplication of AK minus 1 and ADJ to get AK. Alright, so now I can write this. So to calculate the entire matrix AK, my AK is simply AK minus 1 into ADJ matrix multiplication. So this is an interesting relation. However, this still does not solve our problem, not yet. Let's see what A of 1 is. Okay, so A of 1 simply represents the number of paths that start at node number I, end at node number J, and are of length exactly 1. So this means nothing but that there should be an edge from node I to node J. This is represented by ADJ matrix itself, right? So A1 is nothing but ADJ. Now using 1 and 2, what you can infer is that A1 equals to ADJ, which is okay, and A2 is nothing but A1 into ADJ, right, from the previous relation, which is nothing but ADJ into ADJ, and that is ADJ raised to the power 2. Similarly, A3 equals to A2 into ADJ, which is ADJ raised to the power 3. So the thing that we would like to find out was AK, which is nothing but adjacency matrix raised to the power k. Now this is an interesting relationship. Finding ADJ raised to the power k is much easier than you can think. So if you are aware of the technique matrix exponentiation, okay, if you're aware of this technique called matrix exponentiation, then you would know that calculating ADJ to the power k can be done in n cube log of k using matrix exponentiation. If you're not aware of this technique, I'll be describing it in brief. So let's see how you can calculate some matrix A to some integer power k. Okay, so if k was in, so I could write AK as AK by 2 into AK by 2 if k was even, right? Otherwise I could write it as A into AK by 2 ceiling into AK by 2 ceiling if k is odd, right? Because if k was equals to 4, I could calculate a square and multiply them to get a to the power 4. And if k, let's say k is equals to 5, I could say okay, a into a to the power 4, that is nothing but a square and a square. So using this kind of divide and conquer to evaluate a to the power k, using this we can calculate a to the power k in log n log k matrix multiplications, and to multiply these matrices here, this takes n cube time, so this thing will take n cube log k time. Okay, all right, so hopefully this thing is clear to you how matrix multiplication works. If it is not, with the implementation it will be clear to you. All right, so now we know that AK is equals to ADJ to the power k, and we know that finding ADJ to the power k can be done in n cube log k time, and n is up to 50 and k is up to 10 to the power 18. So this is very much doable in the time limit, and once I've found out AK, my final answer will simply be nothing but summation AK at ij for all ij, right? For all I, comma j pairs, or you could make it a double summation. This I goes from 1 to n and j goes from 1 to n. All right, so guys, hopefully this solution is very much clear to you, and now I'll be moving towards the implementation of the solution. So guys, you can see here that I have taken the input, the number of nodes in the graph, and the required path length. Then I've made this adjacency matrix. Again, I've simply taken the input here, the matrix, and I've called the function solve with the matrix and the value k. Okay, and maybe also let's just pass in. I don't think it will be needed, but let's just pass it. Alright, so as discussed, we are supposed to find out the kth power of ADJ, and let's have a function to do that. So I will call power ADJ comma k. Okay, and I'll get my result here. So let's call my result AK. It's going to be a vector of vector because it's a matrix. So let's say vector AK is equals to power ADJ to the power k and then simply for every valid ij from 0 I less than n I plus alright, then my answer equals to answer plus ak at ij and then this whole mod 10 to the power 9 plus 7. Okay, once I've done this, all I need to do is return the answer. Okay, now we are supposed to make the power function as well. So let's just this power function is going to return a vector to me, basically a matrix. So power, it receives the matrix mat. Okay, then also value the exponent I need to raise this matrix to, and then what I'm going to do is if exponent is equals to 1, and in fact if exponent is equals to 0, then return, or maybe let's just take exponent equals to 1, and in that case I'm going to return what? The same matrix. Otherwise I'll be calculating matrix to the power exponent by 2. Okay, so let's take another matrix. Res equals to power matrix comma exp by 2. Now if the exponent was odd, in that case I have to return matrix multiplied by result, and else I have to return result into result, right? So this is very much clear, but of course I cannot simply multiply two matrices using this multiply operator, so I'll have to define that thing as well. So let's say I'll be making a function, and this will simply be multiply matrix comma result, and then whatever the result is, multiply it with res. Okay, and here also multiply res and return the result. Okay, now we are supposed to make this multiply function which receives two matrices. Yeah, it seems alright to me now. Okay, so I'll make a function that multiplies two matrices and returns in the product. So multiply, let's just call these matrices A and B. Okay, and the resultant matrix can be called C or maybe result. Of course, this should have the dimension n comma n, and n is nothing but a dot size. Okay, now to multiply two matrices, I'll run basic idea is a res at ij is equals to the multiplying the ith row of A and the jth column of B, right? So I'll be doing that only. So currently I'm evaluating the ith entry of C and the jth entry of I comma jth entry of C, right? Less than n. So I'm calculating Cij. Now to calculate Cij, I have to take Aix and Bxj, right? So res at, so for some x equal to 0, x less than n, then res at ij equals to res at ij plus a at ix, the ith row of a multiplied by the multiplied by the jth column. Is it? I guess so. Let me just check for a second. Alright, so that is simple matrix multiplication, and I think that is the correct formula for it. If we get a wrong answer, I'll just check it, but yeah, that's the formula. And finally I'm gonna return the result. Okay, so this looks alright to me, except I'll just use LL everywhere to avoid, or maybe just LL in the res to avoid any intermediate overflows. And once I'm calculating this, I'll be doing modulo 10 to the power 9 plus 7. Okay, so I'm guessing that this should work. Let's just try a sample input. So there is an error on line 48. Okay, oh sorry, line 99. Vector LL res n comma vector int n comma 0. So this looks alright to me, I think. Okay, this has to be LL. Could not convert res from, could do this, but then if I do that, and what happens is that this result should also be long. Okay, then I'll simply take longs everywhere. Mm, 933, return mat has to be a long. Okay, so I am simply making all the matrices to longs. Yeah, I guess now we're done. Okay, so line 45, answer equal to, yeah, this will be LL answer equals to 0. Okay, now we're getting an output, but of course it's incorrect. Let's check what's the mistake. Okay, so I am feeling that there is something here, and for I from 0 to n, I plus plus. Okay, so yeah, there was a error in this increment, and it might work now. Segmentation fault. Okay, so if exponent equal to 1, and this thing should not have given me an error. Let me just see what the possible cause for this could be. Let me just do one thing. Assert that exponent is greater than equal to 1. If this assertion fails, then this means I'm doing something incorrect in my power function. In fact, this is a compilation error. Alright, so let me just check the multiply function again. So I have made really big problems here. I did not basically this j loop was copied incorrectly. Cool. Now I think it should give me the correct output. So yes, we're getting the correct output now. I'll try and submit it. So I think this should pass. Till then, let's just discuss. So this multiply function simply works in big O of n cube since there are 3 loops. Okay. And then we have this power function. This power function works in big O of log of this exponential, plus this multiply function was causing n cube. So this is, since this is running in log exponent, and every time this runs the multiply is called, so n cube log into exponent, that is this exponent is initially k, so n cube log k, and finally we have this function solve, firstly n cube log k for this thing, and then big O of n square for this. So overall time complexity for this was n cube log k, and as you can see we got an AC. So guys, hopefully the video was helpful to you. Thanks for watching. Bye bye. Hi everyone, my name is Karthik Arora. In this video we'll be solving S digit sum. Okay. So guys, this is a very nice problem based upon digit DP, and we'll be solving it after discussing a brute force. So you can read the problem once. Here we are given with two integers k and d, and k can be up to 10 raised to power 10,000, which is quite huge. Okay, and this d can be up to 100. So what our goal is that we have to count the number of numbers. Okay, count the count of numbers from 1 to k such that the sum of the digits of a number, let's say we choose some number x between the numbers from 1 to k, then the sum of digits of x modulo this d must be equal to 0. Okay, so we have to count all such numbers. So first of all, let's discuss a brute force for this. A brute force is to simply generate all the numbers from 1 to k and then take the sum of the digits of the number, and if that sum modulo d is equals to 0, then add 1 to the answer. Okay, so I generate 1, I check what 1 mod d is, then I generate 2, I check what 2 mod d is, and let's say k is maybe some huge number, maybe 9876. Okay, then I'll be going up to k, so let's say I generate 5031. Then here the sum of the digits is 5 plus 3 plus 1, which is equals to 9, and I'll check what 9 mod d is. If it is 0, then I'll be adding 1 to my answer, and let's say I generate some number 6892. Then I'll be adding the digits, and the sum will be 6 plus 8 plus 9 plus 2, which is 10, 16 and 25. Okay, then I'll check what 25 mod d is. If it is 0, then I'll be adding 1 to the answer, and I can do this up till I reach the largest number, that is k, and then I'll simply display the answer. Okay, this solution is big O of k log k base 10. Okay, because there are k numbers to check, and for each number to find the sum of the digits, it will take log k time. Okay, now of course this solution will time out given that k is up to 10 to the power 10,000. So let's first of all check the sample inputs and we'll think of a solution then. Here you can see the sample input 1. We are given with k equal to 30 and d equal to 4. Here they say that there are 6 integers in the range 1 to 30, so that the sum of the digits modulo 4 is 0. So 4 mod 4 is 0, 8 mod 4 is 0, 13 is sum of digits is 1 plus 3 equal to 4, and 4 mod 4 is 0. Again 1 plus 7 8, 2 plus 2 4, and 26. Okay, so again for here we want to count all the digits such that sum of all those numbers whose sum of digits modulo 1 is 0, and no matter what the sum is, modulo 1 is always 0. So here in this case the total count will be 10 to the power 9, or 10 to the power 9 plus 9, and then modulo 10 to the power 9 plus 7, so answer becomes 2. Okay, alright, so guys, hopefully the problem statement is clear to you, and now we'll be moving towards the solution. Okay, so we are solving S digit sum. So given an integer k, and as we saw, k can be very huge, up to 10 to the power 10,000. So let's say that the input number k has n number of digits, and it is something like this, d1 d2 up to dn, so that n is at most 10,000. Okay, so here what we can see is that we have a very huge number. We will input it as a string maybe, since long and integer will overflow and they cannot hold such a huge integer. Now what we wanted to do was generate the count of the numbers such that the sum of their digits modulo capital D was equal to 0. Alright, so first of all let's solve an easier version of the problem. So in the easier version, instead of having the upper limit of k, let's instead generate all the numbers which have n digits. Alright, so instead of having this k d1 d2 up to dn, I am assuming that k is up to 999 n times. Alright, so maybe if k was 8962, then this version will have k as 9999. Okay, so this basically means that now we just have to generate all the 4-digit numbers so that the sum of their digits modulo capital D is equals to 0. Okay, so let's first solve this problem, and then we'll see how we can use the solution to this easier version to solve the actual version of the problem. Okay, so now to generate all the n digit numbers, first of all we will not have to generate n minus 1 digit numbers again or something like that, because an n digit number, and since we are in which leading zeros are allowed, will basically generate all the possible numbers up to this number. Okay, so this is also an n digit number. Okay, this is a 4-digit number and it's 0. Okay, cool. Also in our original problem the range is 1 to k, but let's say for now I'm also taking 0, so currently I'm evaluating the range 0 to 99999, and this has n digits. Okay, this number. Alright, so let's solve the easier problem now. So guys, let's think about it. I am trying to generate an n digit number, and let's assume once I've fixed all, currently no digit has been fixed, and once I have fixed all the digits, let's say that the sum turns out to be s. Okay, now according to the problem, if s mod d is 0, then I will be counting it into my total count. Okay, so consider this example. Currently let's say I'm generating all the 5-digit numbers, and the sum of their digits must be a multiple of d. Basically should modulo d, the sum should be 0. Okay, so let's think about fixing the leftmost digit now. I could write any number from 0 to 9 in this position. So let's say I write x, so that 0 less than equal to x and less than equal to 9. Okay, so what happens after this? Now the count of all the 5-digit numbers such that they start with an x. Okay, we can find that using we can find that if we knew the count of all the 4-digit numbers such that their sum modulo d equal to something. Let's find that something first. Okay, so we wanted s mod d to be 0. Now since we have fixed the first position to be x, then I can write capital S as x plus s, and the small s is the sum of the digits, basically sum of these 4 digits. We want x plus small s mod capital D to be 0. So now I can use the property of modulo, and then I get x mod d plus small s mod d whole mod d equal to 0. Now I'm interested in finding out what is s mod d, because then I can reduce this thing to a sub problem in which the sum of the digits to find all these 4-digit numbers, so that the sum of their digits small s modulo d is something, and let's find what that something has to be from this equation. Okay, so let's just say that I'm removing this modulo for now and that means that x mod d plus s mod d has to be a multiple of d, which means small m into capital D, and this small m is an integer. Sorry. So this gives us that s mod d has to be small m into d minus x mod d, right? And since both the sides are under the modulo d, it is all right to add okay, before I do that, so just one thing, it is all right to do this thing, add d to both the sides and then take a modulo d on both the sides, right? Because that way I am not doing anything to any of the equations. Initially I'm adding a d to both the sides and doing a modulo. So add a d here and also add a d here. Okay, and now take the modulo d on both the sides. What happens is, after taking the modulo d on these two things, we get this s mod d. You can try on the LHS, because the LHS will break into d mod d plus s mod d whole mod d, and then that is simply s mod d whole mod d, which is again s mod d. So I get the LHS to be s mod d, but for the RHS what I get is, I get this thing d minus x mod d whole mod d. Okay, it is very easy to verify. You can verify this thing, but with this I have a new, basically I have a way to say what the sum of this digits modulo d should be. It should simply be d minus x mod d, right? S should simply be d minus x mod d under the modulo d. All right, so I'll be raising this now and we'll just keep the result. Okay, so how this helps me is that once I know, now I can fix the first position, right? Now to count all the numbers with 5 digits that start with an x. Okay, this x can go from anywhere from 0 to 9. What I need to find out is the number of 4-digit numbers such that their sum modulo capital D is equals to d minus x mod d. Okay, so I've broken down my problem into a smaller sub problem. Give this result. Okay, and next time, now I want that the sum of these digits modulo capital D should be d minus x modulo d. Okay, now let's say I wanted that the sum of these digits modulo capital D is equals to d. Okay, so s mod cap d equal to small d. You can easily use the same equations and find out, if I put a y here, and y can also be anywhere from 0 to 9, what should be the sum of these digits mod d. Okay, I'll quickly write the equation for that as well. So small s is the sum of the digits for the 4 places, and let's say this is s dash. Okay, so let's just try and find out what s dash should be. S dash mod d. So I have that small s mod d equal to small d, then I can write this as y plus s dash whole mod d is equals to small d. This becomes y mod d plus s dash mod d. This is what we are interested in. Whole mod d is equals to small d. Now removing this mod d from both the sides, this simply becomes equal to a multiple of d plus small d. And then what happens is, I can take this to the left RHS, and I guess I get S dash mod, sorry, this has to be capital D. Okay, I get S dash mod D should be equal to MD plus D minus phi mod D. Okay, now I could simply do the same thing as before, add D to both the sides, and then mod with D both the sides, and I get this thing. S dash mod D should be equal to, this side becomes D plus D minus Y mod D whole mod D. Okay, so hopefully now this thing is clear how our problem is breaking down into smaller sub problems. Now let's define a term dp of position comma small d. Okay, I'll tell you what it means. Hopefully this thing is clear to you. Okay, so let's define dp of position comma small d. This is the count of all the numbers such that all the positions starting with POS and up to capital N are not yet fixed. Okay, so let's say, in fact let's say 0th position, first position, second position, and so on till n minus 1th position. Okay, so what dp of pos comma d signifies is that we are still yet to basically fix the positions from POS till the last position. So that means that we have fixed all the positions from 0 to pos minus 1. So this is the number of, or count of numbers, such that we are yet to fix digits in the places just a second. Yeah, digits in places starting with pos up to n minus 1. Okay, count of numbers so that we are yet to fix the digits in the places from pos to n minus 1, and after fixing these digits, the sum of these digits modulo capital D, the sum of these digits that we are about to fix modulo capital D equals to small d. Okay, so hopefully dp of pos comma d is clear, and with this definition our answer to the easier version of the problem becomes dp of 0 comma 0, which simply means that we are yet to fix all the numbers starting from the 0th position up till the n minus 1th position, and after fixing these positions the sum of the digits has to be modulo d 0. Okay, all right, so this is the answer to our easier version problem, and this is a definition. Let's try and write a recurrence for this thing. So dp of pos comma d. Now let's try and fix the pos number of the position POS. So I could write a 0, I could write a 1, and I could up till write a 9. So let's say I fixed the position to be x. Then after fixing that to be x, after I fixed the POS position to be x, then dp of pos plus 1 comma something. Okay, now what this something has to be, we found it from our equations, and this something turns out to be d plus d minus x mod d. Okay, and x is the number that we have fixed at the POS position. So this becomes d plus d minus x mod d. Okay, over all the possibilities of x starting from 0 up till 9, and this is what dp of pos comma d is. So guys, you can take a minute to understand this, but now we have reached the solution to the easier version of the problems. given that we had to generate all the numbers from 1 to k only, but we are generating all the n digit numbers including 0 and also some numbers which are greater than k, which we have to avoid generating. All right, so let's see how we can solve the actual problem. Okay, here the major thing here is that here our summation runs from x equal to 0 to 9. Okay, so let's say in our original problem we had an input number d1, d2, d3, d4 and d5. Okay, this was our k. It had 5 digits and the digits were these d1, d2 up to d5. Now while generating all the 5-digit numbers, what we were doing is we were assuming that any number could be anywhere from 0 to 9, any digit basically. So now we have to take care that we never exceed capital K. Okay, and counting 0, that can be easily managed. I'll discuss it later, but let's first of all see how we have to manage not exceeding K. Okay, so let's say now this is the number which we are generating using our algorithm. So initially we were writing all the numbers from 0 to 9 here, but very clearly if let's say d1 is equals to maybe 5, then I cannot write any number which is greater than equal to 5 here. Okay, so instead of going from 0 to 9, I should only go from 0 to 5 for the first position, since there is a tight bound of 5 here and the upper limit because of this tight bound is 5 to me. Okay, all right, and let's say I set this number to be something like 3. Then I have this d2. Okay, I am assuming that d1 equal to 5 and let's say d2 equal to 1. Now let's say I had fixed the first position to be 3. Now for d2, even though d2 equals to 1, I can still write all the numbers from 0 to 9 here, because now there is no more tight bound left, since my first number was 3, whereas in k the first digit is 5. So the tight bound has already been avoided and now the problem is the same as the easier version of problem. All right, okay. However, if I had written a 5 here, then the tight bound stays. Okay, because since d1 is equals to 5 and my first digit is also equals to 5, so now this digit can either be 0 or 1, because otherwise I'll be exceeding the tight bound. Okay, so let's introduce another variable into our easier solution problem to take care of this tight bound. Okay, so let's say a DP state looked something like this: pos, comma, some small d, comma. Now I'm introducing a new variable here. Okay, so let's call this a boolean variable tight, and tight simply tells me if there exists a tight bound. Okay, so if there exists a tight bound, then I cannot go from 0 to 9. Okay, I have to go from 0 to some upper bound which is decided by dpos. Okay, so initially tight is 1. Okay, and let's say I am trying to fix the first position. Then since tight is 1, I cannot go from 0 to 9. Instead I'll be going from 0 to d1, right? From 0, 1, 2, 3 and at most 5. Okay, and for the next position, if I choose d1 to be anything less than basically this first position to be anything less than d1, then my tight becomes 0. From now onwards I could go from 0 to 9 freely. However, if I choose the first position also to be 5, then tight remains 1. And next time when I am thinking about the second position, I have to take care that d2 equal to 1, and since there is a tight bound, I could only set this particular position to be 0 or 1. So guys, let's write a recurrence for this also, and hopefully then it will be very much clear to you. Okay, so dp pos and small d, comma tight. Okay, so this thing simply becomes from x equals to 0 to some upper bound. We'll discuss what this upper bound is. From 0 to some upper bound, this thing becomes dp of pos plus 1, comma, capital D plus small d minus x mod d, whole mod d of course, comma, what about this tight thing? Okay, so if currently tight is 0, then even in the future there is no tight thing. Okay, if once tight has been removed, okay, like the first position, if I have set the digit to be 5 and I could have gone till 7, then I am generating all the numbers that start with a 5. They are obviously smaller than all the numbers which start with a 6. So if once this tight bound is gone, it is gone forever. Okay, this means for tight to be on, it has to be on currently, and the number that I am setting here should be equal to the upper bound. Okay, the largest number here. So x equals to upper bound. So if currently we had a tight position, if let's say my k equals to 5 1 3 2, and I had set the numbers till 5 1 and 3 5 and 1, this is the number that I am trying to generate. And if I write a 3 here, currently because I am setting 5 and 1 for the first two positions, then my tight was 1. Now if I set a 3 here, my tight stays 1. However, if I set a smaller value here other than 3, then my tight disappears. Okay, so tight should currently be present, and the number that we are setting here should be equal to the upper bound or the dpos. Okay, so guys, hopefully the recurrence is now clear to you. If you have any doubts, I am almost sure that they'll be cleared out through the implementation, so keep following to it. So guys, now we'll be implementing the same idea. Okay, so here I've just simply taken the input. K has been taken and into the input as a string, and then capital D is the number. The modulo D should be 0 overall, and here is our solve function. It takes the string K, it also takes this integer capital D, and then we have the pos, the current position which we are setting. So initially it will be 0, and then we have small d, the modulo which we require. Basically, after setting all the digits, the sum modulo capital D should be equal to small d. Okay, and this bool tight simply represents that whether we are in a tight bound situation or not. Okay, so let's see how this works. Initially I make a call to solve with the number and the capital D, and I want the answer from, after setting, initially I have not set any digits, so set all the digits starting from the 0th position up to the n-1th position, such that after setting the sum modulo capital D should be equal to 0, and initially I have to take care of the tight situations. Okay, I should not be generating any number greater than small k. Alright, let's see how this thing works. So first of all, let's write a base case. So if I have set all the positions, then pos equals to k dot length. This means that all the positions have now been set, and I'll return a 0. Alright, or maybe let's think of some other base case. If pos equals to k dot length minus 1, if I am at the last position, then what? Okay, so I'll write something for this. We'll write this later on. This is simply a base case. Given that I'm setting the last position, then what happens? Okay, for any other position POS, what happens is I have an upper bound, integer upper bound equals to, so if we are in a tight condition, if tight is 1, then the upper bound is equals to whatever is the digit at the POS position. So kpos, k at kpos, and since this is a string, I'm converting it into an integer. Okay, if there is a tight condition, then the digit at kpos, otherwise 9. Okay, since there is no tight condition, then I can go up till 9. Okay, now I'll be implementing the same recurrence which we discussed. So let's say ll answer equals to 0, and for some integer x goes from 0, x less than equal to upper bound, and x plus plus. So answer equal to answer plus. Now what? Now I'll be calling for the remaining sub problem. Since I've set x at the position POS, I'll be calling for dp POS plus 1, and wait a second, I also need to pass k capital D Now I'll be sending POS plus 1, set all the positions starting with POS plus 1 up till the n minus 1th position. And then what is the modulo that I require? That after setting all these, I require it to be capital D plus small d minus, I'm setting here x, then minus x mod capital D, and this thing whole mod d. This is from the equation that we made. Okay. And finally, how is tight decided? First of all, if tight has to be 1, then tight should be 1 even now. So tight, and if even if tight was 1, at this position I must be setting x equal to the upper bound. Okay, otherwise the tight gets removed. So it should be tight till now, and even after setting this position, our number should be exactly equal to the number k up till this position, right? Then after this I will be modding this with mod that is 10 to the power 9 plus 7, and once we're done with this loop I can simply return the answer. Okay, so let's discuss what about this pos. Again, I could set any number here. Let's start with an upper bound, and upper bound has to be the same thing. So let's just declare upper bound. I'll declare upper bound here. Okay, then I can set the last position with any number starting with 0 and up till upper bound, that is the same thing as this. So after setting this, let's have an LL answer here as well. Okay, so let's say set x at this particular position. Now if this after x mod capital D equal to small d, then answer plus plus, simple as that. So if x mod capital D equals to small d, then answer plus plus, and once this is done, return the answer. Alright, so this seems alright to me. And if this was not the base case, then do this. And I am also using this dp array. So what I could do is dp at tight, and here it was capital small d and pos. Okay, so if this particular state was already evaluated, then I should also return it. So if this is not equal to a -1 maybe, then return this thing. This means I've already solved this subproblem before, and here I'll use memset dp -1 size of dp. Alright, so I think this should work. Let's try a sample input. Maybe let's try sample input 3. So there's some problem here. Line 21, ub equal to tight. Oh, sorry. Okay. This is line 32. All right. Tight and x equal to ub. Error dp cannot be used as a function. Oh, I'm sorry about that. I have to say solve. We should be getting this output. It's taking a little bit time. All right, so yeah, the output is correct. Is this no, this is some problem. Okay, yeah. My answer is 1 plus the our sample output, right? This is because we are also counting 0. And here is one thing I'd like to mention. So I am generating this particular number 000 with n digits, right? However, after generating this number, the sum of the digits will also be 0, and 0 mod any capital D is equals to 0, and therefore I am always counting this number. So the easiest way to solve this thing is to do a -1, and that's it. So whatever I find out, I should be doing a -1 from it. So whatever you find out, do a -1 from it. However, I should not simply do a -1. Instead, I should do D plus mod plus solve -1 whole mod. Okay. So this is basically subtraction, and whenever you want to subtract something in modular arithmetic, you should also add mod, then subtract anything, and overall mod. Now I'm getting the correct answer. See, because overall this equation is simply mod, then that this term will become 0, right? So this is not making any effect on the overall result. Cool. So I can now try and submit this thing. Till then we'll just discuss the time and space complexities. So guys, as you can see here, the table size is 10,000 into 100 into 2. So overall the space complexity will simply be log of k to the base 10 into capital D into 2, which is avoided in the big O notation. So this is the space complexity. All right. And for the time complexity, the transition time here is 10, basically the number of digits we have. As you can see here, we are using this for loop, and this ub can be up to 9. So this is 10 times d. The time complexity will be 10 into d into log k. However, 10 is just a constant here, however, but our digits could have been more. Okay, so you have to mention that in the time complexity as well, the number of digits into the capital D into log k. Okay, so we are getting an AC. So I hope guys this was a helpful this video was helpful to you, and you can try a few digit DP problems on your own as well. Okay, so all the best and thanks for watching. Hi everyone, in this video we'll be solving the problem T permutation. So you can go through the problem once and then I'll be explaining it to you. Okay, so we are given with the positive integer n, and the gist of the problem is that initially we have the set of numbers 1 to n, and we have a string which consists of operators less than and greater than. Okay, so the gist of the problem is that you have n empty places and you have n minus 1 operators, and each operator could either be less than or greater than. So let's take an example, something like this. Okay, and you would like to fill these empty places with the numbers you have from your set. Okay, and each number can be used only once. So you would like to find out the number of ways in which this thing can be filled such that these operators are valid. So basic idea is that if I fill a 1 here, this can be a 2, 3, 4 because 1 is less than 2. Similarly, if I fill a 3 here, then 3 is less than 4 or 5. Okay, so for this thing to be valid, if there is a 3 in the first empty place, then there has to be a number greater than 3 in the second empty place, and at the end we would like to find out the total number of ways in which these dashes can be filled in a valid way. So if the problem statement is not clear, it will be clear once we discuss the sample input. Okay, and right after we discuss the sample input, I will describe n factorial solution, and then we'll move on to better solutions. Okay, so the first sample input is that you have 4 dashes and you have the string less than, greater than, less than. Okay, So basically you have the numbers 1, 2, 3 and 4, and you would like to find out the number of ways in which you could fill these dashes so that the operators are valid. Okay, so you can fill it like 1, 3, 2 and 4, and this is valid because 1 is less than 3, 3 is greater than 2 and 2 is less than 4, so this is a valid way. And then again 1, 4, 2 and 3 is also valid. You can verify why. 1 is less than 4, 4 is greater than 2, 2 is less than 3, so this is another valid way. And overall you can see that there are 5 such valid ways. I'll describe by one invalid way. Okay, so this is an invalid way because 4 is not less than 1. Okay, alright, so hopefully the problem statement is clear to you. You just need to find out the number of valid ways in which you could fill the dashes. So the first thing that comes to the mind is that there are a total of n factorial permutations of the 1, 2, 3, 4 up to n set, and you could try each and every permutation and check if the after filling the dashes if it is valid or not. If it is valid, then add 1 to your answer, otherwise do not add it. So it will be a big go of n factorial algorithm. Okay, but of course n is up to 3000, so this will not work and we need to think of something better. So you can go through the sample input 2 and 3 as well. So here in sample input 2 you have 5 dashes and all the operators are less than. So you are constrained to only one sequence of, or basically only one permutation of the numbers, that is 1 is less than 2, 2 less than 3, 3 less than 4 and 4 less than 5. There is nothing other than this which is valid. Sample input 3 is quite a larger input and we will not go through it. Okay, so guys, hopefully the problem statement is clear to you, and now I'll be moving towards the solution. So we are solving, just a second. Yeah, T permutations. Okay, so in this problem, before we really reach a nice solution, we need to make a few observations. Okay, and in order to reach the intuition for them, let's try to write a backtracking solution first of all. So initially you have the set 1, 2 up to n. Okay, and you have n empty places and you have some n minus 1 operators between those places. Any operator could be either less than or greater than, right? Now initial dash I could fill any number from 1 to n, right? Because currently there is no constraint, so I could go ahead and put any number in this position. Once I've done that, I could put any number in this position and then I could recur for the remaining set and the remaining places, right? So imagine from this set of numbers I use the number x to fill this position. Then I'm left with the set 1, 2, 3 up to x minus 1 and then x plus 1 to n, right? This is the set that I am left with after putting an x at the first position. Now I have this operator, and to fill this dash, now I cannot just use any of these numbers to fill this particular dash, isn't it? I will have to think what this operator is. So if this operator were maybe a less than, then x is less than the next dash. So the valid things that could come here are anything from 1 to x minus 1. Okay, no, sorry, anything from x plus 1 to n, because otherwise my string becomes invalid right here itself, because x would not be less than some number from this portion. Okay, so this way I could think of writing a backtracking solution, and what I need to remember is what are the current elements I have and what was the number that I wrote one position behind, right? So if I were thinking about the ith position, I need to know what is the set of elements I currently have and what was the number I wrote in the I minus 1th position. Knowing these two things could allow me to fill the ith position, right? and I could come up with a backtracking solution which is still big O of n factorial. However, backtracking makes it much faster than the worst case. Now we need to think what is the lesson from this backtrack solution. So lesson number one from this thing is that, and when I am trying to fill the ith position, I need to know what number was at the I minus 1th position. So I minus 1th position number needs to be known. Either it should be known or there must be some idea of what are the valid things for the ith position, right? So either I should be knowing the I minus 1th person, or there must be some relation so that I know which all people are valid at the ith position, isn't it? One more thing to observe here is that the set of numbers that I have, imagine I have the some numbers, maybe x1, x2 and some xk. Let's say I am currently having k number of elements, and in the sorted set they are x1, x2 and xk. So the observation here to make is that what matters is the number of elements I have and not really what elements I have. The only thing I would like to know is how many of these elements are less than the number that I put just behind the ith position. So number of elements which are less than the number at the I minus 1th position, and the numbers which are greater than it. It does not really matter what are the magnitude of these numbers, isn't it? Because if initially my set was 1, 2 and up to n and I had to fill the dashes, it would not have made any difference if my numbers would have been x1, x2 up to xn, and of course x1 is less than x2, x2 less than x3 and xn is the greatest. So it would not make any difference what are the magnitudes of the numbers. It just, the only thing is that I would like to know the total numbers I currently have in my set, and how many of them are greater than the previous number and how many of them are less than the previous number, isn't it? So if I knew what number I have filled at the I minus 1th position, I would know that okay, x1, x2 and let's go with here. Okay, so x1, x2 and let's say up to some xs. These are the numbers which are smaller than the number I filled at the I minus 1th position, whereas the elements xs plus 1, xs plus 2 up to xk are the numbers which are greater than the number I filled at the I minus 1th position. Alright, so if I knew this, maybe I could come up with a better DP solution, isn't it? Having this much knowledge. Because by knowing this, let's say I had filled some number at the I minus 1th position, and let's say that the operator between the I minus 1th position and the ith position is less than, then I know that at the ith position I could use any of these numbers starting from s plus xs plus 1 to x of k, because all these will be greater than the previous guy. And if this operator was greater than, that means the I minus 1th person should be greater than the ith person, then I could use any of these s numbers, isn't it? So having this much knowledge allows me to hopefully break the solution to smaller subproblems. Let's see how. So first of all, one important observation here is, what matters is some important observations here. The total numbers that I have, total numbers remaining, out of these how many numbers are less than the number I placed at the I minus 1th position. So let's define S, the numbers, the count of numbers among these total t numbers. S is the amount of numbers which are less than, count of numbers less than the number I placed at the I minus 1th position and similarly G, the count of the numbers which are greater than the number I placed at the I minus 1th position. Okay, so knowing these can help me find a better solution. Also, the major observation was that if you have the set of numbers 1 2 3 4, or you have the set of numbers maybe 1 2 4 5, these two things are exactly the same. If initially I had the numbers 1 2 3 4, or I initially had the number of numbers 1 2 3 4 5 in my set, these two things are entirely the same. The number of ways to use this set or to use this set would be the same. Okay, because the actual magnitudes do not matter. What really matters is the relative magnitudes, and knowing that this number is smaller than the next number, that is what really matters. Okay, with these observations, let's try to come up with a solution. Okay, so now imagine that I'm trying to fill the positions starting from I plus 1 up to n, right? I'm trying to fill these positions. So, or maybe let's take from I to n, right? So I'm trying to fill the positions starting from I up to n, and currently I have a total of t integers in my set. Okay, I currently have t integers in my set, and I'm saying that s of these integers are less than the integer I placed at the I minus 1th position. So s ints, this is the total, and s integers are less than the integer I placed at the I minus 1th position. And I'm saying that g integers are greater than the number I placed at the I minus 1th position. Okay, so I know these. So now I'll define a term dp of I, t, s and g. Okay, this is the number of ways to fill all the basically the number of valid ways to fill the positions from the ith up till the nth, given that I have a total t number of integers, and among these s of the integers are less than the number I placed at the I minus 1th position, and g of these integers are greater than the number I placed at the I minus 1th position. All right, so I have dp of itsg. So before I really write the definition, again there are a few more observations to make. Since I am about to fill the numbers starting from I to n, t does not really need to be included, because t is obviously n minus I plus 1. The number of dashes I have to fill, that is the total number of integers I still have in the set, right? Basically I have filled I integers. From the n integers I initially had, I used I minus 1 of those, so of course I have n minus I plus 1 integers still with me, right? That's it. Since I've used I minus 1 integers from the initial n integers, so t is nothing but t equals to n minus I, sorry, yeah, I've used I minus 1 integers because I'm about to fill the ith place. So first I minus 1 places are filled, and this becomes t equals to n minus I plus 1. So t is entirely defined using I, so I do not need to keep t in my dp state, since t is entirely defined by the I, as n is a constant. Alright, so t can easily be eliminated. So I am left with dp of I, s and g. Again, s and g are nothing but s plus g will become t, right? So knowing only one of these gives me the other as well, because t is entirely defined by I and s plus g is a constant. So if I knew any of these things, I could easily determine what the other is. So I need to keep only one of these in my unique dp state, isn't it? It is not necessary to have both of these variables in my dp state, as s plus g is a constant. So I am left with the dp state I comma g, and s I can easily determine using t minus g, and t can be easily determined using n minus I plus 1. Alright, so now I am left with the state dp ig. Now I will be defining what dp of ig is. Okay, so I define this thing as the number of valid ways to fill all the positions starting from I up till n, the last position, such that I have g numbers which are greater than the number I filled at the I minus 1th position. So number of ways to fill positions from I to n such that I have g numbers greater than the number at the I minus 1th place. Alright, so this is what my dp of ig is, and let's see how this will help me find the actual answer. So imagine I filled a 1 at the first position, then the number of ways to form actual valid, so the valid ways to have a 1 in the first position is nothing but dp of 2 comma, since I filled a 1 at the first position, all the numbers are greater than 1 which I'm left with, that is 2 up to n, and this is nothing but n minus 1 numbers are greater. So if I fill a 1 at the first position, then the ways to fill the entire n places is nothing but dp of 2 comma n minus 1, right? Okay, if I fill a 2 at the first position, then the number of valid ways to form basically number of ways to form a valid permutation, or the number of valid ways to fill my entire places so that the first number filled is 2 in the sequence, then my answer will be dp of 2 comma n minus 2, because now there are n minus 2 numbers which are greater than the number I have filled at the first position. And similarly, I could fill the third number at the first position and up to so until I could fill the largest number at the first position. So if I fill the number n at the first position, then I'll get the valid ways as dp of 2 comma 0, because there is no number greater than n. So my final answer is nothing but summation dp of 2 comma I, and I goes from 0 up to n minus 1, and that will be my final answer. Okay, so now we need to think how we can really find dp of ig, or maybe basically build a recurrence for it. So I'll urge you guys to try it first and then you can watch the solution. Okay, so we would like to find out what dp of I comma g is. Now at the ith position, I know what the previous operator was. There was some I minus 1th position, then there was some operator, and then the ith position. And I know that among the numbers that I still have, which is t numbers, and t is nothing but n minus I plus 1, I know that among the people that I have, g of the numbers are greater than the number I filled here, and the other people are smaller than the number I filled here. Okay, So let's try to build the recurrence assuming that the operator is less than, or maybe the operator is greater than, whatever you want to assume first. So let's assume that the operator is greater than, then we have I minus 1 greater than the I. Okay, so now here I would like to fill the numbers which are less than the I minus 1th position, isn't it? So I have a total now of n minus I plus 1 people, and among them G were greater than this guy. I am thinking about the people who are less than, so they are nothing but n minus I plus 1 minus G. So these are the numbers less than. Let's write it here. S equals to n minus I plus 1 minus G. These are the number of integers which are less than the previous guy. So I could use any of these integers to fill this position, isn't it? So these are S numbers. This looks something like this: x1, x2 up to xs. All these numbers, x1 is less than x2, x2 is less than x3, and xs is the greatest among these. But all of these are less than the number I filled at the I minus 1th position. And I have the set of numbers from xs plus 1 up to xg, or basically x1, x2, x3 and up to xg, and these are the g integers which are greater than the number I filled at the I minus 1th position. So currently at the ith position, since this operator is greater than, or basically I minus 1 greater than I, so I could use any of this numbers from the first set, that is I could use either x1, x2 up to xs. So let's say I use x1. If I use x1, then the number of valid ways for doing that is dp of I plus 1 comma the number of integers that I'm left with which are greater than x1. So all these numbers starting from x2 to xs union all these from this set x1 to xg. This is nothing but g of these numbers and s minus 1 of these numbers, right? So this is g plus s minus 1. Okay, if I fill x1 at the first position. However, if I fill x2 at the first position, then the number of ways of doing that is dp of I plus 1 comma g plus s minus 2, because all these g numbers are still greater than x2. However, only s minus 2 numbers from this set are greater than s2, and I could go on doing that for all these numbers from this particular set. And if I use xs to fill this ith position, then I'm left with, then the number of ways of doing that is dp of I plus 1 comma g, because now only these people are greater than this guy. So now I have a recurrence given that the operator is this, and I'll be writing the recurrence in a succinct manner now. So this is nothing but summation dp of I plus 1 comma g plus s minus 1 up to, starting with g plus some integer j, and j goes from 0 here up to s minus 1. J goes from 0 to s minus 1, and this is my dp of ig. Okay, however, this is the recurrence only for the case when the just left operator was greater than. Now what if the just immediate left operator was less than? Okay, so we need a recurrence for that case as well, and we'll be writing it. So just a second, we'll be doing that here only. You can try that as well, but it really follows a very similar pattern, and it's easy to write. If operator equals to, okay, and the other cases when dp of ig equals to, there's the immediate left operator is greater than or less than. So in this case, the number at the I minus 1th position should be less than the number I place here. So this means I could use any of the numbers from the greater than set. Yes, I could not use any of these x1, x2, xs, the elements which are smaller than the I minus 1 position, because this position has to be greater than the previous one. So I could use any of the people that are from the larger set. So any of these xg people. Now assume I use the x1 of this set. Okay. So if I do that, the number of valid ways is dp of I plus 1, comma, I fill x1, so I am left with the numbers greater than x1 are x2 up to xg, so g minus 1. If I would have used x2, then the ways would have been dp of I plus 1, comma, g minus 2, right? And if I would have used the largest of these people, that is xg, then I would be left with no person greater than xg. So the valid ways are dp of I plus 1, comma, 0. There is no guy greater than xg. And I could again write this in a more succinct manner. This is nothing but dp of I plus 1, comma, g minus j, and j goes from 1, just a second, this is 0, okay, j goes from 1 to g, right? So here is the recurrence, dp of I plus 1, comma, g minus j, and j goes from 1 up to g. All right, so guys, we have the recurrences, and now we can easily evaluate our answer as described previously. However, we need to see what the time complexity for this is. So the time complexity for this will be the number of states into the average transition time per state. So here you can clearly see that the transition time, the number of states is simply n squared. All right, it can be up to n square, right? The number of states. And just a second, yeah, and the average transition time is definitely not O1, and in fact it is big O of n, the average transition time, and this gives us a big O of n cube solution, which is not the required or the optimal solution. Reason being that n is up to 3000 and this will time out. We are looking for a big O of n square solution. So here is a place that where we'll be using an optimization, and you can think what kind of optimization might help us. So if you would remember that we solved a problem m candies, and from that there was an optimization which we applied to reduce our solution from n cube to n square. You can think in that direction, and that may help to basically faster up the solution, optimize this recurrence. However, yeah, if you would like to try it on your own, you can pause the video, otherwise I'll help you out with it. So let's think about this recurrence first. So it's dp of ig. Think about dp of I comma g plus 1. What will dp of I comma g plus 1 be? It will also be a similar summation. It will be dp of I plus 1 comma g plus 1 minus j, and j goes from 1 to g plus 1, isn't it? So this is this recurrence breaks down to the following thing, that is dp of I plus 1 comma g plus 1 and j equal to 1 initially, so this becomes nothing but g plus dp of I plus 1 comma g minus 1, and so on till dp of I plus 1 comma 0. And if you are careful about this thing, if you carefully inspect this, dp of ig and dp of I comma g plus 1 have only this particular term which is not common. Okay, this is the only extra term included in dp of I comma g plus 1. So I could really use the result of dp of I comma g to calculate my answer, isn't it? And my answer for dp of I comma g becomes I comma g becomes dp of I comma g minus 1, or just a second, we'll write as discussed, I comma g plus 1 is nothing but the answer for dp of I comma g plus dp of I plus 1 comma g plus 1, sorry, g, right? Because the first term for dp of I comma g plus 1 according to this summation is g plus 1 minus 1, that is dp of I plus 1 comma g, and this was the only term extra that wasn't included in dp of ig, rest all terms were same. So now using this kind of recurrence, our transition time becomes big O of n, because this state now only depends upon two states. Sorry, transition time becomes O of 1, because now this state depends upon only two states. Now we need to think of a similar way to optimize this equation as well. So in a similar manner, let's think about dp of I comma g plus 1 here as well. So it will be nothing but dp of I plus 1 comma g plus 1 and dp of I plus 1 plus dp of I plus 1 comma g plus 2 and so on till dp of I plus 1 comma g plus basically g plus 1 plus s minus 1, right? So g plus 1 plus s minus 1, that is nothing but g plus s, and g plus s is nothing but the total number of elements. So if you're careful to inspect this as well, you will find out that dp of ig and dp of I comma g plus 1 are almost the same, except that in dp of ig even dp of I plus 1 comma g is being included, whereas in dp of I comma g plus 1 dp of I plus 1 comma g is not being included, right? So I could use the result of dp of ig would say that dp of I comma g minus the only extra term in dp of ig was dp of I plus 1 comma g plus j, and that was g, right? This was the only extra term in dp of I comma g. So this way now I have the optimized recurrences, and these recurrences depend upon only two other states. Therefore my solution, the transition time has reduced to big O of 1, and my overall solution becomes n squared in running time. All right, so this solution will definitely pass the time limit, and we can go forward to implement it. I'm just writing the recurrences once again, and then we'll move forward to the implementation. But first we should also discuss some base cases. So we have these two recurrences depending upon the immediate left operator, and we need to discuss a few base cases and then we can directly implement this thing. Okay, so we'll be writing a base case as dp of I comma 0. Okay, this will be a base case. We'll be seeing how we evaluate it, and of course, yeah, I forgot to mention this is the recurrence when the operator, the immediate left operator to the dash is this guy, and this is the recurrence when the operator is this guy. Okay, so now let's think about dp of I comma 0. It's simply if my operator was minus 1 position, then a less than, then ith position, so I had to fill some person which is greater than the person I just filled at the I minus 1th position, right? However, that's not possible for me to do because I do not have any person greater, and if then in that case dp of I comma 0 is nothing but 0 if OPR, and in the other case it will be Then I will have all the people, the total remaining people will be equal to s, and I could use the smallest of them. And the ways for doing that will be dp of I plus 1 comma s minus 1. And among this, j goes from 1. I use the smallest person, then the number of greater people at the next position will be s minus 1. If I use the second smallest, and so on up till if I use the largest, then again g will be 0, so up to s. And this will be the equation for dp of I comma 0, the base case. Okay, now you will say that this guy, the transition time is not big of 1. However, there will be only n states in which the transition time is greater than big of 1, isn't it? And even if for n states I use big O of n time, that will still be only big O of n squared, because for all the remaining n squared minus n states, my transition time will simply be big O of 1. So my overall time complexity is going to be big O of n square. Alright, now we'll move forward towards the implementation, and we'll simply be implementing these recurrences in a bottom-up manner. Yeah, and we'll have this base case and we'll simply implement these. Okay guys, so now we'll be implementing it, and I'll be removing this. So for my convenience, I have simply written down these recurrences here. These are just the same recurrences that we have discussed. For my convenience, I have written them here. And one new thing here is that dp of n comma 0 will be 1 if the operator is greater than. This is because when I'm filling the nth position, there is no n plus 1, right? There's no dp of n plus 1. So when I'm filling the nth position and I have 0 people which are greater than the person I filled on the n minus 1th position, so I'm left with one integer, and that is less than the person I filled previously. So the operator must be greater than, only then will it be valid, and I'll have one new case. Otherwise I'll be having 0. So that is simply dp of n comma 0. Okay, now we'll be implementing these equations. That's it. Okay, so here I've taken the input n, the number of dashes, and s, the operator string. After calling solve, my dp array will be ready, and then I'll simply take the values at dp of 2 comma gr for all gr starting from n minus 1 up to 0. If I fill the smallest number, then I'm left with n minus 1 as my gr, and similarly for taking the second smallest number, third smallest number, and the largest number if I take, then I'm left with 0 numbers that are greater than it. So that is simply what we're doing, answer equal to the sum of all this. And now we'll be writing this function solve to evaluate our dp array. So first of all, dp at n comma 0. Okay, so dp of n comma 0 is going to be if the operator at n, basically n minus 1, because the length of the string itself is n minus 1, so I have to look at n minus 2 instead. Yeah, and if the last operator is equals to this guy, then I have a way in this case 1, otherwise 0. And now for int I goes from n minus 1, n I greater than equal to, I have to calculate till 2, right? Yep, I greater than equal to 2 minus minus. Okay, then currently g starts from 0 and g up to g less than equal to the total number of people I have. So integer total equals to n minus I plus 1. G less than equal to total and g plus plus. So first of all, if I'm still basically if I check n comma 0 again, I should skip it. So if I equals to n and g equals to 0, then skip this state. This has already been evaluated. Okay, and otherwise what do I do? Otherwise there are two possibilities. Either this is a base case I comma 0, or it's simply a dp of I comma g state, right? So if g is equals to 0, then what do I do? And I could put this thing inside it. Then I just have to check if I is n, then the state was previously calculated, so just ignore and move on. So if g is 0, then I'll do something else. If this is not a base case, then I'll do something. So if this is not a base case, then that thing is very easy. So if s at I minus 2, I guess, equals to, because for n we were using n minus 2, and for n minus 1 we will be using n minus 3, and that is how it will work. This is only due to the difference in the indexing. The string is 0 based index, and the dp array we are using is 1 based in the first dimension. That is why this problem is there. So for if s at I minus 2 equals to this, then something else something. Okay, so let's write our first recurrence here. So if it is the greater than sign, then I'll just check the recurrence. If it's this, then my recurrence is this thing. We'll be copying it. All right. Also, since it's g, so ig becomes, and this becomes g minus 1. I comma g plus 1 became ig, and this guy became from ig to ig minus 1, and this will also become ig minus 1, right? Same way in the other case we will also have a recurrence, and it's almost the same except that it's plus dp of I plus 1 comma g minus 1. Cool. So this case is done now, and we just have to write the base case. So if g is equals to 0, our recurrence was something like this, and that is precisely what we are going to write in code. dp of I comma 0. So for integer I goes from, basically j goes from 1 to s, and s is basically the total number of integers I still have, right? So j goes from 0 to total j plus plus, j goes from 1 to s minus j. Okay, j goes from 1 to s is total only because g is 0, so s equals to total. Since s plus g was a constant equal to total, so if g is 0, then obviously s equals to total, and dp of ig becomes equal to dp of ig plus dp of I plus 1 comma s minus j, and that's it, modulo mod. And I need to do this modulo mod everywhere. So yeah, with this I think our implementation is complete and we can try a sample test case with now. Alright, so I'll be trying this one. DP of IG 31. Okay, I haven't defined S here. S is nothing but total, so it becomes total minus J. Moreover, if the operator is, if OPR equals to, OPR is nothing but S at I minus 2 equals to the less than sign, then DP of simply continue. Okay, so we are getting an incorrect output. I'll just check why. Okay, so I'm guessing it has to do something with this thing, DP of n comma something, and at the nth position my total is equals to 1, right? Then if G was 0, then that is right, that has been calculated here. But what if G is equals to 1? Total can be up to 1. In that case else will run and there is no DP of n plus 1, right? So it will be better if I define DP of n comma 1 itself here itself as a base case. So DP of n comma 1 meaning that I have one guy which is greater than the number I just previously placed. So if the immediate left operator is less than, then I could use this guy to get 1 to my answer. Otherwise, if this guy is greater than the previous guy and I need a smaller guy, then it should be 0. So I guess now I can run this loop from -1. Okay. Alright. So it was a mistake with this base case here. It should be defined here itself. Alright, now we're getting the correct answer. I'll just check a larger test case. 217136. Alright, we're getting the correct answer. I'll submit and we'll check. I think it will pass. Okay, so we got a WA. I'll check why. Alright, so let's just check it out. Okay, so I guess the recurrences are correct. What I'm guessing is that due to this subtraction there is a possibility that this thing becomes negative at a point, right? So during subtraction I should add modulo before subtracting and that should do the work. When it gets negative, because of that it will give me a WA. However, if I add a mod here and even if it stays positive, I do not have any problem because modulo does not really affect my overall answer. So I guess now it should work. I'll just submit again. We'll see. Yeah, I think it worked. Guys, hopefully the video was helpful to you and thanks for watching. We have already discussed the space and time complexities here and the base cases were these guys. At the nth position you could have either 0 people which are greater than the previously placed person or at most 1 person. So these are the only two valid states for DPN. Either it is n comma 0 or it is n comma 1. No, nothing else other than that is valid. And now you don't even need this because we started our I from n minus 1 only. And yeah, that's it. So the time complexity for this was big of n squared. As you can see, the execution time also is 59 milliseconds only for n equal to 3000. So it's n squared in space and time. Okay guys, thanks for watching. I'll see you in the next video. Hi guys, my name is Karthik Arora, and in this video we'll be solving the problem U, that is grouping. So guys, you can go through the problem statement once, and then I'll be explaining it in simple terms. So we are given with n rabbits, okay, or n people, whatever you would like to imagine. So we have given n rabbits and we would like to group them into some number of groups. So let's just say we are forming a number of groups, so maybe x groups, and x could be one group, it could be two group, or it could even be n groups, right? So what we need to do is we would like to group these n rabbits into some number of groups, and each group will have a few number of rabbits, at least one of course. And in the end, if the ith rabbit and the jth rabbit are in the same group, then a score of aij is earned, okay, and we would like to maximize our overall score. So let's say if some rabbit I, j and k were in the same group, then our score will be aij plus aik plus ajk, okay. So similarly, there will be some rabbits in this group, and then we'll take the pairwise scores of those rabbits, and same way for every group. Overall, we'll see what the overall sum overall groups is, and that will be our overall score. And we would like to group these rabbits in such a way so that our score is maximized, okay. So we'll go through a problem statement now. Yeah, so you can look at sample input 1. Here we have 3 rabbits, and you can see this matrix. This means rabbit 1 when paired with himself gets a score 0. Rabbit 1 when paired with second rabbit, you get a score of 10. Rabbit 1 paired with third rabbit gives you a score of 20, and so on for rabbit 2 and 3 as well. So in this, according to AtCoder, the maximum possible score is if you take the 3 rabbits and you group them as follows. You group 1 and 3 in the same group and rabbit 2 alone. Then you earn an overall score of A11. In fact, since AII is going to be 0 as per the constraints, so I will simply take A13 for this group. And since there is just one guy, so the score is 0. And overall score is A13, which is equals to, sorry. Yeah, A13, which is 20, right? So the output is 20. Let's look at one another case, and then we'll move towards thinking of a solution. Example input 2 is since putting them in the same group meant getting a minus 10 score, so you make 2 groups and keep them individually and you get an overall score of 0. Alright, then this is a larger input. So guys, hopefully the problem statement is quite clear to you. Here you can see that we need to use longs. Also, let's just look at the constraints once again. So n is quite small, n is up to 16. The values could be anywhere from minus 10 to the power 9 up to 10 to the power 9, and AII is 0. So the same rabbit score, putting him in a group, you don't have to basically add AII, it is 0. And AIJ and JI is equal, of course, because there are 2 rabbits AI and ith and kth in the same group. Then you need to add a score of AIK or AKI, which is the same thing. Alright, so guys, hopefully the problem statement and constraints are quite clear to you. Here important thing to see is that n is quite small. So let's see what solution we can come up with. Okay, so guys, this is a very nice problem to understand the working of bit masks and how bit masks can be used in dynamic programming. Moreover, you will get to learn about a new more masking operations as well. Okay, so solving U grouping. Okay, so we are given with n rabbits and we have to group them up into some number of groups. N rabbits make k groups maybe, and each rabbit must be in one of these k groups, and overall we have to maximize the scores that is the score that is achieved after the groups are formed. Okay, and you have assigned each rabbit to one of the groups. So this k can be anywhere from 1 to n, and if there is just one group, then all n rabbits are in the same group, and if there are n groups, then all rabbits are in different groups, right? So something like this. If n was 3, you have these 3 groups. Okay, and so let's just try a sample input kind of thing, and we see how it works. So I'll simply take the sample input one and we'll see how things work out. So in the first sample we had 3 rabbits. Okay, and then let's say we are about to make our first group. Okay, so we are about to make the first group. The first group could consist of only the first rabbit, so only rabbit number 1, or the first group could consist of only rabbit number 2, only rabbit number 3, or the first group could consist of rabbit number 1 and 2. It could also consist of only rabbit number 1 and 3, 2 and 3, and simply 1, 2 and 3. Okay, so we were making the first group using all the 3 available rabbits, and we see the possible options that we have to make the first group. Right, now in this case we are still left with 2 rabbits, and we would like to evaluate what is the maximum possible score that we can achieve by combining 2, 3. Okay, since we have made the first group, the score of this group is 0, as there is just one single rabbit here, and now we have to find the maximum possible score for 2, 3, rabbit number 2 and rabbit number 3. Okay, so again I could either make the group 2, or I could make the group 3, or I could make the group 2, 3. Okay, and for this the score is 0, and I am still left with one rabbit, and I'll be making one more group here, and that will be the only group number 3. There is no other possibility. For this also the score is 0, this also the score is 0. So if we make 3 groups, that is 1, 2 and 3, then our overall score remains 0. Okay, sorry, I would rather represent this as 1, 2 and 3. Okay, so in this case the overall score is 0. Okay, so if I would have made the first group to be 2, then I could make the next group in just a second. So we have to evaluate these possibilities as well. So if I made the first group to be 1, then the second group to be 3, then only one possibility is left, and in this case also the score is 0. Here I made the group 2, 3, and no more rabbit is left. The score for this group is A23, and we can see in the problem statement that A23 is minus 100. Okay, so in this way I will receive a score of minus 100, and of course I will choose the better of the 3 possibilities, 0, 0 and minus 100. So yeah, if I make the first group to be 1, my score will be the max of these 3, which is simply 0. Okay, so let's move forward to the remaining possibilities as well. This possibility is easy to evaluate since the first group consists of all the rabbits. So my score is simply I don't really need to group any more rabbits, and my work is already complete, and my score is A12 plus A23. Okay, and in this case I can further go on, and the next group could be either 1 or 2, or it could be 1 and 2 together. So 1 alone, 2 alone, 1 2 together. Here I would make 2, I would make 3 for these. For the single individual three groups, this overall score is going to be 0, whereas in this case my score will be 0 plus the score at A12. And again we will just check what is A12. A12 is 10. Okay, so A12 is 10, and in this case my score is coming out to be 10. Similarly for 2 also we could have evaluated further on, and for 2 it would have been, the next group could be 1 alone, 3 alone, or 1 3 together. Of course, in these possibilities in which all the 3 rabbits are individual, my score is going to be 0, whereas in this possibility my score is going to be A13, and A13 turns out to be 20. Okay, and which was the correct output as well. So if I make the first group to be only 2, and then I make the group 1 comma 3, I'm getting the best possibility. Okay, so guys, you need to notice here that I'll be going to 2 and then making the group 1 comma 3, and I'll be calculating the answer for 1 comma 3. Again I'll be calling for the group 1 comma 3, and we would like to find the best answer for 1 comma 3. So if I would have stored this answer here itself, then of course I would have the answer here and I will not need to calculate it again. Okay, so you can see that there are overlapping sub problems here, and now we'll move towards the solution. Guys, as we discussed, firstly make the first group, then you will be remaining with some rabbits that are not included in the first group. So initially there were n rabbits. Okay, and you make the first group, then let's say the group is G. G could be any rabbits. Okay, G is basically any subset of n, and then you calculate the score which you get by making the group G, and then you find out what is the best possible answer for the rabbits that belong to the group n minus G, and you say find the best answer for n minus G. Okay, so now I'll be defining a term that is dp of S. Okay, here S is the set of the rabbits that I still have and I would like to group. Okay, and dp of S represents the maximum possible score that I can achieve by grouping these rabbits that are represented by the set S. So max possible score achievable by grouping in some way the rabbits represented by the set S. Okay, so now we have a dp definition, dp of S, and we also have a pseudo algorithm. We'll see how we can use this algorithm to find dp of S. So if it's okay guys, now I'll be erasing this. dp of S simply says maximum possible score achievable by grouping the rabbits represented by set S. Initially my set S is nothing but 1 2 3 up to n, because initially I have all the rabbits to group and I would like to find out dp of 1 2 3 up to n. Okay, alright, now let's see how we can write a recurrence to find dp of S. So guys, as we discussed, to find dp of S, firstly we have some rabbits that are represented by the set X. We'll be making our first group of rabbits. Okay, this first group of rabbits is nothing but the group G, and this group G is a subset of S. Okay, because I have some rabbits that currently in the set S, and I'll be taking some of these rabbits and forming the first group. So it is G. Okay, now since I've made the group G, I will get some score because I've grouped the rabbits together, and the score we'll see how we can calculate it. But let's say score of G, the score that you get by making the group G, plus what is the best possible way to group the remaining rabbits. The remaining rabbits are nothing but the set difference of S minus G. Okay, O for all possible G. Okay, so first of all, how many G are there? There are 2 to the power n possibilities of making the set G. Okay, like 2 to the power n minus 1, because we are not including the empty set phi. The first group could be any of the 2 to the power n minus 1, where n is the number of elements in S. Okay, now guys, we have a recurrence. Let's discuss of a base case, and then we'll see how we can implement this kind of recurrence. So what would be dp of phi? dp of phi is nothing but the maximum possible score that you can achieve by grouping 0 rabbits. Since I do not have any rabbits to group, so dp of phi is nothing but 0. Okay, so now I'll be raising this recurrence. We'll discuss how we can calculate score of G and how we are going to represent S. So first of all, let's discuss how we can represent S. So S is nothing but a set of at most 16 elements. I could use an integer, and the ith bit will represent whether the ith rabbit is present in the set or not. And initially I have this, these are n number of ones, because initially all the rabbits are present in the set. So I would like to find out dp of this guy, right? So this is nothing but bit masking again. All right, now how do we calculate score G, right? So G is also a set, and the score of G is simply, if the ith rabbit is present, we have to take all the pairs I comma j, given that the jth rabbit is also present. So let's say if my set is something like this, meaning that the first rabbit is present, or the 0th rabbit is present, and 1th rabbit is absent in the set G, and then again second rabbit is present, and finally third is absent and fourth is also present. So what we can do is, we'll have to add A04 plus A02 plus A24. Alright, so this is how you calculate score of G. Given that there are n bits in our set, to calculate score of G, it will take n square time, because for the 0th bit, see which all bits are on, and add A0j to the total, where j is a bit which is on and j lies to the left of 0. Okay, again for another bit A2 which is on, find any bit j to the left which is on and add A2j, that is to the total. So we add A24. So this is an n square algorithm, and n can be up to 16 in this case, to find score G, of course. Now we are still wanting to find out how dp of S. Okay, so we saw that dp of S equal to score, or let's just say sum G, plus dp of S minus G over all the subsets. And S, we saw that number of rabbits could be up to 16, so this integer S has to be up to 2 to the power n, right? So 2 to the power 16. So memory wise, it seems feasible to have this kind of table. We'll also evaluate the time complexity in a while. So let's say I pre-process all sum G. I make all the sum G, basically for every possible subset I calculate sum G beforehand, right? We'll see how we can do that. and then I'll be simply making the calls, recursive calls, and calculating dp of s, which is the maximum over all these g possibilities. So for all g, and then you select the max out of all these possibilities. Alright, but now the point is, how do you calculate for all g, right? You have to calculate all the g, that is all the subsets of s. So one way is you can do that recursively, but I'll be discussing a very easy way in which you will be calculating g using a single for loop, right? So I'm going to discuss a very nice way. Let's say your subset s is something, some integer 1 0 1 0 1 0 0. Okay, so let's say this is your integer, and you would like to generate all the possible subsets or submasks of this particular mask s, right? You want to generate all the g's, right? Which is 1 0 1 0 0 0 0, and it could also be only 1. So the point is like generating all the subsets. So a single liner that can do the work is, you set m equal to x s, m is the current mask, and then m not 0, we are not considering the empty mask, right? And then what you do is m equals to -1 and s. All right, this single liner for m equal to s, m not equal to 0, m equal to m -1 and s will generate each and every of the possible submasks for this particular mask s. Now how does it do that? I'll simply show it to you by using this example, and if you'd like to see how it really works, the proof, you can read it on Code Forces or CP algorithms. For now, I'll just show you an example how this thing works. Okay, so what really happens is, when you're generating the subset, first of all, m equals to s, then this set is generated, the set of all the possible elements. Then you say, okay, m -1 and s. Then what happens is that this is effectively turning off the least significant bit, right? The least significant bit gets turned off, and any bit that is and all the bits before that are now on, right? This is what m -1 looks like. Now what you do is you AND it with s, then these two bits go away, and you generate the set 1 0 1 0 0 0 0, right? Next, what you will do is you will be doing again -1 in this bit will get turned off, and you will get 1 0 0 and 1 1 1 1. Then you will AND it with s, and you will get the subset 1 0 and 0, again 0 and 1 0 0. So you got another subset. Then next time this bit will also get turned off, and you will get the subset 1 0 0 0 0, and again next this bit will get turned off, and you will have 0 1 1 1 1 1, and then AND it with s, you will get these two elements, right? So this way you generate all the possible g's using a simple for loop. You could have done that recursively, and that might be more intuitive to you. However, this is a very simple way, and it is simple to prove why it always works. You can read it over the internet if you feel less confident about why it works. Okay, so for now we can be confident that this works and move towards the implementation. So we have to implement this particular recurrence, and for that we'll be needing to pre-process sum of g. Okay, so in our implementation we'll simply be calculating sum g one by one for all the possible g, and g is represented by an integer, so all the possible subsets. So g goes from 0 up to 2 to the power n -1. Okay, cool. Let's move towards the and. Yeah, also we saw a way to calculate for a particular g in n square time what is sum of g. We'll be storing it to use for later use, right? Now let's move towards the implementation. So yeah, I've written some code beforehand as only. So this dp array will be storing our final answers, and our final answer will be stored at dp of 2 to the power n minus 1. Okay, and the sums array is nothing but the score that you get by grouping the elements represented by this set or this mask. Okay, first of all we will be completing this prepare sums, and this will basically fill this sums array one by one, and then we'll be using the solve function to get our answer. Here I've taken this input, n is nothing but the number of rabbits we have. Then this is a 2D matrix to take the score inputs. Here I've taken the input. Next we'll be calling solve function with the score 2D matrix passed by reference. And initially I have all the rabbits available to me, so my mask is represented by 2 to the power n minus 1, that is 1 1 1 1 1 n times, right? Okay, so okay, let's implement solve first, and then we'll go to implementing prepare sums. Alright, so we'll simply be implementing as discussed, and if mask is 0, that means no more rabbits are left. Then this is the base case, and we should return 0 since no rabbits are left. There is no grouping to be done. Okay, otherwise for all the subsets of the mask that I am given, or all the sub masks, the first group could be any of these masks. So as discussed, we have a sub mask. Initially I set it equal to mask, then sub mask not equal to 0, I'm not considering the empty set, and then sub mask equal to sub mask minus 1, and mask. Okay, so guys, I would recommend you to study a proof why this always works. You can easily find it on the net, why this statement will generate all the possible submasks of the mask. I just showed you an example. You can Google it and you'll find really good proofs why this always works. Otherwise we could have simply written a recursive function that would have generated the each and every submask of mask by setting one bit off in each recursive call. Okay, but for now I am using this for loop, as of course this is much easier. Okay, so let's say my answer is LL answer. Initially I assume it to be 0, and as I get better values I'll set it equal to that. So my first group that I'm forming is represented by my submask. So by doing that I get a score sums at submask, plus I have to get the answer for the remaining rabbits, right? So again pass score, and now mask minus submask. Okay, so since this is a set difference, I could not simply do mask minus submask. I'll discuss it how we can calculate the set difference using some bitwise techniques. So basically we had a mask something like 1 0 1 1 0 0 1 and something like this. Let's say we selected the first group to be represented by 0 0 and maybe 1 0 0 0 and 1. So the first group that we are forming is these two rabbits are in the same group. Okay, now what we would like to get is the remaining group should be the set difference of these two, which is 1 0 and this is 0, this is 1 0 0 0 and 0. So how can we basically achieve this kind of set difference here? So yeah, it might be visible to you that simply XORing the bits will achieve this kind of effect. So if a bit is on in our mask and it is also on in the submask, XORing these two will make it off in the difference, right? So I guess we can simply XOR these two, right? And if a bit is off in our submask but it is on in our mask, it will stay on because 1 XOR 0 is 1. Yeah, so we can simply XOR these to get the set difference. Okay, just a second guys. Yeah, so I've selected the first group and added the score for that group, sum of submask. and then my remaining group is represented by the set difference, which is masks or submask. And if this answer is better than the current answer, then set it to be the answer. Okay, and it's as simple as that, I guess. After this, I'll simply return the answer and we're done. Now we have to write the prepare sums function. Okay, so we are given the n, which is the number, the total number of rabbits. Okay, so simply for all the possible subsets, integer subset equal to the empty subset and up till, in fact I don't need to calculate for the empty subset, subset less than 2 to the power n and subset plus plus. So as I discussed previously, we'll simply be implementing the n square algorithm to get our answer. Let's just call a function for that as well, and dp at subset equal to get maybe calculate for this particular subset and this score. Once this is done, we'll have our sums array prepared. Also this has to be sum, not dp. Now I'll be implementing calculate. So now I'm going to calculate the answer for the rabbits represented by this subset or this mask. LL answer equal to 0, and for every bit of this mask, for the ith bit of this mask, I goes up to let's say 16, or for safety sake 17, and then for every jth bit that is to the left of I, so for every jth bit equal to I plus 1 and j less than 17, j plus plus, if both the ith and the jth bit are on, then I will be adding aij to the answer, right? So if the ith bit is on in the mask, ith bit is on, how will I find that? I will take the mask, I will take 2 to the power I will add these two values, and then if it is 0, then ith bit is off, otherwise ith bit is on, right? So first of all, mask and 2 to the power I. If this quantity is not 0, then of course ith bit is on. So if the ith bit is on and also the jth bit is on, then my answer becomes answer plus equal to score at ij. Alright guys, so hopefully this is very much clear to you. I'll return the answer here, and I think this code should now work. We'll try a test case. Let's try this one. Okay, there's an error. Okay, there is some problem with the brackets, I think. This looks alright in the bracket here. Yeah, now it should work. Yeah, this has to go up to n because the grid size is n square and not n into m. Okay, so there is some problem with the code, I guess. Let me see what it is. First of all, I want if dp is not yet calculated. So if dp at mask is not yet calculated, now I have to keep some value that signifies it is not yet calculated. It could not be -1 here because the total score for some grouping could be -1 given that these compatibilities are negative as well. So I'll take it to be a very large value. I have defined infinity as 2 to the power 60 and I'll return dp at mask here. But the problem is not due to this, I guess, because this will only help me with faster execution, right? This only reduces the time complexity. There is some more error as well. Let me just check what it is. Alright, so basically I haven't called the calculate function. Calculate has to be called, not calculate, prepare sums. Otherwise the prepare sums array is initialized to some garbage values. I guess I just have to pass the score only and then. Alright, now let's try and run it. Where sums, it calls for every subset up to 2 to the power n and sums array should be ready. Alright, so I haven't even initialized dp to infinity, so I need to do that. I'm going to do memset. Basically I'm setting that dp is not yet calculated, any value of dp has not yet been calculated, and it should now work. Overflow and conversion from long to int. Why is it saying so? 1ll60 to have here, but I guess my dp array is long, right? So I should not be receiving this error. An expansion of macro infinity. So what I'm assuming is that memset receives long, and therefore basically memset receives an integer and I'm passing it a long, so it's not accepting it. That's what I'm thinking. What I'm gonna do is I'll use this to initialize it, the prepare sums only, and for every value I'll set it to infinity. dp at subset equals to infinity. Alright, now I'll try it again. Alright, so we're getting the correct answer for this case. Let me try sample input 4. We should get 132. Alright, we're getting that answer. We'll try and submit. Till then I'll explain you the time complexity and space complexity here. So obviously the space complexity is 2 to the power n. Okay, because I've taken two arrays of the size 2 to the power n. Again, time complexity, initially this pre-processing is nothing but n squared, the number of bits squared, and this solve function. Okay, so for every state we have 2 to the power 16 states or 2 to the power n states, and for every state we are looping through all the subsets of that state, right? And this I'll explain it to you. Let me just check. Yeah, so we're getting an AC. I'll quickly explain the time complexity here. So if my mask has I bits on, this loop will run 2 to the power I times, that is the number of subsets the mask has. So how many uh, for how many mask values will this loop run 2 to the power 16 times? There is only one such value, or one of the 16 of the 16 bits are on. So 16 C16 2 to the power 16. And in how many masks will this loop run 2 to the power 15 times? It will be 16 C15 of such masks. Again, 16 C14, these are the number of masks in which 14 bits are on, and for these masks this loop will run 2 to the power 14 times. Okay, so you can clearly see that overall this loop runs summation 16 Ci 2 to the power I times. I goes from 0 to 16, and I here is the number of bits that are on in the mask, and this is the overall time complexity for this. Now to calculate basically what the sum of the series, I've written a simple program to prove that yeah, it runs in the time bound. You can go to Wolfram and other online series calculator and you can calculate the sum for this. However, I claim it is less than 2 to the power 26 and around the range of 10 to the power 7. So here is the simple code I've written for this. So this is to calculate the binomial coefficient NCI, NCK, and then the sum of the series up to 16, and you can see this value comes out to be, yeah, it's much less than 10 to the power 8, the number of operations we are allowed to do. So it's in the range of 10 to the power 7, and yeah, the time complexity fits into the time limit. Okay, so guys, thanks for watching. Hopefully the video was helpful to you. I'll see you in the next video. Hi guys, my name is Karthik Arora, and in this video we'll be solving V subtree. This is another very good problem on DP on trees, and the problem says that we are given a tree within vertices. We would like to paint it using black and white colors, so a node can be painted either black or white, and we would like to find out the total number of ways in which we can color the tree so that the coloring is valid. Okay, now a valid coloring is defined as, if you color some nodes black, then any black node can reach any other black node through a path consisting of only black nodes. Okay, so here is an example. So this is an invalid coloring because starting from here to reach this black node you'll have to go through a white node, right? So this is invalid. Now let's talk about something valid. So let's say this node is white, this node is white, and rest all other nodes are black. And starting from any node you can reach any other node only passing only through black nodes. So you can go from this guy to this guy only through black nodes, right? So this is a valid coloring. Now what we would like to do is, given the tree, we would like to find out the total number of valid colorings modulo m. So that is the problem statement, and also we have to find the total number of valid colorings for every possible node, right? And they say that assume that the node V has to be black. Okay, assume that a particular node has to be black and then find out the total number of valid colorings. So this is the problem statement, and we will have to do it for every possible V. So for 1 less than equal to V less than equal to N. So first of all, assume that node number 1 has to be black, and then find out the total number of valid colorings given that node 1 is black. Then given that node 2 is black, find out the total number of valid colorings and up to the nth node, and then print the answers for each and every of this case. Let's look at our sample input. So we are given n and m. N is the number of nodes, m is modulo what you have to find the answer, and yeah, we'll be given n, m, and n, then the followed by the edges of the tree. So you can look at the first sample input and output, and they've shown how the number of ways to paint it. So they say that there are 7 ways to paint the vertices as shown below. Among them, 3 ways so that vertex 1 is black. So you can see that this one, this guy here, and this guy here, and this guy here. Among all these ways, the node number 1 is black, so overall 3. Then we have this particular, wait a second, we have this example and this example, this one and this one. These 4 ways in which node number 2 is black, so 4 for that. Finally, for 3 also we have 3 ways in which node number 3 is black. Yep, so 3, and that is what we have to output. All right, okay, you can check the sample input 4 as well. So here in sample input 3 there is just one node, and assuming that node number 1 is black, the number of ways to paint the tree is exactly 1, because this is the only possibility. Alright guys, so hopefully the problem statement is now clear to you. We'll be moving towards the solution. Alright, so we're solving V subtree. So we're given with a tree, right? And what we are supposed to do is assume that a particular node V is black, and then find out what is the valid number of colorings in which node V is black. Okay, that is our goal, and we have to do this for every V. So let's try to do it for one particular node, and then we'll see how we can do it for every node. Okay, so let's say this is my tree, and this is some node, maybe 1, and I'm assuming this to be black. So I paint this node black. Alright, now I wish to find out the number of ways in which this tree can be colored so that the colorings are valid. Okay. Okay. So let's think about these subtrees. Okay. So what if I knew the the number of ways to paint this particular subtree as independent of the remaining tree? Imagine if only this subtree were present. Then if I knew the number of ways to paint this particular subtree rooted at this node, maybe some x, so that x is black. If I knew this, same way, this is x1, this is x2, and this is x3. So suppose that I knew, and I'm rooting my tree currently at this particular node. So I have rooted my tree at some arbitrary node for which I'm trying to find out the answer. So if I knew the number of ways to paint the subtree rooted at x1 so that x1 is black, same way for x2 and x3, then I could definitely find out the number of ways to paint the entire tree rooted at this particular guy, maybe node number 1. Okay, now let's see how we can do that. Of course, if there are some ways to paint this tree in a correct manner and some ways to paint this subtree in a correct manner so that x2 is black and x1 is black and x3 is black, then of course we could simply multiply these different ways to get the total ways to paint it, right? Also, just to clear a doubt if any, why do we multiply these ways? Let's say there were maybe some, okay, I'll just take another example now. So I had some tree, this guy has some number of children, and I'm assuming that my tree is rooted at this node, right? So this is the root of the tree, and I'm trying to find out the answer when the root has been painted black. So I'm trying to find the answer for this node root, the node which I have assumed root. I'm trying to find the answer for that. Okay, now let's say for this particular subtree rooted at some child number 1, some child 2, child 3, and maybe child 4, if I knew the number of ways to paint the subtree independent of the remaining tree, so that C1 is black, and let's say there were W1 ways to do that. There were W1 ways to do that. And to paint the tree so that C2, node C2 is black, there are W2 ways to do that. Same way W3 and W4. Okay. Now, why do I multiply these ways to get my overall answer? Also, one more thing. Why do these children nodes have to be black? Because if they are white, then the entire subtree has to be white. So if C1 is white, then entire subtree has to be white, because if there is any other black node, then going from root to that node in this subtree somewhere here which is black, I definitely have to pass C1, but C1 is white, so I'm violating the condition, and this is an invalid coloring, right? So C1 has to be black if there is any black node in this subtree. Otherwise all of this subtree can be white. Okay, so overall for the root, this particular subtree can be painted in W1 plus 1 ways. One is for if I paint this entire subtree white. Okay, that is a valid way. And W1 is the ways, given that C1 is black, what is the number of ways to paint this subtree independent of the remaining subtree. So here also this subtree could also be painted white, this one also, and this one also. Now why am I multiplying these ways to get my overall answer? This is because imagine there are W1, I'll take this W1 dash, W2 dash, W3 dash, and W4 dash. Okay, so since there are W1 ways for this, W2 and W3 and W4 ways for these, imagine I take the first way here, and I could take any of the ways here, any way here, any way here. So I could take the first, and first. Just for clarity's sake, wait a second. Okay, so there were some W1 ways for this, W2 ways for this, and W3, W4. Now imagine I take the first way for the subtree 1, and the first way for this, the first way for third one, and fourth one as well. This is one possible coloring, right? Color the root black and then take the first possibility of for each of the subtree. The other way is I take 1, 1, 1 and 2, and so on up till 1, 1, 1 and W4. So these are W4 ways, right? Up till here, these are W4 ways. Now what I could do next is I could take this 1, 1, 1, 2, 1, 1, 1, 2, 2, up to so on till 1, 1, 2, W4, right? So doing this again and again, you will find out that overall the number of valid ways is W1 into W2 into W3 into W4, right? So this is why we are multiplying, and here is a recurrence. Now I'll be writing a recurrence. So dp of u equals to, so I'm assuming that node u has to be black, and I'm assuming that node u has some children. So the number of valid ways to color node u, so that color the subtree rooted at node u such that node u is black, is given by product 1 plus dp of ci for all ci where ci is a child of u. So that is what dp of u is. So now we can easily find out for a particular root, we can easily find it out for any node by assuming it to be the root of the tree and then using this recurrence to find out the answer, right? So simply, if I wanted to find out the answer for node number 1, that is assuming that node number 1 is black, so I will be rooting my tree at node number 1 and following this recurrence to get the answer. This recurrence can be overall evaluated in big O of n time, right? Where n is the number of nodes in the tree. But for each and every node, if I repeat this process, then my time complexity will again become big O of n square even after using the DP recurrence. So now we need to optimize this thing further so that we are able to calculate all the answers in big O of n and not just one. So let's pay attention to how we reached to the recurrence once again. Okay, so I was trying to find out the answer for node number 1, assuming that node number 1 is black, and then I saw that it breaks down to the answers of the children, right? Okay, so for the node 1, I would assume this subtree independent of the remaining tree, and for same way for C2, C3 and C4. Now there will come up a time when I'll be finding the answer for C1 also, right? There will come a time that when I am supposed to find out the answer for C1. So C1 will have some children of its own. Okay. Also, when I am finding the answer for C1, I am assuming C1 to be the root of the tree, right? In that case, 1 also is considered to be a child of C1, isn't it? When I root the tree at C1, my tree becomes this C1, the children of C1. Node 1 also is now a child of C1, and again 1 has C2, C3 and C4, which might further have some children, but of course there's no need to draw them here. Okay, so when I'm trying to find out the answer for C1, this will be the condition of my tree, the way I'll be looking at it, isn't it? So maybe I could use the answer for 1 to find out the answer for C1, and I'll be trying to do just that. So when I'm trying to find the final answer for C1, it will be the products of the answers for these children, assuming that these children are unaware of the remaining tree, and I'm taking the subtrees rooted at these nodes. So these answers will be needed to find out the answer for C1. Also, I need to find the answer for this subtree. Okay, so I need the answer for the subtree 1, C2, sorry, yeah, 1, C2, C3 and C4. Okay, so this answer is nothing but the answer for 1 except the W1 plus 1, isn't it? So the product was something like pi Wi plus 1, I goes from 1 to 4 for node number 1, isn't it? Because if W1 plus 1 were the ways to for this subtree and W2 plus 1 were the ways for this subtree, similarly for these, then my answer for 1 was this. Now what I'm looking at is this subtree, and for this guy my answer will be nothing but the same thing without the W1 plus 1, isn't it? Yes. So we can use this idea to optimize our solution to big O of n. Here is what we will do. Okay, so assume that we were initially finding out the answer for this node number u. Assume this node has k children, right? And it says this is the ith child of node u. So we know that the answer for node u is simple. It is the number of ways to paint this subtree rooted here, assuming that this is not present, right? And same way the ways to paint this subtree, the ways to paint this subtree plus 1 and product. Okay, so pi, let me just define what this means. So I'm defining dp1 as the ways, dp1u as the ways to paint subtree rooted at u. Ways to paint subtree rooted at u given that u is painted black. Okay, so this is what dp1 of u means. And now if I name the child nodes of u to be c1, c2, c3 up to ck, then dp of u recurrence is simply product of 1 plus dp of ci over all I from 1 to k. Now imagine once this is done, I have the answer for u. But when I'm thinking about calculating the final answer for I know what dp1 of I is, that I know, cutting this off. However, I would like to find out the actual answer for I also. That is assuming that node I is the root. So let's just define one more term now. Okay, let's define dp2u as the number of ways to paint the subtree rooted at node u, or the number of ways to paint the entire tree given that node u is black and assuming that u is the root of the tree. So dp2 of u is simply assume node u is root of tree and it is black, then dp2 of u is simply the number of ways, the valid colorings assuming these conditions. Okay, so initially for this guy dp2u, or the initial root that I assumed, for that dp1u is equals to dp2u, so that is easy to find out. Now for the ith guy, I knew what dp1i is, that was easy, I knew what that is, but I wanted to find out what dp2i is, right? That is the actual answer to the problem. So dp2i was assuming node I is the root of the tree and I is painted black. Now for this I can reuse the answer for node u. For dp2i I can reuse the answer for this guy. So the answer for dp2i is going to be whatever dp1i was multiplied by dp1i was number of ways to paint this particular subtree rooted at node I, and given that node I is black, into, so dp1i into whatever the answer you get from the parent plus 1. Okay, 1 plus answer that the parent gives you, and what the parent should give me is the number of ways to paint this entire thing assuming that I was not a child of u. Okay, so this is the answer I need from the parent of I to calculate dp2 of I. Precisely to get this guy, this is nothing but the product till the I minus 1th child here for u. So the prefix I, the product till the prefix I minus 1 into the suffix from I plus 1 to k. So suffix I plus 1 to k. This product is going to give me the number of ways to paint this tree. And now I can simply use this answer, if I know this, to evaluate dp2i, and that's it. Doing this, I can pass the actual answers for the parents to the children, and then the children can use these answers to evaluate their final answers as well. Okay, so just for clarity, this answer thing is going to be u is black, u does not know that I is the child of u, and the number of ways to paint this particular tree which are valid. So this is basically going to be 1 plus this guy is dp1 of c1 into 1 plus dp1 of c2 up to 1 plus dp1 of ci minus 1, and then missing I in the product, then going from I plus 1 to k. Guys, hopefully this is clear. I'll explain how we are going to implement it. First of all, we can directly evaluate dp of 1 of I. That is the easiest part because we have a very basic recurrence. This is simply nothing but dp1 of c plus 1 product c is a child of I, and then we can calculate dp2 of I. I am assuming that the root of tree is 1. Root of tree is node number 1. Arbitrarily taking any node as the root. dp2 of I will simply be using the answer of the parent. The parent will be passing me an answer. That answer will simply be that the parent, if the parent did not know that the child existed, then what was the number of ways to paint it. Okay, so that is simply that, this answer. Okay, so dp2 of I is simply going to be answer plus 1 into dp1 of I, and answer will, for the root, for the actual root of the tree, answer is going to be 0. Yeah, because dp2i will be dp1i for the root. And that's it. This is the way we'll be implementing it. After this is big O of n. So let's move towards the implementation now. Okay, so if you still have any doubt, it will be cleared while we are implementing it. Okay, so keep following. So initially I've taken here the input, the number of nodes, and the modulo value m, and then I've taken a tree. We'll declare it here. So it's nothing but a vector, an adjacency list representation. So vector and tree. Okay, and we have, so I take this visited array, mark it 0, and I call solve1. This should evaluate dp1 values. Then again do memset with 0, and I call solve2. This should calculate the dp2 values, and once the dp2 values are calculated, I could simply go from 1 to the nth node, and I could do cout dp2 at I. So let's implement solve1 and solve2 now. So for solve1, as we discussed, first of all I'll be marking the source to be visited. Now for every child of this guy, so for every child of tree source, if the child is not visited, if not visit child, then calculate its answer. So solve1 child comma viz comma just a second, I think I messed up in solve1 and solve2. It should be the other way around, right? This should be solve2 just to be consistent, right? Because this is what we discussed, dp1 and dp2. So all right, so I'll be calling solve2 solve1 and child viz m, and once for every child this thing has been calculated, for this guy let's say dp1 is ll answer, and I put it equal to 1. Instead let's just say dp1 at src equals to 1, and once I called this and I'm back from this call, that means the answer for the child has been evaluated. Then simply dp1 at source equals to dp1 at source into 1 plus the number of ways for the child. So 1 plus the number of ways for the child are dp1 at child. Okay, and here I'll mod it with m. So I guess after this function has run, I should have dp1 for every possible node of the tree. Okay, now let's consider dp2. Okay, so again mark the node visited once you reach it, and now as we discussed, we'll need the prefix and the suffix to calculate parent answer. First of all, we'll do this thing: dp2 at source is equals to 1 plus parent answer into dp1 at source, right, as we discussed in the recurrence. And then we'll need the prefix and the suffix for the ith child to pass the answer for this parent. I need the prefix and the suffix also, so let's evaluate that. Okay, so let's take a vector ll prefix and a suffix. So for every child of this node, for every child of tree at source, prefix dot pushback prefix dot pushback dp1 of child, and suffix is sorry, suffix is simply going to be the reverse of prefix. So right now I will be pushing dp1 of child and then I'll reverse it. Okay, so I guess there is a direct function in STL to reverse suffix dot begin and now I have the prefixes and the suffixes. Now I simply need to call every child of this particular node and tell them to calculate their answers. Okay, so again, for every child of tree source, we'll be calling solve1 if child is not visited, of course, not visited, then call solve1. Okay, now I need to think about how to use the prefixes and the suffixes. So before I really move forward, consider this. Let's say currently we were evaluating the answer dp2 for this guy, and now we'll be calling the children nodes for this guy. Okay, so for this node, to calculate the answer for itself, the overall answer for itself, what it would like to know is the answer for the parent, right, and of course the dp1 of itself, but the answer for the parent is also very important. Now how do I send it the answer for the parent? That is simply 1 plus the product 1 plus all these children and also this guy. So 1 plus the parent answer of this and this suffix of products, right? Next, when I need to find the answer for this guy, what I'll be passing is this prefix of products multiplied this by this suffix of children 1 plus the suffix of basically product 1 plus till this guy, so the prefix nodes of, and similarly these into 1 plus the parent answer of this guy. So 1 plus parent answer is always there. So hopefully this idea is clear to you, and now we'll be seeing how we can pass this required parent answer to the next guy. So I have calculated my prefixes and suffixes. Initially for the first child I'll simply be the answer that I'll be sending forward is simply the suffix except the 0th element. Okay, so first of all what I'm going to do is for integer I equal to suffix dot size minus 1, I stays greater than equal to 0, I minus minus, then in fact I can start from -2 and suffix at I. Also I should be putting 1 plus dp1 here because of the case in which the entire subtree is black, entire subtree is white. 1 plus for that. Yep. And suffix at I becomes equal to suffix at I into suffix at I plus 1 whole mod, right? So this should make the thing very much clear to you now. Same way we'll build our prefixes as well. This will be starting from 1 going up to prefix dot size I plus plus, and it will be prefix of I equals to prefix of I into prefix of I minus 1 and whole mod. Okay, so for the first child, let's number them. Integers C number, child number. Initially I'm at the first child, or let's call him 0th child. Okay, yep. Okay, then if not with that child, then the thing I'll be doing is for the 0th child I have to take the suffix starting from CNO plus 1, isn't it? So suffix starting from CNO plus 1 excluding 0th and all the child from 1 till the nth, right, or the kth child, right? And I have to take the prefix CNO minus 1, but CNO minus 1 is of course negative, so I cannot take that. LL ways equals to 1 plus parent answer first of all, and now depending upon the child number, ways equal to, if CNO greater than 0, then ways equals to ways into prefix at CNO minus 1. Yeah, that seems alright to me. Same way I have to check if I need a suffix or not. If CNO is less than suffix dot size, in fact suffix dot size minus 1, because the last entry of suffix represents the CNO, the last child, so only the second last child will have a suffix. Greater than 0 suffix minus 1, and this will be suffix CNO plus 1, and we know the ways that we need to pass to the next guy, so we'll be calling solve1 the name of the child, and visit solve2 source visited m and parent. Okay, so solve2 child visited m and parent answer, that is ways, and I guess that should do it now. Once this is done, we'll have our answer at the dp2 array. Let's just check a sample test case and we'll know. Let's just check sample input 4. So some error running the code. I'm sorry, I'm not connected to the internet. Just a second. Alright. So now I'm connected. I'll just hit. The answer should be 003101. So 944 is equal to this. Oh, just a second. Also here I need to add modulo m. Same way here I need to add modulo m. And the second case in which the ways remain equal to ways. Alright. I think I should have taken a better test case to run, but it's okay. So we're getting an incorrect answer. Let me check why. So looks like some problem with the mod here, I guess, and I haven't taken the mod properly here. With this the problem should hopefully be fixed. I'm taking the mods here. Yeah, it looks like the correct output. 01011. Yep, looks like the correct output. I'll just check one more test case. It should be 8 and 3 5s. Yeah, we are getting the correct answer. I'll check, submit and check, and then we can discuss the time and space complexities. So I guess this will pass. No, we are getting a WA. Let me check what's wrong. Alright guys, so I have missed a major thing here. We did take the CNO in account, but I never incremented CNO here. I wonder how the other test cases passed. Okay, now this should be working, because this was important. If there is more than one child, then this will make a difference, I guess. In some of the test cases there was only one child for every node. Now this should most likely run. I'm really sorry about this mistake. There was no point of reversing this suffix. Okay, why? Because the prefix is simply the first guys, node 1, node 2, node 3, node 5, and the suffix is simply 5, 4, 3, 2 and 1. Okay, so if I reverse it, these are basically the same things. Okay, sorry about this mistake here. This should have been, there was no need to reverse this. Okay, and now it will pass. Let me just submit it. Now it will pass. Really sorry, I had to pause to find out the error in the code, and it was it gave me quite a hard time. Here I have used modulo mod, and I have defined mod to be 10 to the power 9 plus 7, whereas the problem asks me to mod it with m instead of modulo, right? And that is the reason of all the WAs till now. So I'm sorry about that. I'll just check if I'm using mod anywhere else. No, now I'm not using it anywhere. So let me just try and submit it now. Sorry about this delay. Yeah, now it is passing. Alright, so the time complexity is the same as that for a DFS or a BFS, which is big O of n. We're simply using two solve functions and they are basically performing DFS, that's it. Alright, and of course, so it's big O of n. Hopefully the solution was clear to you guys, and yeah, here's the mistakes that I've made. We can look over them once again. Yeah, so we've got an AC here, V sub 3, and the mistakes that we made. So the major mistake that I made was modulo mod instead of modulo m, and here I did not need to really reverse the suffix. The point of suffix was to reverse in the reverse direction and multiply the children from the right to left, and prefix was meant to multiply the answers of the children from left to right. And here I forgot to increment C number as well. I had to increment C number to be aware of what answer of the prefix and what answer of the suffix I require. Yeah, other than that, initially I did not mod m here. Okay, so guys, hopefully this was a helpful video to you. It is quite helpful to watch other people debug their codes as well. So thanks for watching. I'll see you in the next video. Hi guys, my name is Karthik Arora, and in this video we'll be solving the problem W intervals. So we'll be making two parts. Basically I'll be making two parts for this particular problem, and in the first part we'll be discussing a brute force DP solution to this problem, and in the next part we'll try to optimize the same brute force DP solution and then fit it into the required constraints. Okay, so you can go read the problem once and then we'll begin. So we are given with okay, so we want to generate a string of length n, and the string will have zeros or 1 at any places, right? Okay, then for each I, ai is added to the score if the string contains one at least once between li and ri characters. Okay, so consider that there is some interval that starts at li and it ends at ri. So there is an interval that starts at li and ends at ri, and this interval has some corresponding score si. Okay, so si will be included in my total score if in my string there is a one anywhere between li to ri, at least one anywhere between li to ri, then si has to be added to my total score. Okay, and there will be m such intervals, and I have to construct my string in such a way so that the sum of the intervals which are being considered, the total score is maximized. Okay, so I hope the problem statement is clear, and if it is not, with the sample input it will be clear. Okay, so here in the sample input one you can see that we are supposed to make a string of length 5. Okay, and this has to be a binary string, so either zeros or ones have to be filled, and the first interval starts from 1, ends at 3, and if this interval gets included, then a total score of 10 must be added. Then a 10 must be added to the total score I'm getting. Okay, then there is an interval from 2 to 4. Let's say this is plus 10. Then from 2 to 4 there is an interval, and this has the score minus 10. Again from 3 to 5 there's an interval, and the score for this interval is plus 10. Okay, so sensible thing would be if I am able to include this guy and this guy. Okay, and I could put a 1 here and I could put a 1 here and all these could be taken as 0. Then I am not including minus 10, but I am including both the plus 10, so my score is coming out to be plus 20. Okay, which is the output, so I have to output 20. So we can look at the sample input 2 as well. So we are interested in a string of length 3. There are 4 intervals given. Okay, the first interval starts at 1, ends at 3. Okay, second from 1 to 1, here the score is 100. For this the score is minus 10, and then from 2 to 2 there is an interval. For this the score is minus 20 and then from 3 to 3 also there is an interval and minus 30. Okay, so the best thing would be 100 minus 10 by doing this. Okay, and I will get a score of 90. I guess that must be the output for this case. Yeah, so you can see that the score is 90, and since I'm putting a 1 at the first position, then I'm including this guy with the 100 score, and I'm including this -10 guy, and this -20 and -30 do not need to be included in my score, and my score comes out to be my total 90. Okay, so you can also see the sample input 3. In this we can construct the string 0 and include no interval. Okay, then our score becomes 0. Alright, so guys, hopefully the problem statement is clear to you. Majorly what we are supposed to do is we are supposed to construct a string of length n, and in the string only zeros and ones can be written down, so it's a binary string, and among all the possible binary strings we have to tell which one has the highest possible score. So straight off we can think of a 2 to the power n solution, or maybe a little higher than 2 to the power n, and we can generate all the possible strings. There are 2 to the power n possible strings, and for each string we can find out what is the answer for that string, and whichever string has the best answer, that is our output, that score. Okay, cool. So we have a brute force solution now, but that is exponential, and we can see that n is up to 2 into 10 to the power 5, and the number of intervals can also be up to 2 into 10 to the power 5. Alright, let's move to the solution now. Okay, this is solving W intervals. So first of all, let's just rephrase the problem. We have n empty positions, okay, and I could fill a 0 or 1 in any of these positions, and have some intervals, okay, that looks something like this. And if for any interval that is starting from Li going up to Ri, if there is a 1 at any of these empty positions from Li to Ri, then a score of Si must be added to my total. Okay, alright, so there are a lot of such intervals. So again, it might make sense to first of all sort these intervals up to according to some criteria, isn't it? Because it makes more sense to look at some sorted intervals instead of them being not sorted. Okay, so let's see what we can do with that. So imagine I'm thinking about my string, okay, and I'm thinking about the nth position. So of course I could either put a 0 or 1 at the nth position, right? Now if I put a 0 here, my problem simply reduces down to this thing, because putting a 0 here means that it is almost like it is that nth position is absent from my string itself. Okay, so my problem will simply be the best answer for the string with length n-1, isn't it? However, if I put a 1 here, then is the interesting case. Okay, so if I put a 1 here, first of all, the score for all the strings that end at the nth position has to be added. Okay, so it makes sense to know which all strings are ending at the nth position, and moreover it makes sense if these strings are sorted according to their endpoints here. So if I knew the strings that are ending at maybe the nth position, something like these 3 people, let's say, this is just an example, there might be no string ending here. In that case, making it a 0 or 1 makes no difference to us, and there could be just one interval ending at the nth position, or there could be many. So I take for example 3 intervals end here. Okay, now what happens if I put a 1 here? First of all, the score for these things, 3 intervals, has to be added to my total. So score of these will be added to my total. Score of, let's say, intervals that end at n. Okay, now my problem will reduce down. Okay, so since I've put a 1 here, I'm getting the score for these 3 things. Now after putting this 1, my problem simply reduces down to this thing, except that these 3 intervals are not to be considered again. Okay, since I've considered these 3 intervals and the score for these 3 has already been added, so even if I put a 1 here, these three intervals score must not be considered again. Okay. Alright, so I have to take care of this thing that I do not consider the same intervals again and again. Okay. Okay. Okay, so before we actually build a recurrence, let's consider a few more things. Okay. So first thing is that writing a zero somewhere nicely breaks down our problem, and the problem is nothing but generating the best possible string with n minus 1 characters, okay, instead of n. So writing a zero nicely breaks down the problem. There is no problem with that. Okay. However, when we are writing down a 1 at the nth position, then there is something to take care of, right? So one thing is that if you write a 1 at this position, then a string will be something like this: some number of zeros, and then there will be one more one, right? It will look something like this. These could be a lot of zeros, then finally a 1 comes, or it could be straightforward 1 and then again a 1 in the best possible string. Okay. So let's first of all define what dp of I means. Okay. So as we saw that writing a 0 is nicely breaking down the problem, so let's forget about the case in which we write a 0 at the nth position. Let's define dp of n. This is the best possible string or the best possible score for a string if the nth position I write a 1. Okay. If nth position of string, if nth position of string has 1, then the maximum possible score. Okay. Max possible score for such string. So dp of n is basically the best out of all such strings which end with a 1. Okay. So these are all the strings like 0 0 0 0 0 1, the nth position, or they are something like a 1, then some zeros, and then finally again a 1. So you get the point, right? That the nth position has to be a 1 and the maximum possible score for such a string. So we have defined what dp of n means now. So on similar lines, dp of I is the best possible score for the string that starts from 1, ends at I, so that the ith position is a 1. Okay. We have a definition of dp now, and if we were able to evaluate dp of I for all the possible I, if we were able to evaluate dp of I at every possible I, then our answer is simply going to be the max out of all these, right? Why is this so? Because in my answer string, there will be one rightmost one in the answer, right? This will be the rightmost one in the answer, and this is at some index I. The rest will be simply be zeros. So whichever is the rightmost one in my actual answer or one of the feasible solutions, we are considering every possibility, isn't it? So dp of I is basically all these zeros, and the ith position is a 1, and the best possible thing that you could do for these first I minus 1 people. So this is what dp of I is. So if I were to evaluate dp of I for every I, then I could know if the rightmost one was at the ith position, then what is the best possible answer. And of course, in my best possible answer, my the rightmost one has to be somewhere, or the answer is going to be 0 if the complete string itself is a 0. Otherwise, either my rightmost one will be at the first position, or it is going to be somewhere in the middle, followed by a lot of zeros to the right and some string at the left. So hopefully this thing is clear to you. Now we'll see how we can generate dp of I, because we know that my answer is simply going to be the highest of dp of I or 0. If all intervals are negative, then my answer will simply be 0. Otherwise, it will be the maximum possible dp of I. Just for clarity's sake, I'll be writing the definition for dp of I once again. So this is the score, or the maximum possible score for any string, or for all the possible strings that have their rightmost one at the ith position, that have their rightmost one at the ith position. Okay, now let's see how we can calculate dp of I for every I. We'll be writing some transitions if possible. Now let's try to calculate dpi. Okay, so consider the string and let this be the ith position, and there will be many strings that basically cover the ith position. So this starts somewhere before I or at I and end at I or after I. Okay, so there will be some intervals like this, and maybe something like this as well. So you get the point. These are the intervals which have to be included in my total score if I put a 1 at the ith position. So imagine I put a 1 at the ith position. Now among all the possible strings which have a 1 at the ith position, and these things are 0, any position to the right of I is 0. I'm not going to write these, but just to make it clear, yeah, I am considering them to be 0. So among all these such strings, there can be some strings in which all the left people are also 0. In that case, my answer is simply the sum of the scores of these intervals that cover the ith position. And there is one more possibility, that one thing was that all these were 0, and the other possibility is that there is a 1 to the left of I somewhere at the jth position. Okay, so there is some jth position at which there is a 1. This is the nearest one to I. Let's just say that the jth position is the nearest to the ith position where there is a 1. So whatever is this position, will be taking the among all the possible strings that have a 1 at the jth position, we'll be taking the best out of them, right? And of course this will be 0. So among all the possible j, what we're going to do is, first of all, to our total answer, the sum of these intervals is added. Now let's say my 1 is somewhere here. Okay, if it was here and all these were 0, then my answer was simply going to be the sum of these intervals plus dp of 1, right? Plus sum of intervals that end at I or that cover I. Sum of intervals that cover I. Okay, but consider the next case. Let's say even here I could have simply taken dp of 2 and added to all this, and these are all such strings in which these two are 0 and this is a 1, and I'm taking dp of 2, so the best possible strings among the strings which have a 1 at the second position. But now consider this. If I were to take this to be a 1, then what would happen is that among all the possible strings that have a 1 at the third position, that will be dp of 3. However, I'll be considering this one interval twice, isn't it? So I have to take care that I do not consider this again. So instead of dp of I becoming sum of these intervals plus dp of 3, it will become sum of these intervals plus dp of 3 minus this common interval, right? So hopefully this makes sense. And of course, if my 1 was here, the nearest one to I, if it was here, then my dp of I would have been the sum of these three intervals plus dp of j minus the sum of these two intervals, because these are counted twice. Okay, so now I'll be writing a recurrence, and I'll expect you guys to try and understand why it is correct. Think about it for a few minutes and you'll be able to understand why it is correct. Here it is. dp of I equals to, I'm writing 1 at the ith position, and my nearest one could be at some jth position, right? So dp of I is equals to dp of j plus sum of those intervals, sum of intervals that start after j, and end after I, that start after j and end after I, among and for all j less than I, and we'll choose the maximum out of all these options. Okay, so I'll just prove it to you very quickly, and then we'll discuss the time complexity of the solution. So this is doing nothing but trying to put a 1 at the ith position, and now thinking that the nearest one could be here, it could be here, it could be here, or there might be no one at all. In that case, it is nothing but sum of the intervals that cover the ith position. So I'll have to put that as a case as well. We'll see how we can do it, but that will be easy to manage. Okay, now let's say that the nearest j to the ith position is here. Now take the sum of all the intervals that start after j. So any interval that was starting at this position and ending anywhere after this, and end after or on I. So end after or at because these are precisely those intervals that the jth score does not include. So dp of j do not include these intervals. However, the ith position are covered by these intervals. So for now, when I'm taking j to be I minus 1, only those intervals are considered that start at the ith position and end somewhere after. So in short, those intervals that cover the ith position but not the jth position. In short, take the sum of all the intervals that cover the ith position but do not cover the jth position and add to that total dp of j, and then that becomes dp of I, and for every j you do this thing, and whichever is the maximum possible, that is your dp of I. So now that we have found a recurrence, let's see how we can evaluate in the most optimized manner. Okay, so dp of I was simply among all the possible j, max over all j, for all j less than I, dp of j plus all those intervals, sum of scores of all those intervals which cover the ith point position but do not cover the jth position. So sum of intervals that cover I but do not cover j, but not j. Okay, so we know that for among all the possible j, our answer will simply be the maximum out of all these, or it will simply be the sum of those intervals that cover I. In the case my string is 0 0 0 0 1. Okay, at the ith position. So now I know what dp of I is. Let's see how we can actually evaluate this thing. So let's say that the sum of the intervals that cover I can easily be calculated, isn't it? That will be quite easy. Now let's say I start my j somewhere maybe from I minus 1. Okay, now in this case only those intervals have to be considered that covered the ith position but started from j plus 1, or basically started from the ith position itself. So I will only include those intervals initially which started at the ith position and covered the ith position. Next, my j will decrease to I minus 2 since I have to consider all the possible j which are less than I. Now I will also consider those intervals which cover the ith position but may also start at the I minus 1th position, right? And same way I'll keep on decrementing j one by one, and if there is any interval starting at the j plus 1th position, that covers the ith position, the sum its score has to be taken into the sum. All right, and at the end, among all the possibilities, my dp of I will be the highest score possible. Cool. So that's it, and you can see that it is quite possible to basically implement this idea and recurrence in a time complexity of big O of n square, because for every I have to look at every j that is less than I. So my time complexity will simply be big O of n square, and this thing will time out. So this is the brute force DP solution that we were talking about. In the next video, we'll discuss how we can optimize this thing further, and we'll try to reduce this complexity down to n log n. Okay. So thanks for watching the video. Hopefully this solution was clear to you, and keep following the next part for the complete optimized solution and the implementation. Thank you. Bye. Hi guys, my name is Karthik Arora, and welcome back to the part 2 of the video. In this part, we'll be optimizing the solution which we discussed in the previous video. Okay. So if you haven't watched the previous video, I definitely recommend you guys to first watch that and then come back. Okay, so as we discussed that dp of I is equals to dp of j plus sum of scores of intervals open at ith position but not at jth position, and we'll choose the maximum of this quantity over all j less than I, right? This was what we discussed in the previous video. The other way to put this would be that, okay, I could simply take dp of I to calculate dp of I would take any j position and then take dp of j plus sum of scores of all the intervals that cover the ith position, and then I'll subtract the common intervals that cover both I and j. That is one thing. But as you can see that the major problem we are facing here is that there might be some intervals which were common to both I and j, and therefore their scores will be added twice if we take the sum of scores of all the intervals over I and take dp of j. Okay, so this is the major problem that we are facing, that there will be some intervals that are common to both j and I. Okay, now here is the tricky part. Okay. So what we'll try to do is, instead of evaluating dp of I exactly now itself, we'll evaluate lazily. Okay, we'll evaluate slowly. So let's see what this means. Okay, so imagine if I was calculating dp of I and dp of j did not contain any interval which is still open. So while I'm trying to calculate dp of I want to reuse the results of previous states, right? Like dp of j. Now imagine that dp of j does not contain the score for any interval which is still open at the ith position. If that was the case, it would be much easier for me to evaluate dp of I, isn't it? Because in that case, it will be straightforward for me that I can take all the intervals that are over I and then use the dp of j value directly and add these two things, because I'm putting the constraint that j does not contain the score of any interval which is still open even at the ith position, right? And that helps me evaluate dp of I in a much easier manner. However, once dp of I is correctly calculated, when I am going towards the right and thinking about some dp of k with k greater than I, then I'll face the same problem at k, that I and k might contain the same intervals. So let's see what we can do to avoid this problem. So for any dp of I, instead of calculating it directly, the exact answer at dp of I, we will calculate it slowly. Okay, let me explain you what I mean by that. We're going to calculate it lazy, and we are going to update dp of I one by one. So when I am calculating dp of I, instead of calculating all the scores of all the intervals that cover I take only those intervals that end at or before I. Okay, so an interval like this is not included in dp of I currently. Okay, we'll update it later when it is needed. Currently I'm going to ignore such intervals and only going to think about intervals which have ended before I or are going to end at I. Okay, and we're going to, for the time being, ignore any interval that covers I but is yet still open. By doing this, this is going to help us avoid the problem of taking the same interval twice. So let's say if we had calculated up till dp of I minus 1 and we are about to calculate dp of I. Let's say there was some interval that opened at somewhere here and is still open. Okay, so according to our previous recurrence, what we'll be doing is that we'll be taking the sum of the score, and again if I take this value, I'll have to remove this interval from this guy. Only then will my dp of I will be correct. But now my dp of I will consist of only those intervals which either end before I or exactly at I. So I'm going to ignore this for the time being. Now how this helps me is, if there was some interval that started somewhere and let's say ends at I. So since this interval is still open, this means that these guys do not contain the score of this particular interval. And I could directly use these dp of j's. But the question will arise that, okay, let's say we are doing it in this manner that when I'm calculating dp of I, I'm not considering these type of intervals which cover I but are still open even at I. So I am not considering them, but then of course it is going to affect my actual value of dp of I because the score is not included. So what we do is we update the scores later on. We'll do a lazy update for this. Instead of updating it right now itself, what I'll do is when I reach the end of this interval, I'm going to add the score of this to all the dp of li to ri. Say, let's say this guy started at li and ends at ri. So when I reach the rith index, at that time I will update this score to all the indices from li to ri. Okay, and once all the intervals are closed which covered I, at that instant my dp of I will become the actual value it has to be. Okay, so I'll be uh, explaining this in more detail now, but the idea is this only. Okay, so let's say you're evaluating dp of I. Now since we're only considering at this instant, instant we're only considering those intervals which either end before I or end at I. Okay, so any index behind this guy, any j less than I, follows the same property. So if any interval is still open, dp of j does not contain the score for that interval even if that interval does cover j. So if there was, let's say I'm thinking about this guy j, and there was some interval that is like this, even if this guy covers this jth position, dp of j does not include this, not yet. It will include this later on once I reach the end of this guy, but till then it does not exist for jth position. So what I can do is dp of j only consists of those people currently which have ended at I minus 1 or before it. Okay, so I could simply take the maximum of these guys, whichever is the highest among these people, and that becomes dp of I. Okay, that becomes dp of I, and after that any interval that closes at the at the ith position, I will do a update of that of the score of that interval. So if there was an interval that started at some index maybe li and ends at I, once I'm done calculating dp of I without assuming this interval is not present, I get dp of I simply by taking the maximum among these people, and once that is done, I have reached the ith instant, and now this guy is going to close. So if now when this is going to close, I simply add the score of this interval. Let's say the score is small s, I simply add s to everywhere from li to I. Okay, and by this my values of the dp array become consistent. And also the advantage of this is that if the jth position was going to include this guy, but because of the lazy property it did not contain this guy when I was calculating dp of I. It only got the value or the score of this interval once the interval got closed. So my actual values of dp of I will be built only at the nth instant. Okay, only at the nth instant of time once all the intervals have been closed. Before that these will be consistent only up till a particular instant. Alright guys, so hopefully this idea is clear to you. Now let's see how this particular idea helps us to optimize our solution. So we saw that while calculating dp of I, we were at the I minus 1th instant, and these values only contained these dp of 1 to up to I minus 1 only contained, just a second, only contained the scores assuming that the intervals which are present are closed at the I minus 1th instant. Okay, so there was no problem of overlapping or anything, and we could simply choose the maximum among these for my dp of I, right? And then I check whichever intervals closes at the ith instant, I add its score to all the other positions before I from li to I. So this kind of updating from li to I, adding a score si or s, is again big O of n, unless I use a data structure to fast make this process more efficient. And what we can do is we can use a segment tree with lazy propagation, and we can add this score to the given range, right? And once that is done, all the dp values will have this score added to them now, and with at every instant our answer gets more consistent. At the end, at the nth instant, all the dp values will be what they are supposed to be. Okay, and to get the maximum among all the indices from 1 to I minus 1, we can call a maximum query to the segment tree, and it will return me the maximum value among the first I minus 1 people. And this lazy update in segment tree is again log n. The range update is log n if I use lazy propagation, and the query is also log n. So overall these queries will be log n, and there are n instants or n length string, so my solution will be n log n. Okay, so hopefully the idea is clear to you, and we can look at a small sample input how the idea works, and then we'll move to the implementation. So if anything is in the algorithm is still unclear to you, you can try understanding how it works on the sample input. Okay, I'll just explain the sample input 5 how the thing is working out, and then it should be clear to you, and we'll move to the implementation. So it says that there are we have to generate a 6 length string. Okay, and there are intervals. One is from 5 to 5, then 1 to 1, 1 to 6, 3 to 6, 3 to 4. All right, so there is an interval that starts at 5 and ends at 5 and has the score plus 5. Okay, again from 1 to 1 starts at 1, ends at 1 and 10. Then from 1 to 6 minus 8. Okay, there's an interval that starts at 1, ends at 6, and score is minus 8. And we have 3, 6, 5, kind of a big sample input, I would say. So again from 3 to 4 we have 9, 5 to 5 we have minus 2. Alright, then 1 to 3 we have minus 6, and finally from 4 to 6 We have -7. Alright, let's see how the algorithm works on this. So first of all, we'll be calculating what dp of 1 is. Dp of 1 will initially be 0, and right at the 0th instant there is all the intervals are still open, so dp of 1 begins with a 0. Let's say dp and 1 2 3 4 5 and 6. So initially it was 0 at instant 0, but again at the instant 1 there is an interval ending here, and we update all the values from this intervals li to ri, which is from 1 to 1, and dp at 1 becomes 10. Okay, now we move on to 2. Now at the instant number 1 I choose the maximum among the first one I minus 1 people, that is the first guy. So this guy becomes 10. There is no interval ending at 2, so no updates need to be done till now. Now dp of 3. Okay, so dp of 3 will simply be, yeah, the maximum of the first two guys, that is 10, and now there is an interval ending at the third position with a score -6. So I'll be updating all the values from this guy's li to this guy's ri, that is from 1 to 3. So add a -6 to all the 3 people, and my people become 4 4 4 and 4, right? Okay, now we reach the fourth index, right? Here I'll choose the best out of the first 3 people, that is 4. Now there's an interval ending at the fourth instant or the fourth position, so add a 9 to all the people from third to fourth index. Okay, so plus 9 and plus 9, this becomes 13 and 13, right? Again, now I move to the fifth person, choose the best out of among the first 4, that is 13. Now there is an interval ending at this position, and the score for that is +5. So update from this guy's li to this guy's ri, that is from 5 to 5, and this index becomes 18. All right, let me just check if there is any other interval ending here. Okay, there's another interval ending here, that is -2, right? So also do a update for this interval as well, and this becomes 16. Okay, now I move to this instant. First of all, I'll choose the maximum among the first 5, that is 16. Now I see the intervals that end here. There are 3 intervals ending at the sixth instant, and first of all let's update -8. So updating -8 means doing a -8 operation to all of these people, right? Then doing -2 to these 3 guys. Oh sorry, -7 to these 3 guys. So -7 -7 -7, and then finally a +5 from to the indices 3 4 5 and 6. So +5 +5 +5, I guess 3 4 5 and 6, right? Yep. So after all these updates my values become -4, and again -4, then 13 plus 5 is 18, and -8 is 10. Again here 13 plus 5 18, 7, 10 -7 becomes 3. Here also 21 minus 15 is 6, and here it is 16 21 20, again 6, right? And our answer is going to be 10 for a string which has the rightmost one at the third index, and some other ones here if at all. Okay, so this is the answer must be 10. Let me just check what the actual answer is. So the answer is in fact 10, and the rightmost one in the string is at the third position. So guys, hopefully the algorithm is now very much clear to you, and we'll be implementing it now. Here I've written a segment tree library to save time. I've already written it, so I'll simply explain what it does. This is the tree to hold all the values at a particular node. This UPD is the lazy updates, and initially I call sec3 to build a sec3 over a array of size n and initialize all these values to 0. Okay, then this is a push function. This basically pushes the updates from the updates from a node to its children. So if this node had an update plus 10 which was not yet applied to its children, it will simply push it to the children, right? That's it. This function push does that. And again we have this update function, the main function here. I'll give the update function a range from li to ri to add a value val to it, and it will simply add it in log n time. This function is the lazy prop function that does the actual range updates. Then we have the query function. I'll give this function a range li to ri and it will return me the maximum possible value in this range, and that's all about the segment tree. Guys, if you are unaware of how lazy propagation works or how segment tree works, I definitely recommend you to go and look up how it works. Here I've declared a structure called interval to hold the intervals, score where the interval starts and where the interval ends. And here is our solve function which we'll be implementing. Here I've simply taken the input and I've called the solve function. Alright, now we'll be implementing the actual solve function. So first of all, let's build our segment tree. So our segment tree is going to represent the DP array. So let's say I have a seg3 DP and the size will be n, right? Yep. So the size is going to be n. Initially all the values are initialized to 0 and at every instant we'll keep updating DP to the correct values. Now first of all what happens is, okay, when do we do the updates? We do the updates whenever some interval ends. So I'd also like to know what all intervals are ending at the ith instant. So let's first of all pre-process that to know which intervals end at the ith position. Okay, so let's say I build this array, integer endings. So which all intervals end at some particular instant or some particular position I, and there could be many ending here. So vector int, I'm simply going to process the intervals. So for integer I from 0, I less than v dot size, and I'll check what this the closing point for this interval is. Whatever it is, endings at that guy is +1. So endings at, what is the ending of this particular interval I'm looking at? That will be v at I dot close. So where does this interval close? Dot pushback the index of this interval, right? So I know that the ith interval closes at ends where I've added the index. That's it. So once this is done, I know the endings. So endings of 1 represents all the intervals that end at the first instant or first position. Now what I'm going to do is, for integer I goes from 0 to n, or maybe from 1 to n, and I'll just update all the intervals ending at the 0th position. So what I'm going to do is endings at 0 for all the people inside endings at 0, for integer I belonging to endings at 0, do the updates because we have reached the instant 0. So we're going to update I know that we are talking about v at I, right? And the update that should be made is v at I dot score, and it should be made to the range it should be made to the range vi.open to vi.close. That's all right. And I'll call dp.update. That's it. So it will update all the range, all the intervals and their scores in the dp array. Cool. So once that is done, now what I'm going to do is dp of I becomes to evaluate dp of I, first of all do a range update from I to I, and that will be the maximum among the first I minus 1 people. So let's get the max among first I people. dp dot query, and the largest among the range from 0 to I minus 1, whichever is the largest. Let me just check the, yep, yeah, right. So dp dot query 0 to I minus 1, the largest guy, and dp dot update, so from I to I add this guy. Now for all the intervals ending here, for all intervals that end at this particular ith instant, update these values as well. So dp.update vi.open, and here this should be some other index, maybe j. All right, so once that is done, after this loop my answer will simply be the largest among all the dpi's. So I can return dp.query 0 to n minus 1, and that should solve the problem. Let me just take a sample input. So the answer should be 10 for this case. Okay, we are getting an incorrect output. Okay, so I am guessing that the algorithm is correct. Okay, I think the intervals are 1 based. Yep, they are 1 based, whereas we have considered our range from 0 to n minus 1. So what I need to do is I need to make the intervals also 1 based. That will solve the problem, I guess. I'm gonna do vi.open minus minus and vi.close minus minus. Now they are 1 based as well, so I'll just check the answer now. Oh sorry, they are also 0 based now. Yep, now we're getting the correct output. Just to be sure, I'll check sample input 2 as well. Alright, we're getting the correct outputs. Let me just submit and we'll talk about the time and space complexities. Alright, there is some error. Let me just check the results. Okay, it's failing on a pretest, in fact. Otherwise it's passing most of them. It's failing on a pretest, so it should be easy to debug, and I'll quickly check it out. It's failing on the third guy, right? So this is the, okay, all right. So we have missed the part where the string may be entirely 0. The string might entirely consist of zeros, and also we have made the part where this is a possible string, right, where you set a 1 at the ith position and the before it all were zeros, right? So we have missed these two things. I'll quickly add them. Okay, so first of all, return max of answer will be at least 0, right? So 0 ll or that, because I can always achieve 0 by setting the entire string to be 0. And here also large equal to max of 0 or this. So I guess now this should properly work. Yeah, we're getting 0. I'll submit it again. Now it should work. Yeah, so it will work now. Alright, so let's just discuss the time and space complexities. First of all, for the segment tree we are using big O of n memory. You can see here 4 into n, so it's almost 4 into n, so it's big O of n memory only. And again, these update queries run, the updating and the queries in the segment tree run in log n time, and we'll be performing m of these updates. These updates will be performed m times, given that there are m updates, m intervals. There are m updates, so m log n for that. M is going to be m log n for that, as the tree size is n, so m log n, that's why. And overall this loop runs n times, so it's going to be n plus m log n, big O of n plus m log n, and it passes the given time limit. All right, so as you can see, we have got an AC. So guys, thanks for watching. Hopefully the video was helpful to you, and I'll see you in the next video. Hi everyone, in this video we'll be solving the problem X tower. Okay, so you can go through the problem statement once. Here we are given with n boxes or n blocks, and each block has 3 attributes. Okay, so each box has 3 attributes. One is the weight, other is the strength or the solidness of this box. So this is the ith box, and every box has a weight, it has some solidness or some strength, and it has some value vi. Okay, and we are given with n such blocks or boxes, and we would like to make a tower. Okay, we would like to build a tower out of these boxes, such that the tower, the value in the tower, the value of the boxes, the sum of the values of the boxes used to make that tower is maximum among all the possible different towers, but each tower must follow a constraint. Okay, so if you build a tower, then for each block in the tower, the sum of the weights of the blocks stacked above it should not be greater than the solidness of this ith block. So imagine if you build a tower, then in this tower, this block has to withstand a weight of the sum of these boxes. Basically the sum of the weights of these 3 boxes needs to be withstood by this single box. So he needs to withstand all this weight. So the solidness of this box should be greater than equal to the sum of their weights. Same way for this box, the solidness of this second box must be greater than the weight of this fourth and third box, the sum of the weights greater than equal to. Alright, otherwise the tower breaks down and it is not a valid tower. So following this constraint, we must find out what is the maximum possible value or the sum of the values of the blocks out of which we can make a valid tower. So hopefully the problem statement is clear to you. We'll be going through a sample input, and if there is any doubt, it will be cleared away. Yeah. So you can look at the constraints. N is up to 10 cube 1000, and the weights and the solidness values are up to 10 to the power 4. Was not greater than SI, right? And the values of any particular box can be up to 10 to the power 9, and we have n such boxes in input. Already, you can look at the sample input 1. We have 3 boxes and we have weight 2, solidness 2 and value 20. Then we have 2, 130, 3, 1 and 40. So one of the valid boxes they say is firstly stack the box 2 and then the box number 1. So stack number 2 has a weight 130. Let me just check its weight, then the solidness and then the value. Okay, so blocks 2, 1 are stacked in this order from top to bottom. Okay, that means the lower stack is box number 1. So it's 2, 220 and 2, 130, and you can see that this block can withstand the weight 2 because it has a solidness 2, and therefore we get a value, overall value 50. 30 plus 20. This is valid because the lower box was able to withstand the weight of the upper box. Otherwise, if we would have taken the same boxes but in the other manner, that is box number 2 is below box number 1, then this would not be a valid tower because the lower box will not be able to withstand the weight of the upper box, given that the solidness is less than the weight of the upper box. So this is the best possible way to build a tower and get the score of 50, the maximum possibility. Here you can see 3, 140, but you cannot use it in combination with any other box because first of all it has a solidness level of 1, so it cannot basically hold any of the other two boxes because their weights are 2. So if this is used as the bottom box, then this breaks. Otherwise, if this is used as the upper box, even then it breaks the lower boxes because the maximum solidness for any other box is 2, and no box can hold a box which has a weight 3. So this box cannot be used. It could have been used alone, and in that case it would have given me a score of 40, which is not optimal. 50 is the optimal. Alright, so you can go through sample input 2 as well. Okay, in this example they're saying box 1, 2, 3, 4 should be stacked in this order from top to bottom. So first of all they're saying put box 1 at top, box 2, box 3 and box 4, and let's see why this is valid and the tower should not be breaking. So fourth box should be able to hold a weight. The weight of these boxes is, the sum of weight of these boxes is simply 1 plus 3 plus 2, which is 6. So the fourth box should have a solidness greater than equal to 6, and yes, it has, so it can withstand this weight. Then box number 3 should be able to hold a weight of 4, so it should have a solidness greater than equal to 4, and it has a solidness 4, so it does not break. The box number 2 should have at least a solidness of 1, and it has that, so it does not break. And this is a valid way, and we get the value 10 plus 10 plus 10, which is 40. So guys, if you'd like, you can go through these other sample inputs as well. And now we'll be moving towards the solution. Okay, so first of all I'll be discussing a very brute force naive solution, and this should hopefully come to anyone's mind. So the actual tower that we are going to build, the best possible tower that gives me the highest score and is valid, consists of a subset of the n blocks, right? So let's say that my actual optimal tower consists of the subset S of blocks. So S is a subset of n. My tower consists of the blocks that are in the subset S. Okay, and my tower, there is some orderings, and one of the boxes will be used at the bottom, and then this way onwards up to the topmost box. So these are the blocks that I've chosen in my subset S, and there will be some ordering. So what I can do is I could choose a subset S and I could try out every possible ordering of these boxes. So if S has a size maybe small x, then there are x factorial possible orderings, right? Because if let's say S equals to S1, some B1, B2 and some BK, these are K boxes, and all these boxes are subset of this n boxes. Then at the bottom I could place any box, maybe B1, then B2 and up to BK, or I could have some other order of these K boxes. So this is going to be K factorial different possibilities to build a tower out of this single subset, right? K factorial. And then if I am able to build any valid tower out of this subset, then my answer is at least the sum of the values of these boxes. Okay. Now this is a very naive brute force solution, and pessimistically my time complexity will reduce down to 2 to the power n if I try out every subset, and for every subset I have to try out every possible ordering to build the tower. And let's just say in the worst possible case it's 2 to the power into n factorial. It might be a little better, but let's just say it's in the worst case 2 to the power n into n factorial. Of course this is a really poor slow solution, and we have n up to 1000, so this does not work. However, we do have a solution now. So this naive brute force solution simply tells us to take each and every subset, and then for every subset try out all the possible orderings of the blocks in that subset, and if you're able to build a tower out of any of those permutations of the blocks belonging to that subset, then your answer is at least the sum of the values of the boxes in that subset. And you can try out every possible subset, and for every possible subset you can try out every ordering to build the tower, and that's it. This is our solution, but this is slow. Let's try to improve this further. Okay, so maybe if I could limit the number of orderings, then my solution might get better, right? Because the n factorial factor was coming due to the number of permutations of the boxes, the number of orderings to build my tower. So if I was able to limit those number of possibilities, I might reach a better solution. So now consider that I select some subset S, and it has some boxes B1, B2 up to BK, right? I have selected some subset, and I'm trying to check if there is a valid tower that consists of all these boxes. Okay, all of these and only these. So basically a valid tower that consists of these K boxes. I'm trying to find that out. We saw that there is a K factorial way to do that and try every order. However, I want to limit the number of orders, the number of correct orders. So consider that two boxes Bi and Bj belong to this subset S. Okay, then I'll try to find out which box should come at a lower height in the tower, and which should come at a higher height. Okay, since all these boxes are supposed to come in the tower, so one has to come closer to the ground and one will be further from the ground, right? One will be at a higher height and one will be at a lower height, and I would like to limit the number of possibilities. So we have these two boxes. Before we do any maths and find out any good conditions, let's think intuitively. Okay, so if the box I has the weight Wi and the strength or solidness Si, similarly for the jth box we have Wj and Sj. Intuitively thinking, which one must come closer to the ground and which should come further away from the ground? One observation here could be, the higher a box is placed in the stack, the more boxes present have to withstand its weight. Okay, so if there are 10 boxes under this particular box, then all these 10 boxes must be able to withstand the weight of this guy, right? It exerts a weight on all the boxes under it. So intuitively speaking, it makes sense that a heavier box is closer to the ground, because only then will it be able to exert its weight on least number of boxes. It makes sense, if the weight is more, you place it closer to the ground. Also, consider a box that has a lot of strength or its solidness value is very high. Then intuitively thinking, it makes sense to place it closer to the ground, because then it will be able to withstand the weight of more weight compared to a box that has lower solidity value, right? So if a box has high solidity, then it makes sense to place it lower towards the ground or at a height lower in the stack. Alright, so now let's consider some cases for these boxes. Okay, imagine that the boxes BI and BJ we were talking about having the strengths SI, weight WI, SJ, WJ. Now which one should come at a height lower than the other in the tower? So let's consider the first possibility. Okay, in this possibility, let's say that the strength of the ith box is greater than the weight of the jth box. Okay, so this means that the ith box could hold the jth box on top of it because its strength is greater than its weight. And let's say that also the weight of the ith box is greater than the strength of the jth box. So if you think about this possibility, then definitely the jth box can never come under the ith box. Reason being, it will not be able to withstand its weight. If I put the jth box below the ith box in the tower, okay, then the jth box will definitely break down because the strength Sj is less than the weight Wi. Therefore, this order is definitely not possible if my Si, Wi, Wj and Sj follow these inequalities basically. So definitely jth box does not come below the ith box, and we are only left with one possibility, that the ith box comes under the jth box if these two conditions are true. Okay, consider the second case, that basically the symmetric reverse case of this, that Si is less than Wj and Wi is less than Sj. In this case, the ith box can never hold on top of it the jth box, and therefore ith box does not come below the jth box, otherwise it breaks down, right? Okay, and in the other case, the jth box can definitely come below the ith box because the weight of the ith box is less than the strength of the jth box. So this is valid here. And the other possibility is impossible basically, because if ith comes below the jth, then the ith box will break due to the weight of the jth box, right? So we have considered two possibilities, and in both of these possibilities there is a certain winner, right? In this possibility, ith box should come closer to the ground, and in this possibility jth box should come closer to the ground, but we're still left with two other possibilities. Consider the third possibility. In this case, the strength of the ith box is less than the weight of the jth box. This means that the ith box cannot come below jth box, that is definite, otherwise the ith box will break. And the other case is that the strength of the jth box is also less than the weight of the ith box. This means that the jth box cannot come below the ith box, otherwise the jth box will break. So in this particular third number case, it is impossible to build a tower using both these boxes at the same time, because one of them has to come below and one of them has to come above, and whichever comes below is going to break. So in this case, it does not matter which box I put closer to the ground, because anyway I will not be able to build a valid tower. Okay, now I'm left with the fourth and the most tricky case. What happens when the strength of the ith box is greater than the weight of the jth box, and the strength of the jth box is greater than the weight of the ith box? Now the ith box can withstand the jth box on top of it, but also the jth box can withstand the ith box on top of it, isn't it? Because of these constraints, Si is greater than Wj, so ith box can hold jth box, and same way jth can also hold the ith box. Now which one should come closer to the ground and which one should come on top? So there are two possibilities. Either I prove that whichever comes below, there is no difference in my answer, or I try both the possibilities, in which case my time complexity still remains poor, And the third case is that I am able to somehow decide which is the better out of the two options. So here is what we will do. So let's imagine that there is a tower in which the ith box is coming before the jth box. Okay. Now I am just thinking whether it would be a good idea to replace these two boxes in the tower, given that all the other boxes remain at their respective positions. Okay, I'm just thinking about the ith and the jth boxes. Alright, then first of all, if ith box is going to come below the jth box, then Si has to be greater than equal to Wj plus some C for these boxes and these boxes, right? So Si has to be greater than equal to Wj plus C, and this is when the ith box should come below the jth box. Okay, and if the jth box was supposed to come below, that means if I swap the condition, then Sj should be at least greater than equal to the weight of the ith box plus some constant C for the other boxes, for the sum of the boxes of other sum of the weights of the other boxes, right? This C. So this gives me that Si minus Wj should be greater than equal to C, and this gives me Sj minus Wi should be greater than equal to C. Okay. Now it makes sense that these values are as large as possible, isn't it? So you can use this equation number 1 and this equation number 2 to deduce which is a better option. The better option will be in which this particular value is greater. Okay. So I'll be combining these equations 1 and 2 into a single equation. And of course it is better to have the LHS as greater than equal to C as possible. So using these 1 and 2, what I get is I should place the ith box below the jth box if Si minus Wj is greater than Sj minus Wi. In that case, I should be keeping the ith box below the jth box. Alright. And using this equation, I'll take Wj to this side and Wi to the left hand side. I get the result Si plus Wi should be greater than Sj plus Wj, and if this is true, then I will keep the ith box below the jth box, and that is how it is. And just like we have derived this mathematically, but also the way we were thinking intuitively, we had thought of that a box should come below if it has a strength greater than the other box and weight greater than the other box, right? So a heavier box should come below intuitively, and a box that has a higher strength should come below. This was our intuition, right? And you can add these two up and you will get the same equation: Si plus Wi greater than Sj plus Wj. So that's it. In a good order, the box that comes below has the sum of strength and weight greater than the sum of the strength and weight of the other box. You can check it for 1 and 2 as well. This holds true. You can add these two here and you will get that Si plus Wi is greater than Sj plus Wj, and therefore ith box was coming under the jth box. In this case, Sj plus Wj was greater than Si plus Wi, and therefore the jth box was coming below the ith box. So with this we have defined an ordering. Okay, we have defined that whenever the sum of the strength and weight of the ith box is greater than the sum of the strength and weight of the jth box, then ith box comes below the jth box, and we have defined this. Now we will see how this thing helps us to optimize our solution further on. So let's say I order these boxes according to their Si plus Wi values, okay, and then I will know the one with the highest Si plus Wi will come the come at the bottom of the tower, right? If it comes in the tower, then it has to go to the bottom, because that is what we just proved. So let's just sort these boxes according to this particular value, and let's say we get this b1 b2 up to bn. We have these n boxes now sorted according to their si plus wi, and if box 1 is included in the optimal tower, then it will be the bottom of the tower. That has been proved, and this is the sorted ordering. And if bn is included in the optimal tower, then bn will be the top of the tower. Alright, now we have this sorted ordering. These values have been sorted according to the sum of the strengths and weights. So this guy has the highest sum of strength plus weight, and this has the lowest. Alright, let's see how this helps us to come up with a solution. Okay, so as we earlier said, we'll be thinking about this every subset, and then we'll be trying to make the best possible tower. So let's think about the first I items. Okay, the first I boxes, and I want to take a subset of these I boxes and build the most optimal tower possible. So there are two possibilities. In this, when I'm taking a subset of these boxes, either bi will be included, alright, in the optimal tower of that is made using the subset of the first I items. Either bi will be included or bi will be excluded, right? Excluded from the subset or included in the subset. So in the case when bi is excluded, my answer will simply be the best possible or the optimal answer for the first I minus 1 boxes, right? So if bi was excluded, my answer is simply the best answer for the first I minus 1 boxes. Alright. If bi is included, bi will be placed at the top, and I will be choosing some optimal tower from the first bi minus 1 boxes. I'll be making some tower out of the subset of the first bi minus 1 boxes, and then first of all, whichever tower I make out of the first I minus 1 boxes or the subset of the first I minus 1 boxes, they should be able to withstand the weight of the ith box, as it is going to be placed on top of them. So I need to find a tower that has the maximum value among all the possible towers of the made out of the subset of the I minus 1 item boxes, and above that we'll be placing the ith box. So the best possible tower that is at least able to withstand a weight wi. So it must be clear that one thing that we would like to know about the subset of some first I items or the first I boxes is that what is the value that I am getting, and also I would like to know what is the weight that this tower can withstand, so that I could further put a box on top of that currently made tower, right? So with these intuition, I will be defining dp of a comma j as the maximum possible value I could get by stacking a subset of the first I boxes. So I take the first a subset of the first I boxes, that is box number 1 till box number I, and I make a tower out of these, and the maximum possible value that I can get by doing that, such that the tower I make can withstand at least a weight j on top of it. Okay, so dp of I comma j is the maximum possible value such that I take a subset of the first I items, subset of first I items, and make a tower and stack the boxes into a tower, stack the boxes such that the tower made can withstand a weight at least equal to j on top of it, and stack the boxes such that tower can withstand a weight at least j on top of it. All right. So with this definition in place, dp of ij, my final answer will simply be dp of n comma 0, and this means that I take a subset of the first n boxes. That is, I take a subset out of all the boxes, and I make a tower out of these boxes using these boxes. What is the maximum possible value that I could get, so that I make a tower which could withstand on top of it a weight of at least 0. Alright. So if I were able to make the recurrence for dp of ij, I'll be able to find out my answer at dp of n comma 0. So you can pause the video, think about the definition that I've given for dpij, and try to build a recurrence on your own. Okay. Now I'll be proceeding towards writing a recurrence, and I'll be erasing this part. So let's try dp of ij. Okay. So in dp of ij, I'm thinking about the first I boxes, right? So I want to take a subset out of the first I boxes. In this subset, the ith box can either be present or it can be absent, right? So I have two possibilities. Either I exclude the ith box, or I include the ith box, right? These are the two these are the two possibilities I have when I'm thinking about the about taking a subset of the first I boxes, right? So of course, if I have two options, I'll be choosing the better of these two options, whichever gives me a higher dpij value. So consider the first option, I exclude the ith box. Okay, so I'm going to choose the better of the two options, and the first option is excluding the ith box, and in that case our value is nothing but dp of I minus 1 comma j. Since the ith box is not being included in our subset, so it's the same as taking a subset of the first I minus 1 values that could withstand a weight of at least j on top of them. That's it, right? This is the first case. And the second possibility is I include the ith box. Okay, in that, if I include the ith box, first of all, I will be adding a value vi, the value of the ith box, to my answer, plus, now since the ith box is being taken, I need to take a tower below the ith box, so that this tower can at least hold the ith box on top of it, right? It should be able to hold the ith box on top of it, and after that it should still, this tower, the final tower I make, this tower should still be able to hold at least j on top of it, right? So this means that this tower that I'm going to take, on which I'm going to keep the ith box, this particular tower should be able to hold at least j plus wi on top of it. Wi for the weight of this ith box which is being placed on the top now. Alright. So my recurrence will become vi plus dp of I minus 1 comma j plus wi. Right. Because the tower that I'm going to take, it has to hold the weight of the current item as well, and after that it should still be capable of withstanding another j weight on top of it. So that is why I'll choose a tower that can withstand at least j plus wi on top of it. Alright, now here there is a small flaw here. The thing is that we would like a tower to withstand at least a weight of j, but it is possible that the ith box itself has a solidity value that is lesser than j. Okay, and if that is the case, then there could never be a possibility in which you include the ith box and then build a tower that is capable of holding a weight greater than equal to j on top of it. Alright, so if this is the case, then our second possibility disappears and we are left with only one possibility. Okay, so guys, this is the recurrence, and option number 1 is always available. Option 2 is available if the solidity of the ith item is at least j. Okay, so guys, hopefully the recurrence is clear to you, and we'll simply be implementing this thing. First of all, before we implement, let's discuss a base case. So what will be dp of 1 comma x? Okay, so I'm taking a subset of the first one items. So basically there is just one item, and it should be capable of withstanding a weight at least x. So let's say that the solidity value of the first item is nothing but s1. Then dp of 1 comma x will simply be the value of the first box whenever x is less than the solidity value, right? Because in fact x is less than equal to the solidity value, because then we are able to at least hold x weight on top of the box, and otherwise it's impossible. So I keep that to be 0 whenever x is greater than the solidity value of the first box, right? Because if I want a tower that can hold a weight of at least maybe 1000, but the solidity value of the first box is 5, then of course it is not possible to build such a tower. So I simply keep a 0 here. Alright, now with these base cases and the recurrence, I'll be implementing the same solution as discussed. Alright, now I'll be erasing it. So guys, here I've simply taken the input and defined a structure box. Here this is used to model our boxes, and SI is the solidity of the box, WI is the weight of the box, val is the value you get by putting this box in the tower. This will be the solve function that will return me the final answer. Here n is the number of boxes, and then I've taken the input as described in the format, weight, solidity and value. Then I'll be calling solve v, and this should return me the answer. Here I've declared this dp array, and there can be at most 1000 boxes. So the I that was there in my dimension describing the first I object, so there could be at most 1000 of these. So this dimension is up to 1000. And the second dimension describing j, the weight a tower should withstand at least j. Okay, and that can be at most 10,000, because the solidity value of any particular box can be at most 10,000, and that is the weight it can withstand on top of it. So that is the second dimension, 10,000. Alright, now we'll simply be implementing the same idea that we have discussed. So first of all, I get the vector of the boxes. Sorry, I need to sort these according to a criteria as discussed. So sort v dot begin comma v dot end, and some comparator to sort these. Let's define the comparator as well. So bool comparator, and I get the two boxes here, box b1 and box b2 maybe. So box b1 should come before box b2 in the sorted order if b1 dot solidity plus b1 dot weight is greater than b2 dot solidity plus b2 dot weight, and that's it. I'll return this thing. Yep, that's right. So I've sorted my boxes according to the criteria we have discussed. Next I'll be writing the base case. So for the base case, for some integer j, the capacity, basically the minimum weight that this tower should withstand on top of it, j goes from 0 up to 10,000 maybe. Right, and if the solidity value of the first box, if vi dot si is greater than, or let's say even equal to, the j, the value we want on top to keep on top of this box, then our dp of ij or dp of 0j will simply become the value of the first box, that is vi dot val, else it's not possible to hold so much weight on top of this box, so dp of 0j becomes 0, and that's it. Next, what I'll be doing is I'll be calculating dpij for all possible I and j starting from 1 up to n. So taking the first I items, a subset of the first I items, such that I make a tower which can withstand a weight j on top of it. J goes anywhere from 0 to 10,000. Okay, and here we had two options. Okay, LLOP1 was, the first option is that I exclude the ith box, and in that case my answer is nothing but dp of I minus 1 comma j, and the second option was to include it, right? So LLOP2, and I could only include this box if it could at least withstand j on top of it, so its strength must be greater than equal to j. So let's say if vi is greater than vi dot si, the solidity of this box is greater than equal to j, the weight I want on top of it, then I could have some possible answer. Otherwise option 2 is not even there, so I put a 0. Okay, cool. Now if this option is present for this box, then what I will do is I will do op2 equals to, I will take the value of this box because I'm taking it, plus, because I'm taking the box in my subset, so I'm keeping it on the top of the tower, so I'm getting the value of this box. So vi dot val plus, I need a tower out of the first I minus 1 boxes, a subset of the first I minus 1 boxes, such that they can hold a weight at least j plus vi dot wi, right? And this will be my option 2. However, there is one thing to consider. This j plus vi dot wi may be greater than 10,000, in which case I get a segmentation fault. So let's just make sure, if this is greater than 10,000, then of course there is no possible tower, and I'll simply take a value 0, right? So if j plus vi dot wi is greater than 10,000, okay, so if that is the case, if it is greater than 10,000, then there exists no previous tower that could basically have that much weight capacity on top of it, so I take a 0 instead, and otherwise I take the value which we discussed, that is dp of I minus 1 comma j plus vi dot weight. So hopefully this thing should be clear to you. And finally, out of these two options, I'll be choosing the better one, max of op1 comma op2, and I'll be storing that in dp of ij. Finally, after all this, I should have my answer at dp of n minus 1 and 0. So guys, hopefully this code is clear to you and it should work as well. I'll try it on a sample input. Okay, I was not declared in the scope. Yeah, this has to be 0. I'm thinking about the 0th item. Anything else? 39. Okay, n was not declared. All right, anything else? No, that's it. Error, I was 36. Yeah, this has to be 0. Alright, we're getting the correct output. I'll check for sample input 4. We should get 22. Yep. Alright, I'll be submitting it now and then we'll discuss the time and space complexities. So it's getting AC now, and first of all, the space complexity is simply n into the maximum solidity or comma weight of any box. So space complexity is n into maximum solidity of any box, and maximum solidity according to the problem statement was up to 10,000. So this is 1000 into 10,000, and as we saw, the transition time everywhere is simply big O of 1. So our overall complexity is proportional to 10 to the power 7 operations, and that is very much doable in the time limit. Also, there was a sorting, so that sorting was n log n, but n is only up to 1000, so the sorting is very fast, and our limiting factor is this thing, 1000 into 10,000, that is 10 to the power 7 operations. So guys, hopefully the video was helpful to you, and I'll see you in the next video. Thanks for watching. Hi everyone, in this video we'll be solving the problem by grade 2, and this is simply a harder version of grade 1. Okay, so grade 2 is almost the same question as grade 1, except that in grade 1 we had a grid of size h cross w, and so h rows and w columns. So we had a grid of size h and w, and there were some obstacles here, and there could be any number of obstacles, and h and w were limited up to 3000. Whereas in this problem, grid 2, h and w can be up to 10 to the power 5, but the number of obstacles are limited. So at most there will be 3000 obstacles in the grid, and what we would like to do is we would like to find out the number of paths starting from 1 comma 1 up to n comma m, h comma w modulo 10 to the power 9 plus 7, and that is the problem statement. So first of all, I'll discuss the solution to grade 1 once again. So there we used a very simple approach. We said the number of paths starting from I comma j up to h comma w equals to dp of ij, and the transition was very basic. Either I go down or I go to the right. Either I go to the right down cell or I go to the right cell, and that was it. However, why this solution will not work for this problem is because the constraints are up to 10 to the power 5 and our solution is big O of n square. So we will not be able to do 10 to the power 10 operations within 2-second time limit, and that is why this solution will fail for grade 2. Otherwise this solution is perfectly alright. The only reason we cannot use this solution is due to the constraints. Okay, so I'll just quickly go through the sample input. Here you can see the sample input 1. We have 3 rows and 4 columns. There are 2 obstacles, and the obstacles are at 2 comma 2 and 1 comma 4, and then you can see the 3 possible paths, right? Again, for sample input 2, we have a 5 cross 2 grid, and there are 2 obstacles in the grid, 2 comma 1 and 4 comma 2. I'll just draw how it looks. There are 5 rows and 2 columns. 1 2 3 4 and 5, and one of the obstacle is at 2 comma 1 and the other obstacle is at 4 comma 2. 1 2 3 4 and here. So no matter what path you take, you cannot basically reach the endpoint, because I am only allowed to move either to the right or to the down. So it's impossible for me to reach here, because if I take this path, which I'm forced to, I cannot take a left here, so that is why I'm blocked. I cannot go down here because there is an obstacle, and therefore the answer is 0. Alright, so guys, if you'd like, you can go through sample input 3 or 4 as well. However, I'll be moving to the solution now. Okay, so we're solving Y grid 2. Okay, so before actually solving the problem, the actual problem, let's solve an easier version of the same problem. So the easier version is simply that the number of obstacles is always 0. Okay, so easier version of the same problem is that n equals to 0. N was the number of obstacles. Now I would ask you to pause the video and try to think of a solution. No obstacle. Okay, you can pause the video and try on your own, then I'll help you out if you're unable to. So we need to find the answer for this easier version, given that there is no obstacle in the grid and I'm given a grid of size h cross w. So for example, here I have a grid of 1 2 3 4 and 5 cross 5, right? Let me take some other dimension instead. So now I have a grid of 1 2 3 4 5 cross 1 2 3. Okay, now I have a grid of 5 cross 7. There is no obstacle. I just want to find out the number of ways starting from this guy ending at this guy. Of course we have the previous solution, but I want a much faster solution than that. Okay, we don't want that dpijn squared solution, we want a faster solution. Okay, so to find out the number of ways that start at 1 comma 1 and end at 5 comma 7, given that there is no obstacle in the grid at all, what I can do is, there's an observation to make here. So overall in any of my path, I'll be taking a total of 4 plus 6 moves, isn't it? I'll be taking a total 10 moves, which is the Manhattan distance between these two blocks, isn't it? So no matter what my path is, I'll be moving 10 moves. 1 move, 2 move, 3, 4, 5, 6, 7, 8, 9 and 10. So no matter what path I take, you can be assured that you'll be making exactly 10 moves. So observation 1 for this easier version of the problem is that total moves will always be, total moves is equals to n minus 1, or if the grid size is h cross w, then h minus 1 plus w minus 1. And this is because I'll be making h minus 1 moves in the downward direction and w minus 1 moves in the rightward direction. Any valid path has to make these number of moves, isn't it? Now the total number of paths using this observation, so we have the total moves, we have number of down moves, and we have the number of right moves. So number of down moves equals to h minus 1. Same way number of right moves equals to w minus 1. So any valid path has to do these number of down moves and right moves. So basically my valid path is a sequence of 10 moves, or basically h minus 1 plus w minus 1. Let's just consider our 5 cross 7 grid. Okay, I'm just considering this example for now. So any of my valid path will be a sequence of 10 moves, isn't it? Out of which 4 of these moves will be downward moves and the remaining 6 moves will be rightward moves. So basically any valid path is choosing when do I go down and the other times I go right. So I could choose to go down here, down, 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 and of course the remaining are rightward moves. Or I could have chosen some other sequence for the path. I could choose these 4 downward moves. So basically I have 10 places to choose from and I would like to choose 4 of them to be my downward moves. Remaining moves automatically become the rightward moves. So the number of valid paths is basically choosing 4 positions out of the available 10 positions for my downward moves. This is nothing but n choose k or 10 choose 4. So my answer is not going to be nothing but 10c4. That this is the binomial coefficient. So the number of valid moves to my problem will be 10c4, or to the general problem it will be total moves h plus w minus 2 c h minus 1, and this will be the answer to the easier problem. So just to be sure you guys are following me, I'll just repeat this thing. And basically I had h plus w minus 2 empty moves to make, and out of these I wanted to select h minus 1 of these moves to be the downward move. So I want to fill these dashes with downward moves and I want to select h minus 1 of these dashes, and choosing some number of objects out of a given number of objects. Basically choosing r objects out of n objects is nothing but ncr, and here I wanted to choose h minus 1 dashes to be my down moves among out of the h plus w minus 2 total dashes. So my solution to the problem became this. It could have also been that instead of downward moves I would have selected the rightward moves, and in that case my solution will be h plus w minus 2 c w minus 1, and you can verify these two are the same thing. These two values will be equal. Okay, so you can write any of these to be your solution. So we have a solution to the easier problem. Now let's move forward to the actual problem. Okay, now so imagine that you have this grid of, of h cross w dimensions, and now you definitely know if there is no obstacle, the number of ways is very easy to find out. We just proved, we found the relation, so that is easy to find out now if there is no obstacle. However, imagine, let's say there is just one obstacle here. Then what is the number of ways to reach from 1 comma 1 to n comma h comma w? So if this obstacle was not here, I knew the number of ways to reach from this to this, and let's just say it is nothing but w. So there were w moves if this obstacle were not be there. Now if this obstacle is there, I would like to find out the number of ways now. Okay, so all the paths that go through this obstacle and then reach h comma w, these paths should be excluded out of the actual answer, right? So if there is any path that will cross this guy, that is not a valid path because we are being blocked by the obstacle. So what I can think of is, among these w moves I should be removing the moves that go through this particular obstacle minus moves that go through, let's say this is 3 comma 2, right? So 3 comma 2, or wherever the obstacle is, if there is just one obstacle. So w minus the moves that go through 3 comma 2. Now what is the number of moves that go through 3 comma 2? For that I would like to find out the number of paths that start from 1 comma 1 and reach 3 comma 2. Once I know the number of paths from here to here, what I could do is I could also find out the number of paths that start from here and end here. Okay, Then overall, if I were to find these paths, say x1, and then these paths, the number of paths starting from 1 comma 1 and reaching this obstacle, and then the number of paths that start from this obstacle cell and end at this n comma m or h comma w, then I will be able to multiply these two together, and this will be the overall paths that go through this obstacle. Again, finding the number of paths that reach from 1 comma 1 to this is simple. We'll use our binomial coefficient relationship, and again for this as well we'll use our binomial coefficient relationship. So overall I'll be having w minus x1 y1, and x1 is the number of paths from 1 comma 1 to the obstacle, and y1 is the number of paths from the obstacle to h comma w. So again, if there was just one obstacle in the grid, then also I can find out my answer very easily. X1 and Y1 can be found out using the same relationship which we used to find out W. Alright. However, now let's think that, let's say that there is not just one obstacle but more. Let's say there are two obstacles now. What happens now? So what happens now, I could think of is that, alright, I could use a similar idea. W minus x1 y1 and minus x2 y2. Here x2 y2 is simply the number of paths that start at 1 comma 1 reach this obstacle, the second obstacle, and the number of paths that start at this obstacle and reach h comma w. However, there is a flaw in this thing. I could not simply say this. Okay, why is that so? Because x2, this x2 also includes those paths that first reach this obstacle and then reach this obstacle. However, it should not be including these paths, isn't it? Because if I do include these paths, then I'll be counting the same path twice and removing same paths twice from W, isn't it? Let's imagine when, so maybe when I counted x1 y1, I would have counted this path. Yeah, I would have definitely counted this path and removed it from W. But when I do x2 y2, I count this path again, right? Because this is also a way to reach the second obstacle from 1 comma 1, and this particular path and many other paths that basically first reach obstacle 1 and then reach obstacle 2 are being counted again. I do not want this to happen. I want only to count those paths that do not go through obstacle 1 but reach obstacle 2 directly without reaching obstacle 1. I need to think of it in that way. So here is what I can do. Among the total paths that start from 1 comma 1 and reach the second obstacle, which is x2, I could remove the number of paths that reach the first obstacle and then reach this guy. Okay, so this is nothing but x2 minus x1, the number of paths that reach obstacle 1, and then multiplied by the number of paths starting from obstacle 1 and reaching obstacle 2. So let me just call it O1, O2. Or basic point is the number of paths starting at the obstacle 1 and reaching obstacle 2. Alright, O2. And then I would have the number of paths that directly reach obstacle 2 without going through obstacle 1, isn't it? This thing will give it to me, give me that quantity, and now my answer will simply be W minus x1 y1, and let's call this capital X2 minus capital X2 small y2, and now I'll have my ways again. So guys, with this you should have developed a nice intuition of how we are going to solve this problem, and now I'll move to the final solution. You can pause the video and try it on your own, how you can build a final solution to this thing when there are not just 1, 2 but many obstacles up to 3000. Alright, so I'll be erasing this now. So now we have a grid that may have n number of obstacles, and this can be a very huge grid with dimensions up to 10 to the power 5 into 10 to the power 5. Okay, but we can have at most 3000 such obstacles. So we're gonna follow the same idea as before. We're gonna find the total number of ways, which was easy to find out using binomial coefficient. So imagine it to be w. W is the number of ways if there was no obstacle. Okay, then what the number of ways to reach from 1 comma 1 to n comma h comma w. Okay, that's okay. Now we are going to remove those paths that are blocked by some obstacle. So we'll be removing all those paths that go through an obstacle and belong to w. Okay, to count those, we saw that if there was one obstacle, of course it makes more sense to first think about those obstacles which are nearer to 1 comma 1, isn't it? Because my path starts at 1 comma 1 and I'll be reaching those obstacles first, and obviously it never makes sense that I'll reach some obstacle like here and then reach this guy. So it makes sense for me to think about the obstacles that are closer to 1 comma 1 before I think about the other obstacles. Okay, so basically closer basically could mean the Manhattan distance from 1 comma 1. Okay, so let's say I'm thinking about this obstacle. So I find the number of paths it blocks. I found that out. Okay, and I removed it from W. Paths blocked by 1. By O1, obstacle 1. Okay, next I think about some other obstacle. Maybe this one. Okay, this is according to the Manhattan distance I'm taking. This is the closest to 1 comma 1. Now I would like to take all the paths that are blocked by O2. However, I should avoid taking the paths that reach O2 through O1, right? And basically, if I'm thinking about OI, the ith obstacle, then I should think about all the paths that reach OI but do not go through any of the obstacles from O1, O2 up to OI minus 1, because then I will be counting the same paths more than once. Since all the paths that were going through O1 were already removed, so I should not count any of the paths reaching O2 that go through O1. They have already been counted by me. Okay, so I'll count all the paths that reach O2 from 1 comma 1 but do not go through O1. Okay, then minus paths blocked by O2 but not O1. Okay, hopefully this also makes sense, because for O1 we have already done the calculation and now I just want to find the paths that are blocked by O2. Alright, then I'll take O3, maybe this guy. So again, paths blocked by O3 minus paths blocked by O3 but not, so by O3 but not O1 or O2 and not O2. That's okay, we'll find that out as well. Then so on, next path, next maybe I'll be taking this guy. Then I'll be the number of paths that go through O4 but not through O1, O2, O3. And this way I can easily, for any obstacle, I could keep going and subtract the number of paths that the ith obstacle basically blocks. However, I will not again count the paths which go through any of the previous obstacles, right? So my recurrence will be something like this. My recurrence is going to be W minus paths blocked by OI but not by OJ for all j less than I. Okay, and this is going to be my final answer. Here there are a few things to consider. First of all, how do I decide which obstacle comes first and which comes later on? So as we discussed, it makes more sense that the obstacles which are closer to the 1 comma 1 cell, they should come first, or they should be numbered, given a smaller number. So most likely this should be given a 1. This should be given a 1, and definitely before I number this guy should be numbered. So it makes more sense to me that I sort them according to the Manhattan distance from 1 comma 1. Okay, because I'll prove it to you why this is correct. Because if there is any obstacle OI which has some Manhattan distance MI from 1 comma 1, and there is some obstacle OJ and it has some Manhattan distance MJ from 1 comma 1, and let's say MI is less than MJ, then it can be proved that there is no way that starts at OI and then reaches OJ. Oh, sorry. Then it can be proved that there is no way that starts at OJ and then reaches OI. So, just a second. Yeah. So, I'll be proving that thing as well. I'll just erase it. Yeah. So, there's an obstacle OI with a Manhattan distance MI, and there is an obstacle OJ with a Manhattan distance MJ. So that MI is less than MJ, then there exists no path that starts at OJ and then goes to OI. So if this was 1 comma 1, OJ will be some xj plus yj distance away. Xj plus yj distance away from 1 comma 1, and OI will be some xi plus yi distance away from 1 comma 1. Okay, now for OJ, for there being a path from OJ to OI, the situation must look something like this. I should be reaching OJ first, and then either by going right or by going down, or both, I should be reaching OI. However, if this was the case, if I went only right and down and reached OJ, and then I reached again went right and down and reached OI, then this would mean that my Manhattan distance for OI has to be greater than the Manhattan distance MJ of OJ, right? Because this was MJ, and now since I'm going right and down once, even after this, then this has to be something greater than MJ only. So this makes a contradiction here, and therefore there exists no path that starts at OJ and then reaches OI. Alright, so we can sort the obstacles according to their Manhattan distances. Second thing that I would like to make clear over here is, how do I really find out the number of paths that go through a particular obstacle OI but not through any obstacle OJ where J is less than OI, right? That is another thing of interest. Now basically, if you have understood how I am going to calculate, why is it correct? Okay, so imagine this is some obstacle O1, maybe this is O2, then O3, and let's say this is our O4, and I would like to find out the number of paths starting from 1 comma 1 and reaching this guy, that is the fourth obstacle O4, but these paths should not cross any of the previous obstacles, isn't it? So for doing that, of course, the total number of ways will be found out using our binomial coefficient. I need to go down and I need to go right, so I'll use the binomial coefficient relationship for that, and from that I can definitely subtract the number of paths that go through this guy and reach this guy, isn't it? All these paths will be simply subtracted out. Now I could take this second obstacle, and the number of paths that go through the second obstacle but not through the first obstacle, these will also be subtracted out. Same way for the third obstacle, I will think about all the paths that go through this particular obstacle and reach O4, but none of these paths should go through either O1 or O2, right? And I will subtract this as well from the total ways for reaching from 1 comma 1 to the obstacle number 4. and this way I'll be able to find out all the number of paths that start from 1 comma 1 and end at the 4th obstacle. So guys, hopefully the idea is clear to you, and so is the recurrence. I'll be implementing the same idea in the following video, and if you have any doubt here, most likely it will be cleared once you implement the solution to the problem. So thanks for watching. I'll see you in the next video. Hi guys, in this video we'll be implementing the solution we have discussed to y grade 2. Okay, so here I've added some code, save some time. Basically here I've calculated NCRK. I've made module to find out NCK, and these functions allow me to do just that. Basically NCK is nothing but n factorial over k factorial into n minus k factorial, and we wanted to find out NCK under the modulo 10 to the power 9 plus 7, isn't it? So what we can do is we can find out n factorial first, then we can find out k factorial and n minus k factorial, and I could simply choose the modular inverse of these two under the modulo 10 to the power 9 plus 7, and I could invert these under the modulo value, and I could find out NCK modulo 10 to the power 9 plus 7, and that is exactly what I have done. I'll just show you how. So here I have first of all pre-processed the factorials under the modulo mod. Okay, and these are all the factorials I would require. This power function I'll explain why I need it, and here is the NCR mod. It is doing nothing but factorial of n into inverse of factorial k modulo m into inverse of factorial n minus k, and maybe I could do a modulo again. Yeah, and it has to be mod. Alright, modulo mod, and that's it. So to find out the inverse of a number, I've made this function, and according to Fermat's little theorem, the inverse of any number a is nothing but the inverse of some number a under the modulo m is nothing but a raised to the power m minus 2 under the modulo m, and this is precisely what I'm going to do. This is according to Fermat's little theorem, and if you are unaware of it, I would recommend you to go and study about it. So by calculating the power m minus 2, we can find the inverse. So this is exactly what my function inverse is doing. It is calculating the mod minus 2 power of val, and here is the function to calculate the power. This is nothing but binary exponentiation. Alright, so here I've taken the input h, w and n as per the input format, and then I've taken these obstacles, and that's it. Then I'll be calling the solve function, and the solve function should return me the answer to the problem. Alright, so let's first find out the total number of ways if there was no obstacle, and as discussed, it is nothing but LL ways equals to NCR mod, and we'll be needing h plus w minus 1 comma, I guess h minus 1. Yeah, I guess so. So just to be sure, I'll take a second. So maybe if h was 3 and w was maybe 4, then I would make a total number of h minus 1 down moves, that is 2 down moves plus 3 right moves. Overall I have 5 dashes, and h minus 1 plus w minus 1 dashes, that means h plus w minus 2 dashes in all, and among these h minus 1 will be downward moves, so it has to be h plus w minus 2 ch minus 1, right? So this has to be 2 here. All right, no problem. Okay, so we know the total number of ways if there was no obstacle at all. Now I need to process these obstacles one by one and find out the number of obstacles those basically the number of paths those obstacles block. So first of all, I would like to sort the obstacles up according to maybe the Manhattan distance. So obstacle dot begin obstacle dot end and some comparator that I'll be defining. Let me just define the comparator as well. It is going to receive pairs P1, P2, so return if P1 dot first plus P1 dot second is less than P2 dot first dot P2 dot second, then P1 should come before P2 in my sorted order, right? And that is precisely what this comparator tells it to do. So with this, my obstacles have been sorted according to the Manhattan distance from 1, 1. All right, now the number of ways, the number of paths a particular obstacle blocks should be subtracted from ways. Okay, so I need to know the number of paths from 1, 1 to some obstacle. So let's make a vector for that. I'll be keeping this in a vector ll paths to obstacle, and for the first obstacle the number of paths can be easily determined. Paths to obstacle dot pushback from 1, 1 to the first obstacle. These will be the number of downward moves plus the number of rightward moves. Just a second. From 1, 1 to the first obstacle. So my first obstacle is nothing but OBS at 0 and a total of 1 minus basically OBS at 0 dot first minus 1 moves will be made in the downward direction plus these moves will be made in the downward direction plus OBS at 0 dot second minus 1. These are the moves that will be made in the rightward direction, and overall I should push the number of paths starting from 1, 1 to this first obstacle will simply be this quantity NCR, this quantity comma the downward moves. Exactly. Yep. So this simply represents the number of paths that go from 1, 1 to the first obstacle, and what I'll be keeping in this paths to OBS is the number of paths that go from 1, 1 to some ith obstacle but do not go through any of the jth obstacles such that j is less than I. That is what this paths to OBS is going to maintain. Alright, so it might be useful to define a function that simply helps me calculate the number of paths between 2 points. Basic idea is the number of paths that start at a particular point and end at some other point. So paths between points, this might be a helpful function, and let's say ll paths between points, and 2 points are received by this. P1 and P2, and this will tell me the number of paths that start at P1 and end at P2. So first of all, if there is any path, then P1 dot first has to be less than P2 dot first, or at least less than equal to, and same goes for P2 as P1 dot first and P2 dot second as well. If there has to be any path, this condition has to be satisfied first of all, since I'm only allowed to move right and down. So only if these two are true, then go here, otherwise return there are 0 paths. Alright, and now what I'm going to do is I'm going to use this relationship. CR mod. Here I'll simply use P1 dot first. Since I'm going from some point P1 to P2, then I need to know how many down moves I make. So let's say integer down equals to the number of down moves I'm going to make. That will be P2 dot first minus P1 dot first. And the number of right moves I make is P2 dot second minus P2 dot first. And as we saw, we have to do down plus right minus 2. Not really down plus right, down plus not down plus right minus 2, in fact down plus right. And here I could simply use any of these two quantities, so maybe down, and that's it. That will return me the number of ways that start at P1 and reach up to P2. Okay, now I'll simply be calculating this paths to OBS vector. That is first of all, path to OBS dot pushback, the distance from the number of paths from 1 to 1 to the first obstacle, that is OBS at 0, right? And I'm going to pass pairs. That looks all right. And then I'll be calculating this for every path. For integer goes from 1 to OBS dot size. Now for this particular obstacle, I should count the number of paths that reach from 1, 1 to this ith obstacle, but should not reach any of the previous jth obstacle, right? So what I'm going to do is, for every j from I minus 1 and j greater than equal to 0, j minus minus, let's say ways, or not ways, maybe paths equal to, initially the number of paths will simply be paths between points 1, 1 and this obstacle, and then we'll keep subtracting the extra paths that I'm counting here. Okay, so 1, 1 and OBS at I. Now this is all the paths from 1, 1 to OBS at I. However, the previous obstacles must be removed. Basically the paths that went through them and then reached this guy should be removed. So what I'll do is, for the jth path, the number of paths that have to be removed is simply paths to OBS at j into paths between points OBS at j and OBS at I, right? So this is the number of paths from j to I multiplied by the number of paths from 1, 1 to j, and and paths between points OBS J and I, this has to be removed from the actual paths. So paths minus this whole modulo mod, and since I'm doing a subtraction, I'll be adding mod as well. Alright, and yeah, of course, also this multiplication should also be under another modulo. Alright, now I know the paths to OBS matrix. Now I simply need to subtract from ways. For that, what I'm gonna do is I'm gonna iterate over this vector. And then for I equal to 0, I will know base, right? Then base equals to, also need to set paths equal to mod plus paths minus this, and this looks right. Yeah, here ways equal to ways minus paths to obstacle at I into all the paths that go from this particular obstacle to h comma w. So paths between the points the ith obstacle and h comma w. Yep, this thing should be under a mod, again under a modulo. And since I'm doing a subtraction, I'll add mod. And once this is done, I should have my answer as ways, and I'll return it. So I guess this should work. I'll check on a sample input and we'll see. Okay, so 40. Factorial was not declared in the scope. Has to be fact. K was not declared in the scope. Has to be fact of R minus R. NCR, not NCK here. Okay, 64 paths dot obs dot push 1 comma 1 comma obs 0. I don't get what the problem here is. So it's vector long 0. Matching functions were called to vector long int. Okay, push back. I need to call the function. I haven't called the function paths between points. This should do it. Alright, now we are getting an answer. It is incorrect. I'll check what's the problem. Okay, so this code was simply calculating the paths to OBS. One thing I have not done here is that paths to OBS dot, I have to put this path in fact. Once I've calculated the number of paths to some ith obstacle that do not go through any previous obstacle, I should also add it to this, but still the answer could not be 0 due to this mistake. It has to be something else. I guess I haven't called preprocess. I should call preprocess right after, right here, and this should do it, I guess. Let me just run the code. Okay, we're getting 3. Yeah, that's the right output. We'll check maybe this guy. The output should be 1 2 3 4 4. Alright, I think that's the correct output. Alright, I'll try and submit. So as far as the time and space complexities are concerned, uh, first of all, this looping is n square, and again, since I'm calling this paths between points everywhere, this uses ncr mod. ncr mod uses the inverse function, and inverse is log n, so you can safely assume this to be n square log n at worst, or n square, right? Only because of the power function. Okay, so it's given TLE. Let me check what's why is it giving me a TLE. Alright, 3 of the cases are giving a TLE. So what I could do is I could probably cache up the inverses, and that will make the process faster. Here I'm calling the inverse function again and again, this guy. If I could have cached this thing, then the process will be much faster, isn't it? So let's just cache it up. LL inverses. So if I've already calculated some inverse, I will not calculate it again. Here if inverse is at val is not equal to -1 maybe, then return it. Return inverses at val. Otherwise calculate it, store it, and then return it. Yep. Yeah, I think that should do it. I should set inverses to -1 also, so I'll just do that in the preprocess function. Here I'll write memset inverses -1 size of inverses, and yeah, with this I think it should pass the time limit. Okay, let me just check what's the problem. Alright, so I cannot simply do this because my inverses could be large and up to 10 to the power 9, so I cannot use a array to store them. Maybe I could store them in a map or something. But before I do that, I'll just try to use fast input output, and that might just do the work. Since the input is large when there are 3000 points, so using fast IO might just help out. And if it doesn't, then we'll see what we can do to make things faster. We need to cache something, I guess. Let's just see if this works. Okay, so it does not. So we'll have to make things faster somehow. Right, so it has to be because of the inverses being calculated again and again, and we can cache them somehow. So the value that I'm calculating inverse for is very large, that's true. However, I'm always calling for factorial of r or factorial of some values inverse, right? So if I could store maybe inverse factorial somewhere, then it would look something like this. So ll inverse of factorial, and I could pre-compute all these, then I won't have to call again and again the inverse function, isn't it? So during pre-processing itself, what I could do is I could also, once I've calculated fact of I, let's also calculate inverse, the inverse of this particular value, that is the inverse of fact of I. And once I get this value, I'm going to store it in inverse of fact at I. And this should do it. Here I'll use inverse of fact or same way here I'll use inverse of fact n minus r. Yep, that should do it. Inverse of fact n minus r. Other than that, here in the preprocess function I've called inverse of fact for every, yep, except for inverse of fact of fact 0 will be 1. Alright, this caching should do the trick, and my solution's complexity will reduce down to n square from n square log n. Just checking if I'm still getting the correct answer, and then I'll submit. Okay, so line 34. And this. Yep. Okay, so there is some error now. Alright, so let me do one thing. What I'm gonna do is take this code and just correct it and make a fresh copy instead of messing things up. Here I'm going to store my inverses 3, 4, 5, and I'm gonna put my preprocess here. inv at 0 becomes 1, and inv at I simply becomes the inverse of this particular factorial in fact of I, right? Yep. Okay, so this should set up my inverses and cache them up, and next time onwards, let me just check the answer currently. Yep, so it's giving the correct answer. Let me just change these things as well. So instead of inverse of factor, I will simply write in invr, right? Because that is what's stored there. Same way for this, I'll simply write inv n minus r. Now this should give me the correct answer. Yep. Now this should pass the time limit. I'll explain how the time complexity has improved. Yeah. Alright. So I'll quickly explain how the time complexity has improved here. So before the solution was n squared log mod. Okay. and now mod, because I'm calculating the power raised to the power mod. Every value is being calculated to the power mod minus 2 to get the inverse, right? This was the complexity earlier. However, after evaluating those inverses, this factor is removed and my pre-processing has become n plus in fact n log mod, not n log mod, in fact 2 into 10 to the power 5 into log mod. That is my pre-processing now, and overall my solve function runs in n square because I've cached up the inverses. And yeah, so now it is getting an AC. Also you can see the execution time has got much better, all because of caching up the inverses. So guys, hopefully the video was helpful to you, and thanks for watching. Hi everyone, in this video we'll be solving the problem Z, that is frog 3, and this is the final problem of this contest. So let's get to it. Okay, so this problem is the problem statement is almost the same as frog 1 and frog 2, except that the constraints are quite large. And here it says that there is a frog who's initially at stone number 1 and he would like to reach the nth stone in such a way, and he has to make jumps in such a way that the overall cost to reach the nth stone is minimized. Okay, and what they say is that a frog can jump from the ith stone to any of the stones that is in front of the ith stone. So from the ith stone the frog can jump up to the I plus 1th or to the I plus 2th and even to the nth stone. Okay, the thing is that the cost that will be incurred to jump from some stone Si to Sj is equals to Hj minus Hi whole squared plus some constant C. Okay, this will be the cost incurred when you jump from a stone I to J. Okay, and overall you would like to jump in such a way that you reach the nth stone with the minimum possible overall cost incurred. Okay, so let's look at a sample input. First of all, here you could see that n is up to 2 into 10 to the power 5. So the solutions that we came up for A and B would not work here. We'll discuss them again obviously, but still. Okay, and this is an important constraint and we'll look at this thing later on. Okay, that the height of the stones are in increasing order. So you can see the sample input 1. Here they say that it's best to jump from stone number 1 to stone 3 and then to 5. Okay, so jumping from 1 to 3, a cost of 3 minus 1 whole squared plus a constant C, 6 is incurred. This is for the first jump from 1 to 3, and then the frog jumps from 3 to 5. Here a cost incurred will be 5 minus 3 whole squared plus the constant cost of jumping a stone, that is 6 again, and overall it turns out to be 2 square plus 6, that is 4 plus 6 10 plus again 4 plus 6 10 and therefore 20, right? This was the sample input 1, and you could test out any other possible way of jumping up to the fifth stone, and the cost will always be either equal to 20 or greater than 20. Therefore our answer is 20. So you can try this thing. Let's say the frog directly jumps from stone number 1 to stone number 5. Okay, stone number 1 has a height of 1 and fifth stone has a height of 5. So this is 5 minus 1 whole squared plus the constant cost of jumping, that is 6, and we get 4 square, that is 16 plus 6 equal to 22 in our cost. Okay, and 20 was less, so 22 is not optimal. So sample input 2 can be seen here. It's simply jump from stone number 1 to stone number 2, and your overall cost is simply going to be the difference among these two stones squared plus this constant cost of jumping. This is simply here to show that we would like to use long instead of integer. And sample input 3 is a little bit larger input. If you would like, you can try this out as well, but I guess the problem statement is quite clear. The main thing here is that from the ith stone I could jump to any of the stone j such that j is greater than I, and j has to be less than equal to capital N. All right, and n is the total number of stones. Okay, so guys, now we'll be moving forward towards the solution. Okay, so we're solving Z frog. So first of all, we'll be discussing a brute force DP solution, and then we'll try to optimize it further. Before we really move on to the solution, I would like to mention that this problem has a prerequisite, and the prerequisite here is convex hull trick DP optimization. Okay, so I recommend, if you guys are unaware of convex hull trick, you should definitely go through it once. But I will make sure, even if there are people who are unaware of convex hull trick, even they'll be able to follow this video tutorial, given that they have basic knowledge of geometry, that is lines and slopes and the equation y equal to mx plus c. So if you're aware of this much, you don't really need to know the convex hull trick to solve this particular problem. But I would recommend, it's better that you go through convex hull trick once. Alright, even if you don't go through, I'll try to make the video tutorial as simple as possible so that you'll be able to follow it even if you don't have this prerequisite. Alright, so first of all, pause the video and try to come up with a n square dp solution, okay? And only then we'll be able to optimize it further on. So you can pause it and try, and it must be relatively easy to come up with a n square solution to this problem. So consider this. I define dp of I as the minimum cost incurred to reach stone I. Okay, so dp of I is clear. We define dp of I as this, and our final answer is obviously now going to be dp of n, that is the minimum cost incurred to reach stone n, starting from stone 1, of course. So we would like to write recurrence to evaluate dp of I, and if that is done, then dp of n can easily be calculated iteratively or recursively as one likes. So of course dp of 1, the minimum cost incurred to reach stone number 1 is simply 0 because the frog is initially at the first stone, so that's okay. Now we'll write a recurrence for this. Okay, so to reach the ith stone, I could make the final jump from some jth stone such that j is less than I. Alright, so from any previous stone, I'll be making one jump and reaching the ith stone. To do that, a cost is incurred which is equal to hi minus hj whole squared. Okay, since I'm jumping from the jth stone to the ith stone, and therefore a cost is being incurred hi minus hj whole squared plus a constant cost c of making a jump. Okay, and whatever was the minimum cost incurred to reach the jth stone. So overall this is going to be my dp of I, and this is simply nothing but make a jump from any of the previous stone j, and among all the possible stones choose the one so that this cost is minimized, overall cost. Okay, minimum for all j is then I. So now we have a recurrence, we have a base case dp of 1 equals to 0, and we could very easily evaluate dp of n, but very clearly you can see that evaluating this recurrence for all j less than I is n squared, right? Because for every I have to look at every j that is less than I. So my solution becomes, in the worst case, big O of n square time, but n is up to 10 to the power 5, right? So my solution can be n square n root Basically my solution has to have a running time of maybe n root n, big O of n, or n log n, right? It cannot be n square because otherwise it will time out for n equal to 10 to the power 5. Okay, now we'll try to optimize it. So let's just look at this equation again and try to optimize this particular for all j less than I. Okay, so our equation is this. Right, this is nothing but dp of j plus hi squared plus hj squared and minus 2hi hj. Okay, so here one thing that you can notice is hi square is going to be a constant no matter which particular j you select. Hi square will definitely be included in our overall dp of I, right? C will also be definitely included in our overall dp of I. So we can say that hi square plus c is some constant part, plus we have some dp of j plus hj squared. This is constant for a given j, right? So for a given j this thing is constant, and minus 2hi hj. Overall this term is going to remain constant no matter what j you select, and this term will depend upon j, and this term depends upon both hi and hj. Here we are particularly trying to minimize this thing, right? So we're trying to minimize dp of j plus hj square plus minus 2 hj into hi. So here it is quite evident that this particular thing will be constant for a particular j, right? Let's say this is kj, some constant for j, minus 2 times hj into hi. Also this thing is constant for a particular j, so this turns out to be kj minus, let's write this, mj into hi. All right, so this was the value we were trying to minimize, and this is the result that we are getting after replacing a few terms, and we could overall call this result to be yj, right? Then it becomes yj equals to some constant j kj, right? Some constant value for j kj plus mj. Just a second. Okay, it was minus here, and I could take it plus, right? Because then yeah, mj will be, instead of 2hj I'll make mj equal to minus 2hj, right? Then my equation becomes yj equals to kj plus mj times hi, and I want the minimum of this yj for all j less than I, right? Therefore among all the lines y1 equals to k1j plus m1hi, in fact m1x. This is nothing but the equation of a line, and we are trying to evaluate what is the value of that line at x equals to hi, right? So among all the different lines up to y, from y1 up to yi minus 1, I'm sorry about this j, this is nothing but, yeah, k1 k2 ki minus 1, the constant for the I minus 1 with line, plus the slope of the line into x. We're trying to evaluate which of these line has the minimum value at x equals to hi, isn't it? This is what we are trying to evaluate. This is nothing but the equation of a line, and we're trying to evaluate which of these I minus 1 lines has the minimum value at x equal to hi, and whatever is that minimum value, that will be basically the value we would like to use in our use to evaluate dp of I, isn't it? So I'll be just describing the slope and the intercepts here. So we saw that our equation of the line was becoming something like this: yj equal to mj of x plus some constant kj, right? So this mj is nothing but the slope of the line, right? And this kj is the y-intercept of the line. Basically, when x is 0, where does the line cut at the y-axis? So before we optimize, a little bit of interpretation out of this line, okay? So this mj is nothing but minus 2hj, right? So the slope is negative because hj will always be positive according to our constraints, and our lines are going to look something like this. If this is the x-axis, this is the y-axis, okay, and our slopes are negative, so our lines are going to look something like this, making an obtuse angle with the x-axis, right? And the more the negative the slope is, the more it is basically closer to the 90 degrees. So this line has some slope m0 maybe, and this has m1. Then the absolute value of m0 is less than the absolute value of m1. Okay, so as the slope becomes more and more negative, your line keeps getting closer to this y-axis itself. Okay, so this is the interpretation of the slope. The more negative the slope gets, the closer it gets to this 90-degree line. Okay, the line that makes the perpendicular line to the x-axis, that is the y-axis, and the line that is exactly perpendicular, that has a slope infinity. Okay, so this is the interpretation of the slope. A line something like this has some slope, but a line like this has a slope that is more negative than L1. Okay, so L2 has a slope more negative than L1. That is the interpretation of slope. So now among all the different I minus 1 lines that I have when I'm trying to evaluate dp of I, I'm trying to choose the line that has the smallest value when x is equals to hi, right? So among a lot of different lines, a lot of different possible lines, maybe let's take a few more. So imagine these are a few lines. Among all these lines, I would like to find the line at which the value when x is equals to hi has the lowest y-intercept, right? So imagine if x equal to hi is this particular line. Then this is the intersection or the intercept, that is the minimum possible value of y among these different lines. Okay, so this will be the minimum value of my function. For this line, putting x equal to hi gives you the lowest value. For this line, x equal to hi would have given you this value, that is greater than this because it is above it, and y increases in this direction. For maybe this line, the value was this. For this line, the value was here, and that's the major idea. Okay, but how does this help us to optimize the solution? Okay, that is the main question now. We can visualize these different dp of j values as lines, and then we can visualize that we are looking for the line that has the lowest y-intercept with the line x equal to hi. That is all right, but how does this help us to optimize our solution, isn't it? So this is where convex hull trick comes in, and you don't need to worry if you are unaware of it, because I'll be teaching you the very basics. Okay, so initially we have dp10, and that is the base case. That is very easy. Now thinking about dp of 2, we have only one line, right? So imagine the line to be something like this. This is the line, and to calculate dp of 2, we basically need the minimum value of all the lines we have currently. We just have one line at x equal to h2, right? At x equals to h2. So we'll simply evaluate the value of this line at x equals to h2, and it will simply be y equals to m1 h2 plus k1, right? And m1 was nothing but minus 2h1, and k1 was okay, it was dp of 1 plus h1 squared. Okay, so we had this line. We'll simply evaluate the value of this line at x equals to h2, and we'll get what dp of 2 is. That is very easy. But when we're thinking about dp of 2, we'll be having not one line but two lines. Okay, and we'll have to think which gives me a better solution. So an important constraint in the problem here is that h1, first of all the heights are positive. That was one of the constraints, and the second important constraint was that h1 is less than h2, and h2 is less than h3, and so on till hn. What this does is that the lines here are, first of all, in every time a new line comes, it will have a more negative slope than the previous line, because slope is minus twice of the height of the stone, right? So the next line that comes will be a little bit tilted to in the clockwise direction, isn't it? Because the slope is getting more negative, so line is going to be something like this. And next time we'll be evaluating. So if this time we had evaluated the answer for some x equal to h1 at, for this line, maybe this was the line x equal to h1, next time we'll be evaluating the minimum for some line to the right of this, right? Because we are evaluating the minimum minimize at the minimas at hi, right? Initially we'll be evaluating at h2. This was for h2. Next we'll be evaluating the minimum among all the existing lines for the height h3, and then h4. And since these are increasing, so this particular line, the intercept we are thinking of, will keep shifting to the right side. All right. Okay. So we'll see how this thing is going to help us. So next we gonna have, after this we are going to have two lines. Okay, once you have calculated dp of 2, for dp of 3, while calculating dp of 3, we'll be having two lines, and they look something like this. Now for calculating dp of 3, it must be clear that if h3 is less, let's say this is some intersection here. Okay, this is some intersection here. So if I'm evaluating h3 for basically the minimum at h3, and h3 lies to the left of this intersection, then this means I'm going to use line number 1, because that will give me a smaller value, isn't it? This line has a smaller value compared to what we have here. So if we evaluate the minimum at some x equals to h3, and h3 comes before the intersection of these two lines, to the left of these intersection of these two lines, then we should be using L1, right? However, we should be using L2 if x is greater than the x intersection of these two lines, and the x equal to h3 falls somewhere here. In that case, you will have a smaller value at L2, right? So we'll be using the line number 2 instead of line number 1 if our h3 is greater than this point. Otherwise, we'll be using line number 1 only. So one thing from this that we must be sure about is that line 2 becomes useful only after our x or the hi has become greater than this particular intersection. So if this point was maybe x naught, y naught, then line 2 will be useful only once the hi we are evaluating is greater than or equal to x naught. Before that, line 2 is dominated by line 1 because line 1 gives me a better answer. Okay. So now we would have calculated dp of 3 as well, right? Using these two lines and simply by the idea that which of the lines should I be using. We know that line 2 becomes useful once our current hi that we are evaluating has become greater than this x naught. This point was x naught, y naught. And if hi that we are evaluating the minimum at is greater than this x naught, then line 2 has become useful, otherwise we are still at line 1. And once our hi has become greater than x naught, then line 1 becomes useless. Once we have crossed the point that hi has become greater than x naught, then in the future line 2 always dominates line 1, right? So after that point, once you have come with that point that the hi's are now greater than x naught, this guy, then line 1 can simply be eliminated from the lines we are, basically the useful lines that we are keeping with us, because now hi are only going to increase, and the more that hi's increase further, the more the difference between the values that L2 and L1 give you increase, and L2 keeps getting better than L1 as hi increases to the right. Okay, so we would have evaluated dp of 3. So let's say, imagine that dp of 3 came at some value here. So this was the x equals to h3. So we would have used the line 1, and line 2 would still not be useful because we have not crossed the point x naught till now. Once dp of 3 has been calculated, there is an entry of a new line. Basically from now onwards, 3 lines are available to us to choose from. So let's say the third line that comes in, first of all, it has a more negative slope than L2. So let's imagine that this line comes in. This line L3 intersects line L2 at this point, maybe x1, y1. Now we know that once we have crossed the point hi equal to x1, or once our heights of the stones have become greater than this x1, that means we are to the right of this point, then L3 becomes useful, right? Once you have crossed this point to the right, L3 is now useful, and after crossing this point, L2 becomes useless, because after this we'll always be using L3. Once we have crossed x1, the height of our stones has become greater than x1, we'll always be using L3, and L2 becomes useless. But the interesting thing here is that L2 was going to become useful only after x naught, but L3 becomes useful at x1. This means that L2 becomes useless after x1. So this means that there is no more a need of having L2 in my hull, or the useful lines do not need to contain L2 anymore. Reason being, because by the time L2 becomes of any use to me, L3 is only L3 is more useful before that point. So L2 is useless now. And now I'm only interested in this point where L3 and L1 intersect. So this was x1, y1, and I'm interested in this point, let's say x2, y2. So once we have crossed, or once our height of the stones has become greater than x2, then line 3 becomes useful and line 1 becomes useless, right? So let's say the next time while I'm trying to evaluate dp of 4, our value comes out to be something like x equals to h4, and this is the line x equals to h4, and this line, the h4, is greater than x2, right? Therefore the line L1 which we were using till now now becomes useless, because from now onwards line 3 dominates line 1, and whenever there is a query which asks me the minimum at some certain x equal to hi is always going to be greater than this point. So it's going to be the right of this, and to the right of this intersection point L3 always gives me a lower y-intercept. Therefore now L1 also becomes useless, and we are just left with one single line L3. So guys, hopefully the gist of the idea, basically the gist of the algorithm is clear to you. We're going to maintain some useful lines, and as soon as some line becomes useless, we are going to eliminate it from our data structure, and we're going to point to some particular line that we are using currently, and we are going to maintain values when a certain line will becoming useful. Okay, and if there exists any lines, something like we had with L2 which was becoming useful here, but it was getting useless after this point, so this line, these type of lines also will be eliminating, okay, from a data structure. So we're going to maintain a data structure which is going to keep these lines and going to help us find the minimum value. It is only going to maintain the useful lines, okay, and it will basically return us the minimum value at some x equal to hi. And let's say if we were using some line L1 till now, and now our queries have become some x greater than this point, our queries are getting x values to the right of this, then we'll be moving on to the next line which is now useful, that is L2. So that is the gist of the idea. So all that we are now left to do is to build such a data structure that can maintain these lines and return us the minimum at some x equal to hi in a very fast manner. Okay, we would like this to be fast. We would like to build a data structure that can help us do that, and I'll be describing how we can do it, and then we'll move forward towards the implementation. This kind of thing, or this kind of data structure, and using these lines to get the minimum value, this is known as the convex hull trick. Okay, and here the convex hull trick has been made easier due to the constraint that the heights are in increasing order, and that has made our problem easier. Okay, so here is what we are going to do. We're going to maintain a data structure that has all the meaningful and useful lines, and it is going to keep the more currently being a line that is being currently used in the front. Okay, so initially we have a data structure that has only one line L1. Okay, and then we evaluate dp of 2. Since there is just one line, it is quite easy to evaluate dp of 2. We'll find the value of this line at x equals to h2, and it's done. Now our data structure should have two lines, L1 and L2, and there is some intersection between these two lines. L2 has more slope, so we know once we have crossed this intersection point, line 2 starts becoming useful, and before that line 1 is more useful. So we'll find what that intersection point is, and we'll keep it here, maybe some x2. So now we know that once you have crossed the intersection point x2, then line 2 will start becoming useful. So if we are at a point hi, we are trying to evaluate the query x equals to hi, and hi is greater than equal to x2, then line 1 will simply be removed from our data structure, because from now onwards all my hi are going to be greater than x2 also, always. And since line 2 will always give me a better result than line 1 for such kind of queries which have x greater than x2, so line 1 is meaningless to me from now onwards, and I'll be eliminating this line from the front, and line 2 comes to the front. Okay, so this is the idea basic. Now a query comes in, it asks me the value at x equals to h3 while I'm trying to evaluate dp of 3. I check if h3 is greater than equal to x2. Let's say it is not. So of course L1 is the better thing to do. L1 gives me the higher result. So I evaluate the value of line 1 at x equals to h3 and I return it, and that is my dp of 3. Cool. Next, let's say my data structure now gets another line that is L3, and L3 starts becoming useful at x3. Okay, But imagine that x3 is less than x2. That means line 3 becomes useful before line 2 itself. Something like this. So before the line 2 becomes ever gets to become useful, line 3 would have already dominated line 2 by till then. So line 2 is basically meaningless now. Since if I crossed x2, I would have crossed x3 as well, and once you have crossed x3, then line 3 is the more useful thing, right? So line 2 becomes useless in such a case, and we remove it from our data structure. Okay, then we have line 3 and some intersection of line 1 and line 3. So maybe some xy. Let's just say x13, okay? The point where line 1 and line 3 intersect. We know that once our heights have crossed the intersection point x13, then our line 3 will start dominating line 1. But before that, line 1 is more useful. Okay. Line 2 simply got eliminated because line 2 will never become useful, because line 3 becomes useful before line 2 gets to become useful. Now let's say at the next query I get is x equals to h4, and maybe h4 is greater than equal to x13. In that case, I know that line 3 is going to give me a better answer, and from now onwards my hi are always going to be greater than x13, since hi's are sorted in increasing order. So if h4 is greater than x13, so any hj such that j is greater than 4 will also be greater than x13, and line 3 will always give me a smaller answer compared to line 1. So line 1 becomes obsolete now, and I'll be removing it from my data structure. And the only line now I'm left with is L3. However, once I evaluate dp4, I get another line, that is L4, and we know that line 4 becomes useful at some x34. Okay. So again, if x34 were less than x13, basically line 4, if line 4 was becoming useful before line 3, then line 3 would be straight off eliminated, because now line 4 is the winner. Okay, it dominates, and you always get a minimum more smaller answer, or the minimum answer at L4. But let's say that is not the case currently, and line 3 stays in the structure. Next, let's say I get some L5. Okay, and let's say L5 becomes useful at some intersection x45. Right, so this is L2, sorry, L3, L4 and L5, and these are the current lines that are useful. Okay, maybe consider this kind of case, L3, L4. So line 3 is useful till this point, and we call this point x34. After this point, line 4 is the more useful thing, and let's say line 5 is this guy, and line 5 intersects line 4 at this point x45. Okay, so now imagine my next query is x equals to h6, and let's say that h6 is greater than x34. Okay, since it is greater than x34, so L3 is now useless, right? So L3 should be removed from my data structure. So first of all, L3 gets removed from the data structure. That's all right. Next, what happens is I should either evaluate it at L4, but imagine that h6 is in fact even greater than x45. Okay, so h6 is greater than even x45. So this means that even line 4 has now become useless, and I should remove even line 4 from my data structure, and the only line left is L5. Okay, so I hope the gist of the algorithm is clear. Here we'll now simply evaluate this value of line 5 at x equal to h6 and return it, and that will be the minimum. So hopefully the gist of the algorithm is clear to you, and the basic idea is to maintain the useful lines. And as you saw that either the lines will be added or deleted, and once a line has been deleted, it will never be added again. So if L3 has been deleted, this means that we had reached the point x34, and now all the queries are going to be greater than x34 definitely. So there is no point of keeping L3 because L4 is always going to give me a better answer than L3. Same way, once we had crossed x4 5 in my stone heights, it was clear that line 4 is never going to be useful and line 5 will always give me a better answer. So line 4 was also kicked out of my data structure. Okay, so what I could do is I could simply maintain a deck of these lines, and as soon as the line becomes useless, I remove it from the front of the deck and I add new lines at the end of the deck. And if the last line in my deck becomes useless because I am adding the new line that starts becoming useful before the last line in the deck, so even that line must be removed. So if it were the case that L1, L2 and L3 were in the deck and L4 is about to come at the end, but L4 starts becoming useful before L3, then L3 is now useless. So I should also remove L3. So therefore I should use a deck kind of data structure because I'll be removing from both the sides, front and back, and pop front and pop back in a deck is big O of 1. And I'll be either adding a line or removing it, and once a line has been removed it will never be added again, and a line will be added only once in the deck, and overall I'll be doing big O of n operations of these lines insertion and deletion. So I'll just summarize the overall algorithm quickly and we'll move to the implementation. So we discussed, first of all we discussed dp of I is equals to dp of j plus hj squared plus hi squared and plus c plus in fact plus minus 2hj hi, right? And we said okay, we wanted to evaluate this recurrence over all j less than equal to I, and then we said that this guy is constant for a particular j. So we said that kj equal to dpj plus hj squared, and we know that this thing is a constant for a particular I, so we don't really need to minimize it because it's going to be the same no matter what j I select. So I can basically keep it away from the part that I want to minimize, and I could simply take this thing out, and I wanted the minimum over the remaining thing. The remaining thing was nothing but kj plus mj, the slope of this line, and the slope was nothing but mj equal to minus 2 times hj, twice the height of the stone the line corresponds to. And I would like to evaluate the minimum among all these j lines at x equals to hi. So this was the overall formulation, and then we discussed that okay, we'll be maintaining different lines, and the intersection tells us when a line starts to become useful, and if the height of the stones that I'm querying for has exceeded the point at which a line L2 becomes useful, then basically when a line Li becomes useful there is a point xi. So if the query of that is the height of the stones I'm asking the minimum value for has exceeded xi, then all the lines before Li can be easily removed from my data structure, because from now onwards those lines are not going to give me the minimum value. Same way we discussed it when I'm inserting a line Lj into my data structure, and Lj becomes useful at some point xj, but there exists some line Li in the data structure at the end of the data, at the basically right hand side of the deck, that becomes useful at some point xi, but xj is less than xi, then I could also remove line Lj from the data structure, right? So this was the formulation that we have discussed, and the usage of a deck. We'll simply be implementing this idea now, and if you have any doubt I hope that it will be cleared while we actually implement the solution. So here I've simply taken the input as always. Yeah, and I'll be erasing this now. So this is my solve function. This is going to return me the final answer, and here I've taken the input. N is the number of stones, C is the cost of jumping from some, basically C is the constant cost of making a jump, and then this is the vector store to take the heights of these stones. Finally I call the solve function with this height vector, the number of stones n, and the constant cost of jumping c. So as discussed, we'll be modeling the lines first of all, and let's build a structure for a line then. Struct line, and for a line there is a slope, so slope of the line, and a y-intercept, that is the kj, so intercept. Apart from this, we would like to have a constructor here maybe, and this will receive a value m and k. Slope equals to m and intercept equals to k. Okay, so we have a line constructor also. Okay, I don't think I need, okay, yeah. One thing I would like to keep is, what is the value of this line at some particular value x naught? Okay, so y or value at x naught. Okay, value at x naught is a function, it receives some x naught and returns what is the value of this line at the particular value x naught. So it is nothing but my line is y equal to mx plus c, so return slope into x naught, the value I am trying to evaluate it at, plus the intercept, that is c, and that's it. Also I would like to know where does this line intersect with some other line. Okay, so the x point of intersection of this line with some other line, x intersect, and let's say it receives a line L2, and I want to check where does this line intersect with the line L2. This will help me determine when does the line start becoming useful. Okay, so x intersect, and how can I find that? So my one line could be m1x plus c1, and the other line could be m2x plus c2. So let's say that the point of intersection is x naught, then at x naught these two lines, the value of these two lines is going to be equal. So m1x naught plus c1 is equals to m2x naught plus c2. This means that x naught equals to the value I want to return equals to c2 minus c1 divided by m1 minus m2, right? Simple. I've simply taken c1 to the right hand side, m2x naught to the left hand side, then taken m1 m2 common, and that's the result I'm getting. This is the point where the lines, this particular line and line L2 intersect. Alright, and this could be a double value in fact, right? It does not need to be an integer. So what I'll do is I'll seal it, and the sealing value will tell me that after this integer coordinate this particular line starts becoming useful, and before this the other line is more useful. Basically L2 is more useful. Yeah, and c2 does not mean anything. C2 should be L2 dot intercept, c1 should be intercept, m1 should be the slope, and m2 should be L2 dot slope. Alright, so we have a structure to maintain our lines. Now we are going to maintain a structure, basically a deck, to implement our convex hull trick. So let's just call it convex hull trick, structure convex hull trick, and here I'm going to maintain a deck of lines dq, and also I would like to know when this particular line in the deck starts becoming useful. So let's say a pair line comma ll. and this LL simply tells me when this particular line has started to become useful. All right, and then there should be functions to insert a line into my deck and query the minimum value. Oh, wait a second, I've made a structure, so I don't need public. Let's make a class instead. Okay, then I'll have a function insert. It takes a line L, and it inserts this line into the deck. So first of all, I would like to check, okay, if my deck is currently empty, so if dq.empty, if there is no line currently, then nothing needs to be done, simply insert this line and we are done. So dq dot, or maybe push back, this line, and when does this line start becoming useful? Since this is the only line, so this has started becoming useful from any valid point. So let's say from 0 onwards this line is useful whenever my query point is greater than 0, and that is always the case because my heights are positive, and I'll be querying for x equal to hi, the heights of the stones. All right, and if it is not empty, then what do? I check the last line in the deck. Okay, and I check the intersection of the current line with it, and I might be removing that last line from the deck if the new line is more useful, or it becomes useful before the last line in the deck starts becoming useful. So since I'll be removing it, let's say while the deck is not empty, there should be at least one line in my deck while deck not empty, and let's just say while deck not empty, check where does this line L intersect with the last line in the data structure. So let's say x, it intersects at x naught, and L dot x intersect the last line in the deck, that is given by dq dot back dot first. Okay, so if x naught is less than, in fact even equal to, dq dot back dot second, if line L starts becoming useful before the line before the last line in the deck starts becoming useful, then the last line in the deck is obviously going to be meaningless because L will dominate it even before it starts becoming useful. So if x naught is less than equal to dq dot back dot second, then dq dot pop back, that line is now useless because line L has come, so dq dot pop back. And I could keep doing this. At the end, I'll simply do dq dot push back line L, not just line L comma the point where it starts to become useful, so the point it starts to become useful will be this x naught, and I'll insert it. That's it. Okay, so I've inserted my line into the deck. I think there's some mistake in the braces or the ordering of the braces. Let me just check that this is all right. This one is also all right. Okay, yep. So insertion is right. Now the next function I would like to make is querying. So ll query, and some basically among all the lines you have in the data structure, calculate the which line gives you the minimum value at some x naught. Okay, so I'll check the first line, and let's say if this x naught is greater than equal to the point where the second line in the deck starts becoming useful, then I'll simply remove the first line from the deck. Otherwise I'll use the first line, the value of the first line at x naught, and return that. Okay, so for that, to check the second line in the deck should have at least a size 2. So if dq.size is greater than 1, while dq.size is greater than 1, if dq at 1, the second line in the data structure, dot second, the point where this line starts becoming useful, is less than or equal to x naught, then I can happily remove the first line from the data structure of front, right? Otherwise I can break. And once this is done, I'll simply use the first line in the data structure and return the value of that line at x equal to x naught. So return dq at 0 dot first the line dot intercept val at x naught. Yeah, and that's it. So querying is also clear now. We made the insert and query functions. Now we just have to write the solve function. So I'll be having a vector LLDP size n, and dp of 0 is going to be the cost to reach to the first one. Now we are using 0 based indexing, so dp of 0 becomes 0. And let's say I also have a data structure, basically class cht, some data structure. What should I name it? So this is going to maintain my lines and give me the minimum, so I'll name it minima data structure, minima ds. Okay, so minima ds dot, so dp of 0 is simply 0. Now I need to insert the first line into my data structure, so I do insert, and the first line is nothing but the line due to dp of 0, and that line will be a line that has a slope of minus 2 into h0. That is the slope of the first line, and the constant value of the first line is simply that will simply be 0, I guess, because dp of 0 is 0, so that will be 0 because constant yeah, just a second, our mj was minus 2 times hj, and our kj was dpj plus hj squared, right? So it's going to be here the height of the 0th stone squared, because dp of 0 is simply 0, and that's it. So our first line, we know the slope of the first line, and we know the basically the constant k0. Slope is minus 2 into v at 0, comma v0 into v0, and that is our first line inserted into the data structure. Now evaluate dp of I for all I from 1 up to n. So my dp of I becomes v at I square plus the c, the constant of jumping, and then among all the lines I have the minimum value at x equal to vi. So I'll be saying minima ds dot query point will be vi, right? And once this is done, I'll insert a new line into my data structure. So minima ds dot insert, the new line has a slope -2 into vi, and it has a kj value or ki value equal to dpi plus vi into vi square, and that is it. That's it. Finally, I'll be returning whatever is the value I have at dp of n-1, and this should solve the problem. Let me just try at some sample input and then we'll submit. dp was not declared in the scope. dp1 dot second, line number 60. Oh, it has to be dq, and okay. Let me check. Okay, so while not dq.empty, so this was like, if I could remove the last line from the data structure, I should remove it, but if I cannot, I should break. Let's break. Okay, we are getting the correct answer for this case, and I'll check sample input 3. Alright, we're getting the correct answer. I'll try and submit. Okay. So this is basically an improved way to implement convex hull trick. Otherwise, the generic convex hull trick runs in big O of n log n, but here, due to the sorted order of the height of stones, we could implement it in big O of n, and here I just tested the idea, whether my idea of big O of n implementation was correct or not, and yeah, we're getting AC as expected. So guys, hopefully the video was helpful to you. Here we have implemented convex hull trick logic in big O of n, and I hope guys the overall AdCoder DP problem series was helpful to you. And if you have any doubt or you would like to contact me about anything, you can contact me either on LinkedIn or Codeforces. My handle is Karthik8800, both on CodeChef and Codeforces, and AdCoder as well. So thanks for watching guys, and that's the end. Bye.